and Engineering at National Taipei University of Technology. And today, I'll be the MC for the opening ceremony. On behalf of the conference organizers, it's my honor to extend a warm welcome to all the esteemed scholars and professionals from around the world gathered here today. Now, let's listen to the opening remarks from our symposium chairman. Please welcome Professor Chunze Lin, an associate professor from the Department of Molecular Science and Engineering at National Taipei University of Technology.
Okay. Good morning, ladies and gentlemen. My name is Chunze Lin, for this conference, the chairman. So it's my honors to organize this conference. So I work as the Department of the Molecular Science and Engineering. So first of all, I just want to introduce for everybody about this symbol. This symbol is you can look like the Phosphor Safari. It means the P combined with S. So we make this logo. For symbol is the Phosphor Safari, and the others we also use for the colors. It means for the luminescence materials, and also look like the 8. 8 is number 8. It means in Taiwan it means the very lucky number. So we combine all of these factors together. So to design the symbol for this year's the Phosphor Safari 2024. Okay, for the categories, I think the conference we divided several parts: the infrared luminance, the nanobioluminescence materials, also the mini and micro LED. We also introduce some companies the excellent person to give the lectures about the mini and the micro LED. The last one is for the luminescence materials used in the solar photo. I think in Taiwan we also the expertise focus on the solar photo conversion, and also the plant that grows the luminescence. And last one is the others. And next one is I needed to thank all of them to support me, organize this conference. So first one is for my universities is very supportive for me, and last one is the co-organizers, the NSTC, the Chemical Society in Taipei, and next one is the NTU, is for the Advanced Research Centers, the Green, the Material, the Science Technology. And last one, I think is the sponsors that is also very important. I very thankful all of them to help me to organize this conference. Also, I needed to thank our department, the senior and the sister, because all of them we need to thanks for them support me a lot of the funding. Okay, so for this conference, I think it's very interesting for me. And when I studying the master, the first years, Professor Ruchi Liu is bring me to go to attend the Phosphor Safari. It's 2009. It's the first time organized this conference. So this conference is very impressive for me. And after the 15 years, so this time I organized this conference here. And also it's 2016, the organized this conference from Gary. So he also will come later. So set up in Hong Kong. So we have the lunch together for the photo. So it's the Professor Ruchi Liu and the Professor Andrew Marink. So the finals, I need to thank all of you and all my staff to help me to finish this conference. Thank you. Welcome. This one is the want to the make some memory hold. For the Professor Yamamoto, he is one of the organizers for the first one's the years. And next one is the Professor Professor Greenberger's. Also, he also is very expert for the physical luminescence materials. Okay, thank you, everybody.
And next, we are delighted to invite Professor Luxi Liu from the National Taiwan University to give a speech in honor of the founders of the symposium.
Okay, good morning, ladies and gentlemen. I think today is a big event in the National Taipei University of Technology. On behalf of co-chairman, I would like to make a few things for this. I think you see Taipei 101 is a very good symbol nearby here. Even you can see from your eyes from this conference site. But another big event at the same time in Paris is the Olympic game. I think that is also important for the world. So for this, as we just see the memorial movie for the Professor Hajime Yamamoto, I think he was the professor of the School of Bionics in Tokyo University of Technology. So actually, I met him in 2003 at the Phosphor Global Summit. Phosphor Global Summit is a kind of commercial conference. It's very, very expensive. Then that's the reason why when I met professor in Japan and Professor Toda told me probably he will organize another conference to compete with this, but the fee totally good fit for the academic. So that is the start of the Phosphor Safari for this conference. So then I think after I learned a lot of things, Professor Yamamoto, then I invited him to visit in Taiwan in the year of 2005 and for a week. During this week, I think he gave us 3 talks. So the first one in the Single-Tone Center, I think he used high-tech technique, EXAFs, to demonstrate some luminescence efficiency on the phosphor of strontium indium oxide. So then this is his view from the Single-Tone Center during his talk. And this is also, I did not change the front page of his talk. So the second topic give in my department, titled by the electronic energy level observed within with interest in emission color tuning. So that is good for the student to hear this kind of topic in my department. So then this is a view of him with my student. Then later on, he gave another lecture at Academia Sinica Institute of Chemistry. He gave a very good title in the nitride and the oxynitride material. That is still up to now very important material for the Phosphor Society. So this is a photo at that place. Then I also arranged him visit some Taiwanese tourist site, for example. But other than that, I think I also arranged him visit a Taiwan company, China Grace. By that time, they make the phosphor for our country And AP Star is the biggest LED makers in Taiwan. And I arranged him visit the National Palace Museum. So if you have time this time, I hope you have chance to visit this one as well. So Taipei 101, and also the Chiang Kai-shek Memorial Hall, and also the Inga Ceramic Museum. So then he also, as the Phosphor Handbook, three of the authors. So it's William Yan. He is he originated from Taiwan, and Shinoya and Yamamoto Sensei. So from this, I think I met him in 2003. And later on, I met Professor Xiaojing Wang from US. Then he talked about, he was a PhD student of William Yan. Then I realized I am also I learned the phosphor from Professor Yamamoto. So that's why we try to extend this book to more things in this Phosphor Society. Then this book was proved in the November 11, 2019. So this is a pandemic time. So it's luckily most of people have nothing to do, then they can help to write a chapter for this. So then we extended this book into 3 volumes within 2 years. So now this book is extended. So we are the follower, but we hope we can contribute more for this. So then I met Professor Merrick Greenberg in the year of 2015. We submit the joint international cooperation project together. But unfortunately, he died in 2020, even very short time, for 5 years. And we did a lot of things. For example, I attended the conference in Gdansk in 2015. So here in the background, you can see Professor Toda. Then he also visited Taiwan, give us some lectures. Then I proposed to him, probably it is good because he organized the conference for the international workshop for advanced spectroscopy and the optical materials. Then I proposed to him, why not we combine the Phosphor Safari with this conference together. Then let us meet western side with the eastern side, have a same issue for the Phosphor Society. Then this conference did very well for this. So then in 2017, we joined together with Lanzhou University, have a seminar together. So this is a photo at the background. Then he revisited Taiwan in 2017. So for this, I think much more important is before 1 year ahead of he died, then he's luckier joined with me together in Xiamen for Phosphor Safari in 2019. So you see the Professor Andrew at the background, and Professor Longjun Xie and Professor Yihua Wang. They all big contributor to this conference. So after him, I think Professor Sebastian Merlin is his PhD student, now become the head of his group. So as I said, always a young generation will follow this kind of conference. So I just attended the conference just a few days ago, July 7 to 12. So this organized by his follower PhD student. Then I think I just say hello to Professor Greenberg, okay? Then I think I did the registration very late last night with Professor Chunze Lin. So Professor Lin got a master's degree from 2005, 2 years, and continued for PhD for 4 years. Then did a postdoctor for 2.5 years. So with this, he continued with a postdoctor with Professor Andrew. So with this training, nearly 10 years, I think is very successful, not only for him to continue for the phosphor research, but also he organized this great conference. So last night, I realized it's already 9:30 p.m., but all his students all contributed to our conference. So that's why I hope with this hard work, I hope you are enjoying with this conference in at this event, Phosphor Safari 2024. So thank you very much.
Thank you, Professor Liu, for the speech. And next, let's listen to our distinguished guest to give us welcome remarks. First, please welcome Professor Chong Guangyang, the Vice President of National Taipei University of Technology.
Respected conference committee, speakers, professors, research fellows, and all the distinguished guests. On behalf of all my colleagues from Taipei Tech, I would like to welcome you to the 2024 Phosphor Safari, the 13th International Symposium for Luminescent Materials. In the past 13 years, this conference has been an influential platform for many scholars whose work related to the lights. Under the guidance of the conference organizers, this symposium is to foster the cooperation and talent development for the luminescent research. This program provides a unique opportunity for all the participants to deepen their understanding and fundamental research, engage in discussion on science and technology issues, and I believe more creative ways will be developed to enhance luminescent materials and techniques for sustainable development as our research goes. Finally, I wish to wish everyone a fruitful and inspiring experience from this conference and enjoy your stay in Taipei City. Thank you very much.
Thank you, Professor Yang, for your inspirational speech. Next, please welcome Professor Kenji Toda from Niigata University, Japan.
Good morning, and ladies and gentlemen. So I'm Kenji Toda from Niigata University, Japan. I'd like to talk about some concept of the Phosphor Safari. And Phosphor Safari is a very strange name of the conference. Okay, and very early times, so we talked about such a very flat conference on the summit of the Yahiko Mountain near our universities. Okay, and so I said, very peaceful, very flat, and very cheap, not expensive. Also, Global Summit is very exciting and very interesting, but very expensive. So very and flat conference, and this is my dream, I said. Yamamoto Sensei has also said, yes, your dream is also my dream. He said, my life is limited, no time. So if your dream come true, this is very happy to me. So Yamamoto Sensei's talk. Okay, and return from the mountainside. So I said, my labs, Dr. Ishigaki said, he makes a website only one day. Then he said, what's the name of conference? I think Phosphor Safari. Safari is hunting? No, not hunting. Safari is African language, Swahili language. This means a very, very long international journey with your friend. So, Phosphor Safari concept is Phosphor Safari is very flat, And we are standing on the flat savanna. So we are friends. So basic scientist, application, the company, inorganic chemistry, organic chemistry, yes, okay. Chemist and the physics and the researcher, okay. And all member is good and a friend. So we enjoy very, very long international journey with your friend. Okay, and another one is Phosphor Safari, and changed my life also. Professor Toshiyuki Masui, he is now president of Rare Earth Society of Japan. So now he is my son. He became my son. This means my daughter and Professor Masui is now married. So I have two granddaughters. So I am a very old man. Okay, please enjoy this very long international journey. Thank you very much.
Thank you, Professor Toda, for your inspirational speech. And today, to capture today's precious moment, we cordially invite everyone to take a group photo. And we will provide the conference logo and kindly request our guests to hold it for the group photo. Okay, now just look forward and smile. Thank you, everyone. And during this conference, we have arranged for speeches, oral and poster presentations, a banquet, and sightseeing excursions, ensuring our esteemed guests can fully enjoy all the scheduled events. As the opening ceremony comes to the end, I'm Chen Wang. On behalf of Phosphor Safari 2024 team, extending our heartfelt gratitude to all attendees, wishing you a wonderful day ahead. Thank you.
这个你把它打开来。My slide。喂。Okay, cool.
Okay, good morning, ladies and gentlemen. I'm first and chairperson for the first plenary speaker. And Professor Ming Peng. So, okay, this is a great honor to introduce Professor Xi Ming Peng. And so he is a very famous professor, okay? And his now current position is distinguished chair president for research. And he's a very famous and professor in the world. So especially complex chemistry. Sometimes, I feel the very beautiful complex and material, the very strange and linear, good morphology of complex material. So such a material is only limited to Phosphor material. One another thing very important for the organic electronics. Okay, so he has many hours. So if I talk all hours, so no presentation time. So please show the textbook. So okay, Professor Penn's title is from metal multiple bonds to helical metal strings.
Okay. 小田先生、どうもありがとうございます。どうも。It is my great honor and pleasure to be invited to the Phosphor Safari 2024. I'd like to thank the organizing committee for this invitation, although my research field is not really closely related to luminescence material. And I also like to thank National Taipei University of Technology for hosting this event. I formally retired from National Taiwan University 5 years ago from when I was 70 years old. But university still kindly offered me a title, Distinguished Research Chair Professor. With that title, I keep my office and fool around the chemistry department until now. I also get the research support from Institute of Chemistry Academia Sinica, which I hold the adjunct position. So these two are my institute, and I'm attending this conference for my first time. Today, I'd like to present Today, I'd like to present my research for the past 3 decades on metal-metal multiple bond and helical metal string. The outline is as following. First part is so-called homonuclear metal string. I synthesize and study the structure of newly designed ligand with the unique metal string complex. Here's my molecular model made by Professor Biao Jin. This is called bead model. Bead means chemical bond. So this is the bond model of my complex, which I will present today. And of course, as I found the title, I will study the multi-nuclear metal-metal multiple bond. Okay. Then use ATM break junction method to study the single molecule conductance of this class. And then had moved to the synthetic a new synthetic method to new generation of the metal string. This is the first part. The second part will move to the heteronuclear metal string. Even for trinuclear metal string, you will see the ABA, AAB, ABC, many this kind of metal string, and also go to pentanuclear metal string, like nickel, platinum, cobalt, cobalt, palladium, or molybdenum, molybdenum, nickel, molybdenum, molybdenum metal string. At the end, I will give the short conclusion. This field is called molecular electronics. In the cover, you will see almost an organic one. Today, I will present our metal string complex, possess all of this property. This field is very close related to the molecular machine, which is recognized by Nobel Prize in 2016. For chemists, we are interested in chemical bond. Chemical bond is the quantum mechanical approximation between two atoms. Normally, for organic people, talking about carbon-carbon bond. For low oxidation state of the transition metal, using d orbital, we can form similar sigma bond, pi bond, and unique delta bond. Our Cotton discovered the metal quadruple bond about 60 years ago for the metal quadruple bond. At the beginning of my research, the organometallic people talking about metal carbon bond. Okay, of course, this field is also mature in last century and get many Nobel Prize recognition for organic synthesis. At the beginning of my research, I like to extend our cotton dinuclear metal multiple bond to trinuclear, then to oligonuclear. So we have the new type of bonding, namely oligonuclear, multinuclear, metal multiple bond. You want to develop new chemistry, then you have to design new ligand. The new ligand designing ours is this oligo alpha pyridyl amino ligand. Has the amino group connect to the pyridyl group. As you know, the oligopyridyl is very important class of chelating ligand. And you add additional amine group, then you will form similar chelating complex. But under better condition, you can have the bridging type. So you can see the picture now. So for the past 3 decades, we synthesize, this ligand is interested in themselves because by shifting one base pair, they form perfect double helix. In solution, acidic condition, you will form single helix. Under best condition, you get deprotonation, then you have the quadruple helix. In the past 3 decades or so, we synthesize trinuclear metal complex as many metal ion, tetranuclear complex. As long as we have the ligand, then we have the method to synthesize the metal complex by the deprotonation of amine group. In terms of metal bonding, the 4D orbital has best overlap. So here is the example of trileucinium complex. Molecular orbital calculation, because you have the 3D orbital, then you will have the, for example, this 2 sigma orbital become bonding and non-bonding and anti-bonding, okay? Degenerate pi orbital has bonding, non-bonding, anti-bonding. Because the helical structure, the delta bond is really weak. For this trileucinium complex, we simplify, have 3 bonding orbital, 6 non-bonding orbital, 3 anti-bonding orbital. Populate of 18 electrons will give to the sigma non-bonding. So resulting this trileucinium has triple bond. 3 bonding pair give you bond length of 2.25. It's quite short. Then actual ligand play important role in metal-metal bond. Coral is the so-called pi-base ligand. If you move to pi-AC ligand, called cyanide, because this pi-AC ligand will interact with this anti-bonding metal-metal bond. It lowering the energy than the sigma non-bonding. So they will populate this pi star orbital, and also this is diamagnetic. This is paramagnetic with 2 ampere electron. So this will give you from the previous 2.25 to 2.37. Then we claim this is only double bond among this trileucinium. We can further move to the trilodium complex. Trilodium has 21 electrons. You will populate 3 anti-bonding, and resulting the bond length to the 2.39, okay, is only 1.5 bond order, okay. We can take out this electron by oxidation that then give you cationic species, shorten the metal-metal bond to 2.36. So we have very good explanation for the trinuclear metal-metal bonding. So this is our cotton quadruple bond, has a bond length about 2.09. And those are the something leucinium, rhodium between. And I already explained to you this trirhodium, trileucinium metal-metal bonding by the simplified molecular orbital. Very interesting is for the nickel. Nickel is most easily synthesized and high yield, but the bond order is 0 because you will populate all the bonding and anti-bonding orbital. But as I mentioned, it's most easily synthesized one. The nickel-nickel distant 2.43, although it's short, but we still claim the bond order of 0. And from the structure, inner nickel had short nickel nitrogen distance, is low spin. The terminal one is square pyramid, high spin. So the electronic structure are following. This will be spin of the 1, and diamagnetic, nickel 2, and they show the antiferromagnetic coupling, okay, depending on the actual ligand. And this is the diagram showing how these two show the antiferromagnetic coupling. So from 3 move to 4. The diputyl diamine ligand is asymmetrical. Actually, you can imagine that when you have quadruple, you have many possible isomers because they are asymmetrical. We are lucky enough to have the structure of this 2,2,6 isomer in crystal structure. Okay, so in all the nickel 2 are low spin, and this is diamagnetic, and this is the 2,2,6 isomer. Moving to 5, we synthesize this new ligand. Actually, when we do the synthesis, there's no report about this simple compound. And this can be synthesized to pentanickel complex. And when the mass spectrum come out, jump up because the parent peak is identical to those isomer distribution. But of course, we still get the structure of this penta-nickel complex. Again, all the inner nickel are low spin, outer nickel are high spin. Now, the antiferromagnetic coupling is much weaker, and I just omit the 3 carbon of the pyridine ring and become the so-called pendragon. Yeah, we have the 4 quadruple ligand, and this pendragon were growing every year. Okay, now the antiferromagnetic is much weaker. Move to cobalt, D7 system. Now we have metal-metal bonding. This cobalt distance is about shorter than the previous nickel, about 0.1 angstrom. And actinic Hugo molecular opposite calculation showing that the 2 sigma antibonding are empty. So among this pentacobalt moiety, we have the double bond among this pentacobalt moiety. If you divide by 4, that means each cobalt has half sigma bond. Okay, moving to 9. Synthesize the ligand and then get the complex. This is normal bond and stick model. In my hand, as I already showed you, this is the bead model of the same complex. Bead model. The bead represents the bond. So this is the bead model of my complex. This is the milestone metal string in 1999. So actually, I already synthesized the 17 nickel metal string. Okay, the 17 is just one pitch of the quadruple helix. Okay, one pitch. So it means I can synthesize any size, although limited by the yield, also called entropy effect. Some picture to entertain you. This is the double dragon in Shenyang, mainland China, although they are in mirror image. This is in Howard International House. They have also beautiful quadruple brick pillar. This is in Scuba. In 2016, we have also a very beautiful art piece with my metal complex. Okay, nowadays we can attach the molecule to 2-gold gate by the actual ligand, okay, so-called STM break junction, and experimentally and also theoretically study that. And this is the result. This is the experimental IV curve for trichromium, tricobalt, trinickel. Chromium is better conduct than the cobalt, than the nickel. Theoretical study that nickel and the cobalt are very close, quite close. Chromium is not so close, but it's acceptable anyway. With this theoretical model, we can calculate the so-called local current analysis, how electron goes through the metal complex. The answer is that 99% it goes through metal, although the ligand is conjugate, but only small amount. In the popular science sense, this is the world's smallest or thinnest metal wire. That means mimic the microscopic metal wire. It is now to single atom, and metal string is conductor, ligand, insulator, really like those PVC. This is in the popular science sense. And we can study that by the homologue, and all those are comparable to the organic conductor, okay, to even the conductant or the decaying or beta, and all are comparable to organic wire. And furthermore, my colleague can get the so-called potential stat, connect to the two tip and keep the potential moving. That means you are scanning the Fermi level of the electrode. That means you're scanning the Fermi level of the electrode and get the spectrum. Those are the energy level of the metal complex. Similar, this is the cobalt, because cobalt has more redox property, so you can have. Okay, now move the new generation of the metal string. When I was a graduate student, I already know the naphthalidine is a good ligand, although it's stabilized, low oxidation state. So we moved to dinaphtalidyl amine group, then it's less anionic. So it's more easy to stabilize nickel 1, nickel 2 mixed valent complex. The most important thing is that the conductant, we have another electronic structure which I now focus on. And interesting is that the conductant is increased by about 40% by introducing this mixed valence unit. So we have studied many, because this mixed valence unit has the redox property. We can study the interaction. And in 2009, we synthesized the tetranaphtalidyl triamine, and has 3 and 4 nickel 1, nickel 2 mixed valent unit. So we get all the crystal structure, and this is the ball and stick model. Again, this is another one. Is the naphthalidine group is much rigid, so more easy to synthesize and more easy to crystallize. So this is the molecule in our department. When our new building was finished in 2009, that time Peter Zhou was the chairman, and he honored me by putting my molecule in the entrance hall. Okay? If you visit our department, you will see my molecule. And longer and longer, I think due to the time limit, I just skip also. This is another new mixed valent unit by introducing the so-called anthracene deal, that all the nickel, all the nitrogen are neutral. So now they have the new trivalence mixed valent unit, nickel 2, nickel 1, nickel 2. Very interesting electronic structure. Anyway, we also can control the chirality by introducing the chiral group. This chirality controls the chirality of quadruple helix. Now move to heteronuclear metal string. That means you will have the, like a metal alloy, you will have new chemistry and physics. We have the synthesis of strategy. You will see that how it works. So I only present 3 classes of mixed valent unit. One is the Da metal in the center. The terminal can be from D5 all the way to D6. Another unit is the dileucinium have strong metal-metal bonding, they can catch the third metal in this way. And also dirodium is quite similar. So paramagnetic MMR is also very diagnostic for symmetrical and unsymmetrical metal stream. This is the cobalt, nickel, cobalt. The MMR of this hydrogen only 4 peak because they are symmetrical. If I have the cobalt, nickel, nickel metal complex, it's unsymmetrical, so this 4 will split into 8 peak. So this MMR will be very diagnostic for symmetry. The first heteronuclear metal string we synthesize is cobalt, palladium, cobalt. Actually, the electronic structure of tricobalt is very interesting. They have the spin crossover property, okay? But when we cook with palladium and cobalt together, I'm not used to that. Palladium will locate at the center with most high yield because this nitrogen has more strong field. They prefer Da metal. Then from this one, we can further get the terminal. We can synthesize from all the D5 to D10, become ABA. Furthermore, we can substitute, this is another one, copper, nickel, or palladium, copper. And this is ion 2, ion 3 mixed valent unit with this class of the metal string. They show all the interesting property. That means the central atom can play some kind of magnetic insulator. For the nickel one, because their energy is similar, so this is delocalized ion 2, ion 3. For palladium and platinum, they are localized. Palladium, ion 2, ion 3. Furthermore, we can study the substitution of the terminal metal by the third metal ion. And our study shows that nickel will substitute cobalt, will substitute iron and manganese. This is same series as Irving-Williams series of the coordination chemistry. And we can show many trinuclear metal complex we have. For example, this is nickel, palladium, copper, many of this kind. And when we cook with these 3 together, then the lutetium 2, 3 will stick together, and the most labile first row transition metal will at the 3rd position. Actually, we can synthesize the lutetium, cobalt, then can kick out the cobalt by ammonium aqua. Then we get this dinuclear metal complex. It acts as a chelating group to catch all the third metal ion at this periodic table. So they can catch all the third metal ion. And this is just say like the metal crème in the cover of the garden. And similar, dirodium has 2,2 trans dinuclear complex, and also can catch the third metal or fourth metal to form heteronuclear metal string. Go to pentanuclear metal string, it's much, much complicated. For example, cook nickel and lutetium or cobalt with lutetium together. Very interesting is that in the nickel metal string, we can get nickel, lutetium, nickel metal string. Lutetium located at 2 and 3 position. In the cobalt, we get the lutetium, cobalt metal string. Of course, we have our simple explanation, but still quite complicated. Then the other people will ask you what new for this heteronuclear metal complex. When we measure the single molecular conductance, the mixed valence complex, the conductance just between the more conductant ruthenium and less conductant nickel, it just, the value just lie between. But interesting is that in the nickel ruthenium nickel metal stream, mixed metal stream, we observe so-called NDR effect on this one. And we cannot really give the good explanation, but from this diagram, the red line representing the IV curve of the nickel, green line representing the IV curve of ruthenium, and this black line just saying in some potential, the mixed valence, the metal string act like ruthenium in some potential. In some other potential, it act like nickel. So you can switch these two types by different potential. And we try to publish that, but the physics give very bad comment, but still we publish the synthesis. Another one is for stereometric. Some people ask me, of course, this is the racemic chiral one, and most the product is racemic mixture. You have this one and other kind. And when people ask me, is there has the meso position, because this the meso is that has the mirror image that the upper half is left hand, lower half is left hand. But in this monomer, nickel monomer complex, it has this stereochemistry. So, and the quadruple bond play important role. Okay, for synthetic purpose, this is the last one. How we synthesize this nickel, platinum, cobalt, palladium heteronuclear metal string. At the beginning, as I say, we will cook the cobalt with palladium or platinum together. Platinum will go to the amido position, so we can get the highest yield in cobalt, platinum, cobalt, cobalt, cobalt. Then we try to put the palladium in the fourth position. Then we can also then substitute the terminal. But unfortunately, the palladium go to the fifth position. So we purify each step, cobalt, platinum, cobalt, cobalt, palladium. And then finally, we have the nickel substitute the cobalt, become nickel, platinum, cobalt, cobalt, palladium metal stream. So this is the milestone metal stream in 2019. Yeah, and this become cover, and my friend matched the music Star Trek for me as my metal stream floating in the space. They were evolving finally to this nickel, platinum, cobalt, palladium complex. Okay, give the conclusion. As I mentioned, I tried, I think, out cotton dinuclear metal bond from quadruple bond to trinuclear metal stream. And simplified molecular orbital is 3 bonding orbital, 6 non-bonding orbital, 3 anti-bonding orbital. This is a build-up principle, and I illustrate this part of the metal stream and become longer and longer. And it has a unique metal string complex. And then the single molecular conductance by STM break junction method. And then the new generation introducing the mixed valence complex and increase the conductance and the chirality control of this heteronuclear metal string, and finally the heteronuclear metal complex. Okay, this is in Chinese, that we synthesize world's thinnest metal wire and one-dimensional and measure the conductance This is all kind of the metal string complex we synthesize. And thanks to the supporting from National Science Council, NTU, MOE, Academia Sinica, and my collaborator, and all my students. And this again showing the metal string in chemistry hall. Thank you for your attention.
Thank you very much for exciting talks. Okay, it is a great, great chance for the young researchers, especially. Our knowledge and the link for the future. Okay, any question or any comment? Oh, so please use some mic.
Hello, Professor. Thank you for your informative and interesting talk. So I'd like to know, the concept of metal strings is very new to me. And I'd like to know the complexes you have discussed. So how about the, does the environmental temperature conditions affect the synthesis? Because when it comes to inorganic complexes, some can be synthesized in summer and sometimes it doesn't form in the winter. So does these complexes have such kind of complications? Okay. So my question is, so yeah, so can these complexes be synthesized in like throughout the year? Because some inorganic complexes are, it doesn't form in winter.
Sorry, I didn't catch your question because my hearing is decaying.
So I mean the stability of complexes.
Temperature? Huh? Oh, I think so. They are all stable.
Okay.
Stable in air, stable not in aqua. They are all stable, and I can go crystal in solution for months.
Okay.
All my complex are stable, air stable.
Okay, thank you.
Any question? Any comment? Maybe. So, Andrew, do you have a discussion?
Okay. you want to request?
Yeah, very, very impressive molecules. I always admire the organic chemists and the patience they have to do those very long syntheses. Your talk really focused on the D6, D7, D8 transition metals.
Yeah.
I missed the D2, D3, D4. Can you do the same tricks and make the strings with the lighter transition metal elements?
Yeah.
Like vanadium, chromium, and manganese.
We tried the early transition metal, but in most cases they fail because in this metal string, the ion will, in the oxidation state, it will be low to 2 or 3. But the early transition metal, for vanadium, they are stable in 4 or 5. Yeah. And in 2 or 3, vanadium is very unstable. And anyway, we try, but not succeed.
Okay, thank you.
So you will see that many are late transition metal.
Thank you.
Okay, any question? Okay.
Thank you, Professor. You mentioned about anti-ferromagnetic, right, in your presentation. I want to know how we classify as anti-ferro. I just know like paramagnetic, diamagnetic from spin up, spin down, and how we know this is anti-ferro.
How I study the anti-ferromagnetic?
Yeah, you mentioned about that. Can we know from spin of the molecular spin, like spin up, spin down?
Yeah, we study the temperature-dependent magnetic property. We study the temperature-dependent.
It's depend on temperature.
Yeah. Because if you are only paramagnetic,
Yeah.
the moment you were independent of the temperature. But if you have the antiferromagnetic coupling, the magnetic moment will decrease upon temperature. So we do all this study by SQUID, so temperature-dependent magnetic property.
Okay, thank you very much.
Do you have comment? Question? Okay. Thank you very much for a very interesting, exciting talk. Okay.
Thank you for your attendance. Thank you so much.
Thank you very much. Okay. We have a quick time. 10:30, and we will start again. Okay. Please come back.
Okay, next slide. So it's my great honor and to chair and the next and three preliminary and speakers. And first, I'm introduce myself. My name is Qinghua Xu. So in both Taiwan and mainland China, the university whose name is Tsinghua. So that's my name. Myself was trained on femtosecond laser spectroscopy. So actually, this is the first time for me to join this conference. After I was trained on femtosecond laser spectroscopy, and after I went to Singapore, National University of Singapore, I started to work on the long-range optical property of nanomaterials. So for me, for this conference, it's a great opportunity for me to learn about optical materials. So the next speaker, the first speaker of this session is Professor and Mayor Rank. Sorry, it's very difficult for me. Mayor Rank Universities and from whatever universities. And the professor and Mayor Rank, the major areas is on the optical spectroscopy and also the bioimaging applications and of the quantum dots. And also from his experience, is a long time and pretty much from the students and also really all time to attach these universities and working in this area for a long time. So please join me and welcome and professors and Mayor Rank. Yeah, please, thank you.
Yes, thank you, Chairman, for the nice introduction. It's a real pleasure for me to be here. I'd like to thank the organizers for inviting me. It's not my first time in Taiwan. I really like Taiwan. And in 2013, I had a longer visit hosted by Professor Ruxi Liu, and I experienced my first and so far only earthquake, which was quite an experience. So today, I will talk about next-gen doping dots. And I will start with an introduction. And after that, I will talk about old-gen doping dots, the 2,6 semiconductor quantum dots. I will talk about doping transition metals and lanthanides. Then I will go to the next generation, the very popular perovskite quantum dots. Again, transition metals and lanthanides. And I will end with conclusions. So maybe first a short introduction about where I'm from. I'm from Utrecht, and I know that's really hard to pronounce for foreigners. We have our nice from Utrecht. It's in the Netherlands. It's a small country. It's here. And Utrecht is right in the middle of the Netherlands. At the tip of that blue arrow is Utrecht City, 250,000 people, very small town. But a very nice university. It's the biggest in the Netherlands, and I also like to say it's the best university in the Netherlands. We've had 12 Nobel Prize winners. We're pretty high in the Shanghai Index. This is the Dom Tower, the highest tower in the Netherlands. Next to it is our academy building, where we have beautiful ceremonies. And this is our laboratory, and my room is there. So if you ever visit Utrecht, you're welcome to visit me as well. Now, the Netherlands is a small country, but we have a long history. And in fact, we also have a long history with Taiwan. And this year we celebrated 400 years ago. We came to Taiwan, and in fact we occupied part of Taiwan. So in 1624, the Dutch East Indies companies founded this regional trading zone, Zeelandia. And this is Zeelandia Castle in the Dutch city. And that's in the southeast point of Taiwan. And well, I call it old gender relations, because we kicked out the original inhabitants. Flew over or brought over some Chinese workers. And also we had our first attempts to propagate the Dutch Reformed faith, and that was encouraging. We always try to convert people to our religion. Of course, that's the old generation. And then 40 years later, we were kicked out by the Chinese. But here you can still see the old Fort Zeelandia here at the southeast of Taiwan. So that's the old gen relations. We still have very strong relations with Taiwan. And I call that next-gen relations. In the Netherlands, we're very proud that we make the only extreme UV wafer steppers at ASML. We're the only one who can do that. So we make the best machines to make chips, and then TSMC in Taiwan makes the best chips. So that's our next-gen relations. And I think they're much better than the old-gen relations. So let's now go to quantum dots. Nanoscience is very popular, but in fact, nanoparticles have a long history, and already in Roman times they used metal nanoparticles, gold nanoparticles. Of course, they did not know it was gold nanoparticles, to make beautiful colored glasses, and also stained glass windows from the Middle Ages contain metal nanocrystals and semiconductor nanocrystals. Then the first one to realize that the optical properties of nanocrystals were affected by their size was Faraday. He looked at gold nanocrystals, and he had gold and blue and different colors of gold nanocrystals, and he already realized that the different colors of his solutions with gold nanocrystals, that known phenomena appear to indicate that a mere variation in the size of its particle gave rise to a variety of resultant colors. So that's the first time that people realized that you could tune the color by changing the size. And of course, Faraday didn't know they were nanocrystals, had no idea how big those gold nanocrystals are, but he was a genius. And then the first report of what we now know as quantum confinement, quantum size effect, that the band gap of semiconductor nanocrystals changes as a function of size. The first report that I could find was an article by Jekyll in Zeitschrift für Technik und Physik, and yes, 1926. And in the 1920s, German was the language of science, so sadly it's in German for those of you who don't speak German. But Jekyll wrote, die Fluoreszenzfarbe und die Absorptiongrenze der gelben Cadmiumsulfidgläser verschiebt sich nach den langeren Wellen, was auf ein Wachsen der färbenden Colloide zurückgeführt wird. So what he says, we see a shift of the absorption edge to longer wavelengths, which can relate to a growing in size of the colloids in the glasses, the cadmium sulfide colloids. So we already realized that when the cadmium sulfide nanocrystals become bigger, the band gap narrows. And of course now we know that quantum confinement, the big discovery of quantum size effect was in 1981, 1982, independently by Bruce and Akimov, and they explained the change of the color of cadmium selenide and also other semiconductor nanocrystals by a changing of size. When you come in the size range of the exciton Bohr radius, when you make the crystal smaller and smaller, you confine the charge carriers, the electron in the conduction band, the hole in the valence band in a size, in a space that is smaller than the natural extension in the bulk semiconductor. In the bulk semiconductor, the wave functions of electrons and holes are pretty extended. And if you make the size of the nanocrystal smaller, then you squeeze them in a box that is too small, and the energy increases. So the energy difference between the top of the valence band and the bottom of the conduction band becomes bigger, and the emission color changes from, in the case of cadmium selenide, from infrared to red to green to even blue. So those are quantum size effects. When the particles become smaller than the Bohr radius of the exciton, you see two things happen. The band gap shifts to higher energies, and also you start to get discrete energy levels at the edges of the bands. And the reason being that at the edges of the bands of the bottom of the conduction band, the top of the valence band, the density of state is low, and when you make them very small, when you have 100 or 500 molecules of cadmium selenide, you get discrete energy levels. You see discrete absorption lines. So that's important and nice. Another important effect is that the quantum yield becomes very high. If you have a bulk semiconductor, you have electrons and holes. When you excite an electron to the conduction band, the electron is very mobile, it can just move around, and no matter how hard you try, there's always defects present, and you get non-radiative quenching by those defects. When you make a nanocrystal of 5 or 10 nanometers, the defect concentration may be the same, but there will be many nanocrystals without the defect. So if you make an electron hole pair, the electron cannot go anywhere, it cannot probe a large volume where there might be a defect. So the quantum yield of quantum dots, different from bulk semiconductors, can be very high, 95 or even close to 100%. So those are two important effects of quantum dots. And here you see some cadmium selenide quantum dots that we made in our lab. It's all the same material, it's all cadmium selenide. The only thing that varies is the size. So these are about 2.5 nanometer nanocrystals. These are 6 nanometer crystals. All the same material, same crystal structure, everything the same. The only thing, you change the size. When you change the size, when you make them bigger and bigger, the band gap gets smaller. So that was Bruce and Akimov in the 1980s, and a lot of work was done, but then a big breakthrough came in 1993 when this article was published in the group of Monge Bewendi, where they discovered a new method, the hot injection method, to make highly efficient and highly stable monodisperse quantum dots. And here you see me doing this hot injection, watched by Stelsel de Mello from our group, real quantum dot expert, and this is the reaction mixture. So that really made it possible to make reproducible, monodisperse, highly efficient quantum dots, and for applications that was very important. And of course then, last year, the Nobel Prize in Chemistry was awarded to Bewendi, Bruce, and Akimov for discovery and the synthesis of quantum dots. And that's beautiful fundamental work, but also found applications. You can find them in the QLED televisions from Samsung. There's cadmium, selenide, or indium phosphide quantum dots. And also for lighting, they have been used to convert blue light to nice deep red light. So they also find application. And 10 years ago, we, and that's Dubertret, Rice, and me, we organized a meeting in Paris to celebrate 30 years of quantum dots. And yeah, they were all there. Bruce and Bewendi and Akimov, who now have received the Nobel Prize. So that's all very nice. Highly efficient emission, rather narrow band, you can tune it everywhere. So why would you want to dope quantum dots? So I will explain why, what kind of dopants we put in, and also how we can dope quantum dots with luminescent ions. But first the why. Quantum dots are wonderful, but one disadvantage of quantum dots is that the emission is resonant with the absorption. So you get reabsorption effect, and well, the absorption also determines, the absorption edge, the band edge of your material, also determines where your emission is. You cannot independently tune the emission from the absorption spectrum. If you put in luminescent ions, then you can have the emission from a luminescent ion combined with the very strong tunable absorption of your quantum dot. So by combining efficiently luminescent ions of emission from dopants with quantum dots, you can have this larger Stokes shift, less reabsorption. You can tune the absorption and the emission independently. Emission is driven by luminescent ion, absorption by the size of your quantum dot. You're less sensitive to surface defects. In a quantum dot, the wave functions are extended over the full quantum dot. And if there's something bad at the surface, the luminescence will be quenched. But if you have a dopant, and the dopant catches your exciton before it's quenched, you're less sensitive to surface effects. And also you can have multiple emitters in one nanocrystal. If you have many dopant ions, they can all luminesce, whereas when you have a single quantum dot, you can have blinking effects, there's only one emitter. So those are all advantages of doping quantum dots. Another reason is that there was a very important article in 1994 in Physical Review Letters by Bargava, and he reported that manganese doped into zinc sulfide nanocrystals had a nanosecond lifetime. And that was quite spectacular because the efficiency was 18%, so the radiated recombination rate seemed to be enhanced very strongly. And he wrote that, quantum efficiency of 80%, luminescent decay time 5 orders of magnitude faster, and that shows that it's a new class of materials. Sadly, we showed later that that short lifetime that Bargava measured was not manganese emission. Manganese had just a normal spin forbidden, parity forbidden millisecond lifetime. He measured some defect emission and missed the long lifetime of the manganese emission. So, yeah, there was no spectacular shorting of the lifetime. A paper recently done by Egheid Boll in my group. But still it served to really boost the research on doping quantum dots. So, what do we want to dope? This is the periodic table, and every green box is an element that has been used in some kind of application in luminescence. So for displays, for lighting, for X-ray imaging, for bioimaging, all those green boxes have been used. And the most prominent luminescent ions are the 3D transition metal ions and the lanthanides. So those are also the ones that we will try to dope. Transition metal ions, transitions within the partly filled 3D shell, and the energy levels and the luminescence is explained by Tanabe-Sugano diagrams, and it strongly depends on the host, the crystal field splitting, the energy difference between the energetically favorable d orbitals and the energetically unfavorable d orbitals varies as a function of covalency, as a function of the ligands, so you can tune the emission very strongly. Those are the transition metals, and then we also have the lanthanides. For the lanthanides, we have transition in the partly filled fresh shell. that is shielded by a filled 5s and 5p orbital, so they are independent of the matrix. The lanthanides always give the same luminescence, and just as an example, we see here the emission spectrum of terbium-3+. This is the end level of terbium, no matter what the environment is. They have sharp atomic-like emission lines, independent of the matrix, high quantum yields, and long lifetimes because they're forbidden transitions. So those are the two types of dopants that are widely used for luminescent applications, and those are the two types of dopants that we try to get into the quantum dots. Then how? After this paper by Bagava, there was a rapid increase of trying to dope the 3D transition metal ions into the different types of 2,6 quantum dots, zinc sulfide, zinc selenide, so a 2+ element and a 6 and the group 6 element, 2- element. And for some it was easy, but not for all. And there's a very famous Nature paper from 2005 where Dave Norris wrote, despite some successes, many of the efforts have failed for reasons that remain unclear. For example, manganese can be incorporated into nanocrystals of cat sulfide and zinc selenide, but not into cadmium selenide, despite comparable bulk solubilities of near 50%. So in the bulk you can put manganese, replacing cadmium 2+, but in the nanocrystals it didn't work. And well, Norris had some explanation. He had some explanation that it was kind of kicked out because it was energetically unfavorable, but it was impossible to dope manganese 2+ into cadmium selenide. Then also, there were many papers that reported lanthanide 3+ ions into 2,6 semiconductors. And they showed when you excite in the UV, they showed nice lanthanide luminescence. But what was lacking in all those papers, and there's many papers, is an excitation spectrum of the lanthanide luminescence. Now, if you excite your solution with your 2,6 nanocrystals, your quantum dots, and you have also added some lanthanides, you excite in the UV, yeah, then it kind of makes sense that you see some sharp emission lines. But that does not prove that those lanthanide ions are inside your quantum dots. To prove that, what you have to do is you have to take an excitation spectrum of your lanthanide emission. If in the excitation spectrum of the lanthanide emission, so you put your emission monochromator, emission wavelength of your lanthanide line, you scan the excitation spectrum, and then if you see your quantum dot strong absorption spectrum, yes, then you know, exciting my quantum dot, get energy transfer to lanthanide, then they're inside. But if you don't see that, if you just see your sharp lanthanide lines, yeah, then they're not in there, then they're somewhere in the solution and you see lanthanide emission, but they're not incorporated in the quantum dots. And all those papers observed the emission of lanthanides, but they did not show the excitation spectra. So again, Agate Bold wrote her second negative paper. We reproduced all those synthesis methods, tried to see if the lanthanides were in there. They were not in there. So you can also understand that because the lanthanide ion does not like 4 coordination. It's too small. They like 6 coordination, 8 coordination, but never 4 coordination. So, yeah, second negative paper, but still I think it's important that we also publish when we think something is not correct. And that doesn't mean that the authors have done a bad job. They can be, well, being careful, but it's also good to disprove things that are published in literature that are not true. So Agate wrote, the absence of a host lattice excitation band indicates that the presently used synthesis techniques, the rare earth ions, are not incorporated into the nanocrystalline semiconductor particles. So, now let's talk about doping the 2,6 quantum dots, the old generation quantum dots with transition metals and lanthanides. Since the 2000s, many new doping methods, they call next generation doping methods, have been developed. I will discuss 4. Single source precursor method. In the single source precursor method, in the old methods you had a cadmium precursor, a selenium precursor, you heated them up together or you injected them and then the cadmium selenide nanocrystals formed. In those single source precursor methods you have one precursor molecule with both cadmium and selenium. And if that decomposes, you also get cadmium selenide or other nanocrystals. So using a single source precursors helps to incorporate dopants. Another method is cation exchange. You first make your quantum dots, your nanocrystals, then you boil them in a hot solvent and you add a high excess of another cation ion that you want to get in, your dopant cation, and then there will be exchange of your cation ions, and in that way they can get in. The third method is adsorption of your dopants. So you again make your nanocrystals first, your quantum dots. You add the dopant ion, your lanthanide transition metal that you want to incorporate. And then you also add the N-ion precursor. You heat it up, and then it will adsorb, and the overgrowth of with your N-ion precursor will make that you get your dopant ion into your nanocrystal. The fusion doping is somewhat related. Again, you first make your nanocrystals, and then you add your cation dopant and the anion precursor, and then the surface layer of your dopant ion with the same N-ion will be formed, and slowly, in time, your dopant ion will diffuse into your nanocrystal. So those are 4 methods that have been successfully used to dope nanocrystals with luminescent ions. First, cadmium selenide manganese. That was work done together with Daniel Gamelin and Remy Bullock from University of Washington in Seattle. There we use a single source precursor method, so this cadmium selenium precursor. If you decompose it in the presence of a manganese precursor, you get incorporation of manganese 2+. Even though Norris in 2005 said it's a mission impossible, with this method it gets in. And when you then excite, you see both, this is a rather low manganese concentration, you see both manganese emission and still some exciton emission from your cadmium selenide, and it has a very nice and unique temperature dependence. This is the undoped, there you have an exciton emission with an exciton lifetime of typical nanoseconds. When you incorporate manganese, then you also, your exciton is trapped in your manganese, but it can be back transferred from your manganese because it has a very long lifetime. It's a spin and parity forbidden transition. There's a millisecond lifetime. You can get back transfer from your manganese to the exciton state, and you see delayed, slow exciton emission with a microsecond lifetime. So if you look at the emission spectrum as a function of temperature, then you see that at low temperature you have dominant manganese emission, but when you start to heat up, then the exciton emission at higher energy will be fed by your manganese, and you get slow excitonic emission. So as a function of temperature, the exciton emission goes up, and the lifetime is initially very long, and then it slows down to about 4 microseconds at room temperature. So also this is a very nice luminescence thermometer. That's also a very popular field these days. People want to use luminescence spectra to measure temperature. Here both the intensity ratio between the exciton emission and your manganese emission is a function of temperature. And also the lifetime of your manganese is temperature dependent and can serve as a luminescence thermometer. Then lanthanides. Well, I just told you, getting a lanthanide ion on a 4-coordinate site is, well, kind of a mission impossible. We tried it anyway, and we kind of succeeded, but not really. So, the system that we chose was cadmium selenide with ytterbium 3+. The reason to choose ytterbium 3+ as a lanthanide ion, that it has a very nice and simple energy level scheme. It's here at the end of this Dicke diagram with all the energy levels of all the lanthanides. Ytterbium with 13 F electrons has 1 excited state, the 2F5 halves excited state. Emission to the 2F7 halves ground state is around 1,000 nanometers, nicely in the infrared, separated from the quantum dot emission. So to prove that it's in there, you don't have overlap between your excitonic emission and your lanthanide emission, so that helps to identify incorporation. The reason that we chose cadmium selenide is that really, at that time, was the workhorse of all quantum dot research. It was the most widely studied system. So how did we do that? We tried the absorption overgrowth method, and that's work done by Rosa Martin Rodriguez and Robin Geitenbeek. So we first made our cadmium selenide quantum dots, added an ytterbium precursor, then added a selenium precursor, heated it up, and hoped that there would be some surface layer formed with ytterbium and selenium. And that kind of worked. If we excite somewhere in the broad visible range, then we see beautiful characteristic ytterbium emission around 1,000 nanometers. This is the sharp line emission from the 2F5 halves to 2F7 halves emission from ytterbium 3+. And very importantly, when you record the excitation spectrum of this emission, so that's the green line, the excitation spectrum of the infrared ytterbium emission, you see, yes, all the quantum dot features, it coincides with the absorption spectrum of the cadmium selenide quantum dots, the black line. So that shows that there's electronic coupling. When you're exciting a quantum dot, there's energy transfer to your ytterbium. And this is the mechanism that we envision. So you make your cadmium selenide quantum dots, you add your ytterbium acetate precursor, you absorb at the surface, you overgrow a layer, but probably ytterbium is still in a surface layer and does not diffuse in because lanthanides do not like 4-coordination. So those were the old generation 2-6 semiconductor quantum dots. But now we have a next generation of nanocrystals, the perovskites. So the new kids on the block, the perovskite nanocrystals. The perovskite structure is a very well-known and old structure. It's, here you can see the unit cell of the perovskite. You have a cubic close packing, an FCC packing of the N-ions, the oxygens, that are now the cubes, and one cation, the big cation, the strontium cation, here at the middle of all the phases. So that's a phase-centered cubic close packing, but not of only the anions. Usually you have an FCC packing of the anions and then the cations going to the octahedral and the tetrahedral holes. In the perovskite structure, you have an FCC packing of the big cations and the anions. And typically all those old perovskites were oxides, so then you have a 2+ cation, a 4+ cation, and oxygen 2-. Now the cesium lead halide perovskite nanocrystals, they have 1+ cation, 2+ cation, and the 1- anion. The first discovery of perovskite quantum dots was not by Maxim Kovalenko, who developed a revolutionary colloidal synthesis method, but already in the late 90s, Martin Nicol observed when he was trying to dope lead-2+ into cesium halide crystals, so big cesium halide crystals for scintillators, he doped them with lead-2+, and what he observed is that then you get segregation of small cesium lead chloride or cesium lead bromide nanocrystals. And in this article that was presented at the ICL in Prague, he said quantum size effects in the exotonic luminescence of cesium lead halide like quantum dots in cesium bromide, cesium chloride. Then of course the big breakthrough came in 2015 when Maxim Kovalenko published his paper in Nanoletters where he showed that he has a colloidal synthesis method of highly luminescent cesium lead halide nanocrystals. And there you see the beautiful different colors. The important thing to realize is that here the color tuning is not done by changing the size. I showed a similar picture for cadmium selenide. For cadmium selenide, you see, well, it went from blue to red, and that is because the size went from 2.5 to 6 nanometers. Here, the color tuning is done by the chemical composition. If you go from chloride, you have a blue-violet emission around 420 nanometers. For the bromide, the pure bromide, you have a green emission around 520. When you go to the pure iodide, you have a deep red emission. And by changing the chlorine-bromine ratio or the bromine-iodine ratio, you can again cover the whole visible range. But there's hardly any quantum confinement. Those nanocrystals are typically about 10 nanometers, and the Bohr radius of the exciton is about 3 to 5 nanometers in those different nanocrystals. So the color tuning is done by, not by quantum confinement, but by chemical composition. So unique nanocrystals, color tuning by chemical composition, weak confinement, again high quantum yield, easy and fast synthesis. That's of course the great advantage over the paper by Nicol. When you have them in the cesium chloride crystal, you cannot do much with them. But when you have a colloidal solution of those nanocrystals, then you can process them, apply them in luminescent devices. So it was a really revolutionary approach by Maxim Kovalenko. Fairly easy and fast synthesis process. The lifetime is much shorter, only 1 or 2 nanoseconds. 10 times shorter than in cadmium selenide or indium phosphide. And that also means that the absorption strength is also much stronger. And for some applications, like micro-LEDs, that stronger absorption is a very important advantage. So you have faster emission and shorter absorption compared to the 2.6 and this 3.5 nanocrystals. So that makes them very promising for application like many devices, and of course, you also have, again, new fundamental physics. Main problem is the stability. Halides are notorious for being moisture, air sensitive, especially under high excitation density, so the stability problem is still the big issue to be solved for application of perovskite nanocrystals. Then doping them. Again, manganese and ytterbium 3+. First, manganese. We tried diffusion doping, so we again make our perovskite nanocrystals, we add the manganese precursor, and then we have the halide precursor made, in this case from silicon chloride, that slowly decomposes. When there's a little bit of moisture present, you get some HCl, hydrochloric acid, and that helps to give the chlorine- precursor, and then you get incorporation of manganese 2+, first at the surface, and then it diffuses inside. And there you can see the result. Initially, you have the violet emission from your cesium lead chloride nanocrystals, and when you diffusion dope for quite some time, after about 10 hours, you get very bright orange-yellow manganese 2+ emission. And this work, the doping of manganese, was pioneered by your chairman, Chun Che. He did it when he was a postdoc in our group. He was pioneering and was the first one to incorporate manganese 2+ in the cesium lead chloride nanocrystals. Many other methods can also be used, hot injection method. So it works, and you get very bright and efficient manganese 2+ emission. There's quite some differences, and we don't understand even all the differences. One difference is that the transfer of the excitonic state in cesium lead chloride to the manganese is much less efficient than for cesium, or for cadmium selenide. For cadmium selenide, with 1 or 2% of manganese, you get complete quenching of your excitonic emission. For the manganese, these are concentrations inside the nanocrystals, so we lose a large excess of manganese, and then we can incorporate, well, 0.88, 25, or 50%, and then you see that even for 25 or 50%, there's still some excitonic emission left. It shifts to slightly higher energy because the energy level structure of your perovskite nanocrystal changes, but you see that you have beautiful manganese emission, but there's still excitonic emission for high concentrations. Also, peculiar temperature dependence. If you look at the efficiency of the energy transfer, initially you see that your manganese emission drops, and then high temperature increases again. We don't quite understand that yet. It can be that the spin selection rule plays a role, because at low temperatures you populate your dark state of your exciton, but it's different from cadmium selenide. The doping can also help to resolve a problem that appeared in 2018 about the excitonic fine structure of the perovskite nanocrystals. A spectacular paper from the Everest Norris group, where they observed something that's quite peculiar. If you look at the lifetime of your excitonic emission of cesium lead chloride or cesium lead bromide nanocrystals, and they looked at single nanocrystals, they observed that at room temperature, the lifetime is longer than the lifetime at low temperature, 5 Kelvin. And that is unusual. Typically for quantum dots, this is the situation you have. There is a lowest energy excited exciton state that we call the dark state. And the most simple way to understand it is that it's a spin-forbidden transition. In the ground state, the valence band is filled. When you bring one electron to the conduction band, you have an unpaired electron in the valence band and an unpaired electron 3 minutes in the conduction band, and the lowest energy state, Hund's rule tells us, is the triplet state. And the transition back to the ground state involves a spin flip. Spin forbidden transition. Just above there is a bright state, where you have a single state, where the electrons are paired, and that's an allowed transition. So typically, this is what you observe for your quantum dots at low temperature. You have a long lifetime emission from the dark state, spin forbidden transition, and then at high temperatures you start to suddenly occupy the bright state, and you see a shortening of the lifetime. Faster decay. So that's very different from what we saw here. Long lifetime at room temperature and very short lifetime. And they explained it by, and I actually refereed this paper, and they explained it by the Rashba effect, and that's too difficult for me. I didn't understand it, and I said, can you explain it for simple people like me? And they tried, but they didn't quite succeed. But they say that this dark state and bright state is inversion. So in those perovskite nanocrystals, there's a lower energy bright state and a high energy dark state because of the Rashba effect. So we investigated the also luminescence lifetimes of manganese-doped nanocrystals. And what we observed, and this is done by Yara Vlim and Kunyuang Su, what we observed is that we see the normal behavior when you increase the temperature, and this is with 20% doping, now you go from a higher temperature to lower temperature, the lifetime gets longer and longer, and then at very low temperature, below 50 Kelvin, we also start to see a very fast initial decay component. And then when we looked very carefully, we also saw that in the undoped quantum dots. So again, very fast nanosecond lifetime, but a very weak, long-lived component that was about 10 times strong when you started to dope with manganese. So that's the reason they missed it for the single quantum dots. In the single quantum dots, you don't observe this very weak, slow decaying component. You only see this fast component. So our explanation is that there is no inversion of the dark state and the bright state, but the relaxation from the bright state to the dark state is very slow. Much slower than this fast sub-nanosecond decay, radiative decay from your bright state. So that's the reason that you observe very fast decay, but then there is still relaxation to the dark state, and that relaxation becomes faster when you dope with manganese because of magnetic coupling. You partly inverted the spin selection rule, because this is a spin forbidden transition, that relaxation becomes faster when you dope with manganese, and then you observe this slow decay more easily. And this was later also proven by the group of Launis, where they applied a magnetic field. They observed the same effect. When you apply a magnetic field, then you start to see this forbidden transition also in emission. So no rush by effect, no switching of the dark bright state, just slow relaxation from the bright state. So then I have not enough time to talk about the lanthanide doping. There's very nice papers that dope lanthanides into the perovskite quantum dots, but we could not reproduce that. And also Daniel Gamelan writes in our hands, the synthesis of ytterbium nanocrystals following the method described here. We met with some difficulties. We've developed other systems. So we can dope ytterbium 3+ in the perovskite quantum dots, but not europium and terbium, not the other lanthanides. And that's still an active field of research. So ytterbium works, but not the other lanthanides. And yet the perovskites are very promising and important for application. I mentioned the high absorption strength is very favorable for micro LEDs. That was also highlighted quite often in this Phosphor Quantum Dot Industry Forum. That's the successor of the Phosphor Global Summit. That's a very expensive conference that you never should go to unless you're free because you're an invited speaker. Otherwise you pay $1,700 for 2 days. Not worth it. Which I shouldn't say as a member of the organizing committee, but it isn't. But yeah, there you see also nice presentations from startup companies like Avantama, who say that the doped perovskite quantum dots and perovskite quantum dots are expected to become the new industry standard for color and brightness. So they are promising, high absorption strengths, high efficiency, but the stability is the big issue. Yeah, and then the doped perovskites are the next generation, and we've done some work there too, doping with lanthanides. But let's go to the conclusions. So this Phosphor Safari is not about spotting the big five, but about spotting the small nano 4. And I've talked about 4 nanocrystals doped with transition metal ions and lanthanide ions, 2,6 quantum dots with transition metal lanthanides, perovskites with transition metal lanthanides. These are the conclusions that I've shown. So manganese doping is not mission impossible. It goes into cadmium selenide, and you get beautiful temperature-dependent behavior due to back transfer from the manganese to the exciton. Ytterbium doping inside doesn't work, but at the surface does work. Doping manganese to plus in cesium lead chloride has been instrumental showing that there is no dark bright state inversion by the Rashba effect. And finally, perovskite and double perovskite dope is lanthanides. Ytterbium works, the other lanthanides do not seem to work, and well, more careful research is needed. Then I'd like to thank Science Foundation, Utrecht University, and the Dutch people for funding with euros. I'd like to acknowledge the Taiwanese Association for funding Chun-Che Lin, and also me for being a visiting scholar now, and also the Chinese Council for funding Kun Yuan. And yeah, I also like to very much thank Rushi Liu and Chun-Che Lin for organizing a very exciting Phosphor Safari. Rushi Liu says we always make a normal picture, and an action picture. So this was the action picture taken at a beautiful place that I think we will visit during the excursion. Yeah, so thank you for organizing the conference, and thank you all for your attention. Thank you.
Professor Very gave us a very wonderful and comprehensive talk. Maybe we have time for 1 or 2 questions due to time constraint.
Yeah, a very stimulating talk. Okay, what my question is this way. Okay, I mean, say for your cadmium selenide energy transfer to lanthanide group. Okay, could you sort of describe what types of energy transfer mechanism?
Yeah, very good question. And so there's 2 ways of transferring the energy. One way is that you have your excitonic energy, and you transfer it via dipole-dipole interaction or exchange interaction to a high excited state of your lanthanide, and the other goes down. The other mechanism is that you have your electron hole pair, and your lanthanide, for example, the terbium 3+, first captures an electron, becoming a terbium 2+, then captures a hole, leaving a terbium 3+ again in the excited state. So those are 2 mechanisms. They're not easy to distinguish. We have some evidence that in our double perovskite, that there it is this consecutive trapping process. Because there we see that there's no energy transfer from the trapped exciton state. So the normal undoped double perovskite shows an infrared emission. That state does not transfer terbium, but the free exciton does. And so we think there's competition between trapping. But that's not always. But those are the 2 mechanisms that can transfer the energy.
Thing to do, for example, say, if using lanthanide sulfide instead of using lanthanide selenide, would it be possible that you build up the core shell as well as energy transfer, then you will enhance your emission? I'm just curious.
That's an interesting suggestion. We didn't try that. You mean then if you add a sulfur precursor instead of selenium precursor after the absorption?
Yes.
Yeah. We've not tried it.
You have type 1 type of the configuration. So in the case, you build up core shell as well as energy transfer.
Yeah.
Okay.
Yeah, and then you would confine your exciton,
Yes,
but still
yes.
have the transfers. Yeah.
Yes.
Yeah, interesting suggestion. We've not tried that.
Okay, thank you.
Yes.
Thank you very much for your beautiful talk. I have a question about the perovskite quantum dots. So when you mentioned the conversion from bright states to dark states, they have a different momentum. It requires momentum conservation. You also mentioned the Nature Material paper. And so I wonder if you see strong effects when you do doping for this conversion, because they have a different momentum. So when you do doping, do you see very strong effects to change the conversion from bright state to dark states?
Yeah, so we have not seen that. When we,
you couldn't see?
No, so when we dope with manganese from low concentration to high concentration, we always see the slow emission. So the dark state is always the lowest. Okay. So there's no inversion, also not induced by the dopant, no bright dark state inversion. What we do see is that the relaxation from the bright state to the dark state is faster. And we ascribe it to the magnetic moment because you see the same thing when you put it in a 7 Tesla magnetic field. So undoped quantum dots in a 7 Tesla magnetic field also have this faster relaxation from the bright state to the dark state. And we think that manganese, by having an internal magnetic field, does the same. But yeah, it could be also other effects because you're right, the dopant will change the electronic configuration inside your quantum dot.
So did you do magnetic field?
Yeah, so we didn't do that. Those were the experiments by Launis, the group of Launis. They applied the magnetic field. So they looked at a slightly different lead halide crystal. Then there was a semi-organic ammonium molecule that was the big cation, but without the magnetic field. This is the emission spectrum they observed for a single quantum dot. And this is all bright state emission. The bright state splits in a triplet, so this is bright state emission. Then when they, so magnetic field 0 Tesla. When they apply a 7 Tesla magnetic field and at lower energy, they start to see the dark state emission.
I wonder if you did the measurement, doping measurement in magnetic field.
If we measure the magnetic field?
Yes, sir.
I don't know how we would do that. I mean, we know we have magnetic ions. The manganese is highly magnetic, spin of 5 halves. but I don't know how to measure the magnetic field inside the nanorods due to the manganese.
Okay.
And,
all right.
and that probably would also be concentration dependent. There may be ferromagnetic or ordering or antiferromagnetic ordering. So we cannot do that.
Okay, thank you.
This is very exciting in the field. I guess a lot of our many questions due to time constraint. Maybe we can consult, discuss with Professor Meyrink and after the break. Okay, please join me to thank Professor Meyrink again to give us a wonderful talk. Thank you. The next speaker is Professor Adachi and from the Kyushu universities. I think Professor Adachi probably I do not have to give too much introductions because he is the pioneer of TA and TADF. I also have already introduced in my classrooms. So please join me and to welcome Professor Adachi, please.
Yeah. Thank you, Chairman, for your kind introduction. I'm Chihaya Adachi from Kyushu University, Japan, and yeah, I should say great. My thanks to the Professor Kuros, for your great hospitalities. It's really a great chance to visit Taipei Tech and NTU and also this conference. Actually, I made two lectures in Taipei Tech and NTU, so I slightly changed the contents of my talk, and it's a really first time to attend this conference. I have not no information about who is the audience, and it's a mixture of the organic and inorganic, and also not only academia but also the company's persons here. So I'm going to talk about more industry-oriented contents. I mean, aimed for real devices. So I have two topics. First topic is the hyperfluorescence OLED. It's provide almost linear ideal light emission properties. I mean high efficiency and high color purities. It's ready for the commercial use. And the second topic is the organic lasers. It's a really cutting edge device. And okay, so for the next generation display application, AR, VR displays are very promising technologies. Organic laser is one of the potential application for the AR, VR displays. I'm going to talk about our recent result of the organic lasers. Okay, OLED. So when I was a student, the OLED was really a very primitive behavior. When I make a device, within 2 or 3 minutes, device dies. So it seems very hard time to get the longer device lifetime in OLED. But you know, after 30 years later, so OLED has been widely used, not only a cell phone, large TVs, and future wearable and also bendable displays we can expect. Very recently, Apple Computer released a new iPad Pro. If you see this image, it's amazingly beautiful picture because it's the device is made of the actually tandem architectures. So tandem architecture is the OLED is a two stacked structure. Just provide a very bright luminance. So fortunately, the tandem provide the lower driving voltage than that of the two independent OLED because we can tune the thickness of the each layers, so we can actually enhance the power conversion efficiency by tandem architectures. It's a quite good news. Maybe it's competitive with the micro LED. You know the micro LED, if we make a smaller device size, EQE goes down. In case of the few micrometer size, EQ is just 5%, even though the OLED realized that 20 or 30%. So OLED seems quite promising. Also, Apple Computer also released the Apple Vision Pro. It's also made of the OLED. So the panel actually comes from a Sony micro OLED module. It's a 23 million pixels. Each pixel is just a 7.5 micrometer. It's a very fine structures. It's give brilliant pictures. Okay, so OLED seems quite promising technologies, and the key issue is the emitting materials, light emitters in organics. So this summarizes the overview of the molecular emitters used in OLED. So we have a wide variety of the organic emitters. You know, the fluorescence and phosphorescence. I would say in a daily life, we can find a wide variety of the organic luminescent materials, but 99%, maybe 99.99% is the fluorescence. So OLED research started from fluorescence since 1950s, and then maybe you know the very famous Chintan's papers using aluminum quinoline materials. But as far as we use the fluorescence materials, internal efficiency is limited to 25%. We can get 100%. Okay, instead, the phosphorus, such as platinum complex or iridium complex, it's a metal complexes. If we use these complexes, ideally we can get 100% internal efficiencies. But we have to use the precious metals. Iridium and platinum is a little bit expensive atoms. Okay, we have a third choice. This is the TADF. TADF stands for thermally activated diode fluorescence that can realize 100% internal efficiencies. So this is the chemical structure of the TADF molecules. You will see it's a very simple molecules, just made of donor and acceptors. If you are a chemist, oh, it's a quite simple chemical structures. We have a wide variety of molecular choice by combining simply donor and acceptors. Okay, I should also talk about the advanced TADF technology that is hyperfluorescence. I'm going to talk about later. Okay, so what is the fourth generation? Maybe organic radicals, quantum dots, and perovskite. All these materials also has a possibility to harvest 100% electron falls into photons. But I'm not sure. It's really depends on the stability of these materials. Okay, TADF. Actually, we started TADF study around 2003 or 2004 when I have been working in Hokkaido, and then it was if you come to Hokkaido in the winter time, it's completely covered with snow. So I have no chance to go other places. I stay at my laboratory for a long time, and then we focus on these technologies. We spent more than 7 or 8 years, and finally, 2012, we could get the ideal TADF materials. Okay, we have a singlet and a two-pet, and usually the two-pet is lower than the singlet. So our idea is let's align a singlet and a two-pet, making a smaller energy gap between singlet and two-pet. So once we provide a smaller energy gap, such as less than 200 millielectron volt, two-pet start to upconvert, and we can get the emission as the delayed fluorescence. So this is a TADF mechanisms. The material design is well formulated. So to get the small delta ST, we should separate actually HOMO and LUMOS. If we have a small overlap integral, we can make a smaller delta ST. So then chemical structure is quite simple. Okay, let's make a donor acceptor because the HOMO tend to localize at the electron donating unit, LUMO tend to electron accepting unit. So this kind of material realize small delta st and high efficiency. Okay, but TLEF has actually a significant disadvantage. That is the emission spectrums. So this is a kind of CT, charge transfer emissions. So charge transfer emission always provide very broad spectral width because of the, donor acceptor combination. So we have an electron transfer process that provide a wider spectral width, such as 100 nanometers. So if display engineer see this spectrum, Mr. Adachi, it's useless for the display application because of the broad spectral width. Okay, to overcome this problem, we reached to the idea. We use the FLET, first energy transfer, from TADF into terminal emitter. Okay, we first generate whole and electron, extons, and TADF. So we have a 25% singlet exton and 75% triplet extons, triplet upconvert. So we have actually 100% singlet generation. And if we doped a small amount of the terminal emitter, we can efficiently transfer the TADF singlet into terminal emitters. We finally control the concentration of TADF and terminal emitters. Usually, terminal emitters concentration is 0.5 or 1 weight percent, very, very diluted conditions. Recently, Itindi, so she's here today. Also, Dr. Chan, we also collaborate with Professor Hatakeyama in Kyoto University, and we combine phosphate IPN and DABNA materials. And you know that DABNA showed a very narrow spectral width, such as 20 or 30 nanometers. Okay, our research group tried to optimize the devices, so it works quite very hard to optimize. I'm not, so it's a very small character, but many parameters we optimize, and we could get ideal OLEDs. Okay, EQ is, maximum EQ is 25%, FWHM is a 30 nanometer, and lifetime LT95 is almost 600 hours. It's a very stable device we could realize. Okay, we have we set up a startup, QLux. QLux means Kyushu and luminescence, and set up in 2015. They start to commercialize these technologies. Now we have more than 80 employees. Okay, so QLux try to, it doesn't work. Okay, try to commercialize these TADF technologies. So the key issue is the CIE, color coordinations. So okay, this is the real world colors, and we have a blue, red, and green. So depending on the spectral width of the 3 emission colors, we can reproduce the color within these triangles. So particularly to expanding the green region is quite important, and actually hyperfluorescence realized almost satisfy the requirement of the next generation TV requirement, BT2020. So here, you will see two bars. So compared to these colors, you will see more impressive palettes because of the wider, almost 40. This is a conventional OLED, and 40% wider triangle we can realize. This provide beautiful pictures. Okay, let's look at more details. Here is a two hyperfluorescence device, and okay, device one, HF1 showed a more wider triangles. It's very, very important to extend these triangles. Of course, spectral width is quite small, narrow, surprisingly 18 nanometer they realized. And this is the current efficiency against the current, and a very small roll-off, and the maximum current efficiency is more than 200. Okay, it's quite impressive values. Okay, so now, so QLux realized that blue, red, and green, very nice green emissions. And also here, this is the lifetime, LT95, starting from 1,000 candela, realized more than 60,000 hours. Very stable hyperfluorescence was already realized. I think it's ready for the commercial use. Okay, let's move to the second topic. That is the organic semiconductor lasers. So we want to realize the current injection narrow emission spectrum by controlling light emitting material and also the device architectures. Thank you. Something. Okay, so the organic lasers, actually it's a long, long history again. So the very first organic laser was reported 1966, more than 50 years ago. Very interestingly, very first resin was reported by phthalocyanins. Oh, I suppose the phthalocyanin never showed the luminescence, but if we disperse diluted condition, phthalocyanin showed not only a luminescence, but resins. So all the time, all device was examined within diluted solutions. And after 1990s, okay, researchers tried to make a solid state. Actually, it's a waveguide architectures. Okay, so there are some important results reported by Steve Forrest and also the Cambridge group. And to 1997, we also reported okay, very low resin threshold using BSBCZs. Recently, not only optical excitation, so current injection trial has been reported. One of the important report is reported by FET-driven the current injection resin from FET structures reported by Professor Tanigaki in Tohoku universities. Our group also reported indication of our current injection resin 2019, and most recently, St. Andrews Group, UK, reported indirect pumping of organic waveguide by OLED. It clearly showed the appearance of the resins. Okay. This one. Okay, and okay, let's start from advantage of the organic lasers. One of the advantage is the wavelengths. So here you will see okay gap the gap for the inorganic lasers they cannot realize the wavelengths around here. But organics, you know that by changing the chemical structures, we can continuously obtain any wavelengths. This is a big advantage of the organic materials. Okay, please go to the next. Okay, so plenty of OLED material has been developed, and simultaneously laser material has been also, actually some of the OLED emitting materials show the laser behaviors. This is a wavelength dependence of the resin and AC threshold. You will see around the 500 nanometer, we can see lowest threshold. One of the reasons is the longer the wavelengths, we will have a larger non-radiativity case that, in other words, PLQY goes down. And shortest wavelengths, somehow the threshold goes down. So at this moment, around 500 nanometer provide the lowest threshold. BSVCZ, this is, we reported the very low, showing the very low threshold. Okay, next page, please. Okay, let's look at the resin behavior under the waveguide structures. So, firstly, I want to show the quantum efficiency and fluorescence lifetime against the temperature. You will see both values, almost no temperature dependence. Just means non-radiativity is completely suppressed, even at room temperatures. And under the DFB structures, it shows the clear onset of the resin with the threshold of 0.3 microjoule per square centimeter. And over this threshold, it shows narrowed, very narrow, less than 1 nanometer narrow spectral width we could obtain. Okay, why BSBCZ showed such a low threshold? Okay, one of the advantage is no overlap between excited states absorptions. So here, this is the fluorescence spectrums. Resin, lowest resin threshold always happen at 0-1 transitions because the 0-0 transition overlap with the ground state absorptions. And we also have triplet absorption and single absorptions. Fortunately, we have almost no overlap integral at the 0-1 transitions. So emission cross-section is extremely higher than the TT cross-sections. Actually, it's quite delicate. We also try this kind of spiral structures. In this case, we observe the large appearance of the TT absorption. Interestingly, if we put the oxygen, TT absorption completely disappears, showing the resins. Oxygen, you know the oxygen is a harmful material, but sometimes good to quench the triplet, and we have resins. Okay, so lasers, we need a DFB, optical resonators. So we tried a wide variety of the resonator structures, and actually mixed ordered DFB showed a very practical device architectures. We have a first order grating. The pitch is 140 nanometer, and second order grating here, and third order gratings. Actually, first order grating, we can feed back light back and forth these directions. Second order DFB, we can also back and forth, but also perpendicular direction, we can extract light to these directions. So thin film device architecture, we can extract light like surface emitting lasers. So after making DFB structures, we deposit active layer, organic layers. Okay, let's look at the resin behaviors. So black line is before the threshold, and after onset of the threshold, you will see appearance of the resin, and the line width is almost 0.3 nanometers. We compare the AC and only second order DFB and mixed order DFB. Mixed order DFB provide the lowest threshold. We also compare the doped and neat film, and doped mixed order DFB show the lowest threshold of the 0.09 microjoule per square centimeters. Okay, so to confirm the laser behaviors, we look at the near field and far field patterns. This is a little bit complicated architecture. So as I said, second order and first order and second order, first order repeated structures, and actually lasing occurs at the second orders. So each laser beam start to interference, and it shows the characteristics, spatial laser distributions. So this is an angular dependence of the laser beam, and before the threshold, we see a kind of a broad spectral distribution. This is near the threshold. You will see a very sharp peak. Over threshold, we can see a clear appearance of the lasings. So this is the experimental results, and this is the simulations. You will see, this is exactly, we can have a good coincidence. Okay, let's go. So our purpose is electrical pumping. So, let's assume the lasing happened at 600 nanometer. We should escape the over ground state absorption and singlet and triplet absorption, but under electrical excitation. We should also pay attention for the polaron exciton annihilation. Polaron is a logical cation or logical anions. We check the absorption of a BSBCZ cation doped with molybdenum oxide and BSBCZ doped with cesium. We forced to generate cation anion into film and look at the absorptions. So fortunately, again, so the at around 460 nanometer, this logical absorption is not is actually far from lasing wavelengths. It's good news. We have a chance to get the lasing and the electrical pumping. This is our lasing architecture. It's a very complicated structure. So we have a glass substrates and ITO and SiO2. SiO2, we make a first order and second order and first order. On top of the SiO2 gratin, we deposit organic semiconductor resin active layers. And on top of the substrate, we put molybdenum oxide and silver aluminum electrode. This is a cartoon, and we forced to generate exciton at the BSBCZ and try to get the lasings. This is a 10 image of cross-sectional our device. So second order and first order. It seems ideal structure we could get. And then to this device, we apply the electrical 400 nanosecond or 300 nanosecond pulse electrical excitation, and we see appearance of very narrow spectral width over the 700 ampere per square centimeter. It's an extremely high current we injected into organic materials. We tried to reproduce our results, but unfortunately the device dies within 5 or 10 seconds. It's an extremely difficult experiment. So we try to see, as I said, in optical excitation, we see interference effect, but at this moment, it's hard to confirm the optical interference. We believe this is the indication of organic lasers, and then um, we are now still working very hard to improve these device architectures. Okay, so based on our results, so we get this result 2019, and we also set up a startup. It's a Qualatech. It's a very cute name. Quara stands for K is a Kyushu, O is a organic, LA is a laser. So Kyushu organic lasers. So the company tried to realize the highly directed beam. So you know the AR not only flat panel displays, so future smart glasses, AR, VR display, we need a directed beam. So to realize directed beam, so companies try to reduce the threshold, and actually, there is some previous reports. This is the St. Andrews group, OLED and micro kind of photonic crystals combined. Light emission is propagated to the this nano-imprint formed microstructures and extracted to light this direction. They see a kind of a beam. Okay, a second one is the very similar our structure, the DFB structures. They could see a beam like this. So Qualatech Technologies, they already realized the 2 nanometer line width, and the angular distribution is within a 3 degree. It's a highly directed beam, but I would say the current is not so high. We don't need a high current injection. This is the actually IB characteristics. So you will see current is just not kiloampere, even 100 milliampere per square centimeter, less than 1 ampere square centimeter. We already obtained narrowed spectral width. It's the spectral width is less than 2 nanometer, and so angular emission distribution is within a 3 degree. Okay, I would say this is. It's hard to say this is raising or not, but by construction, proper architectures, even at the OLED, similar OLED current injection, we already obtained very highly directed beam. Okay, I'd like to summarize my talk. Okay, so the first topic, the hyperfluorescence OLED. So extending CI coordination is quite important, and QLAX tried to extend particularly green regions. It's already realized BT to zero. It's a really ideal try CI coordination they realized. I think still we have a space, but anyhow, it's already ready for the commercial use. So here you will see red and green and blue, all these RGB pixels. The hyperfluorescence show the improved color purities. And organic lasers. Actually, so we really want to realize the real resin, such as 1 kiloampere per square centimeter with a short pulse excitation, but it's quite difficult because of the degradation, many degradation. We have to overcome many issues. But Qualatech already obtained a narrowed spectral width and the angular distribution within a 3 degree, even at 100 milliampere per square centimeters. I think this device is quite useful for the AR, VR displays. Okay, thank you very much for your attention, and I also want to thanks to our research members, and also I'd like to thanks to the JSPS and the JST for their financial support. Okay, thank you very much for your attention.
Okay, thank you. And now we have time for a few questions. Yes.
Professor Dachi, very interesting data. The very narrow spectrum, 100 milliamp per centimeter square. The spectral width is 2 nanometer, very interesting. So you mentioned you're not sure whether it is a lesion. So I wonder, there's one information we could see, we could look at, for example, if you see any signature related to polariton from your narrow spectrum, then we could claim it's a lesion. So I wonder if you see any signature related to polariton from your narrow spectrum.
So your question is the reason of the narrow spectral width without raising or
whether you see signature related to polariton. Polariton. The narrow spectrum.
Yes.
Do you see that carries any signature for polariton? Polariton.
So maybe
polariton. Polariton.
Yes, polariton.
Polariton quenching.
No, not a polar one, polariton. If you see a signature related to polariton, it's very highly possible your narrow spectrum is a lesion. Because you mentioned that you're not sure whether it is a lesion. We can discuss afterwards.
Maybe after the break, yes.
Yeah.
I can
during the break.
Yeah, thank you. So we discuss afterwards.
Okay. Yeah, I'm sorry for
Okay, thank you. Any other questions?
Yeah, somehow.
Yes, Prof. Joe, yeah.
Just very general question is, could you comment on the stability of this type of lasing out OLED? The stability, the futures, the future perspective should be based on the stability, I believe. And right now, this is a fast booming area, okay, including, a few papers published in Science, I know that. But what would be the stability of this type of lasing OLED? Because, when you show the company of Exciton, or you call Exciton, the company, when I was a PhD student, okay, when I operate the dye laser, I have to change it every 3 hours, okay, for the tank. So what I mean that in this type of a case, you pump by 12 volt. So what would be, especially you use a CW type, okay, so what would be the stability in the future you can expect, okay, for the practical application?
Yes, actually, okay. If we inject 1 kiloampere per centimeter, but in fact it's a pulse operation. So now we use the 400 to 200 nanosecond pulse. If we can use the 1 nanosecond, very short pulse, maybe okay. So the total current is not so high compared to the CW excitations. So and also one of the problem of the OLED is the low stability for the thermal heating or something. So in case of the CW, even in conventional OLED, it's quite interesting. So the internal thermal energy, internal temperature is almost 130 degrees centigrade locally. So then, we need a kind of a high TZ materials. But the point is that even 1 kiloampere per centimeter, if you use a very short pulse, 1 nanosecond, or I'm not sure if electrically, if we can apply 500 picosecond, I think we have a possibility of longer lifetime. But but as far as we use a BSBCZ, it's completely useless because it's contained steel band. The steel band is very unstable for the electrical excitation, even optical, maybe a cis-trans isomerization, many things happen. We really want to escape the use of the steel band. But at this moment, steel band is the best. Steel band shows the lowest threshold. Yes, but maybe a chemist can provide me another molecules, I expect.
Any more questions? Oh, yes, please.
Adachi-sensei, thank you for your impressive presentation. And the hyperfluorescence OLED fully used the TADF and the fluorescence emitters advantages. And you know, recently the multiple resonance typed TADF is a very hot research topic. And the properties of the MR and OLED is have a lot of advantages like the high EQE, low efficiency roll-off, and the narrow emission bands. So for the MR TADF OLEDs and the hyperfluorescence OLEDs, so which is the mainstream solution for the future narrow emission band OLED?
Okay,
Display,
yeah, it's a good question. And actually, okay, so today, actually, Davna material developed by Professor Hatakeyama, it's MR material, you know. And we use MR material as a terminal emitter. We don't use MR material for the TADF because still the MR material risk rate is 10 to the recently, Hatakeyama sensei realized 10 to the fifth or 10 to less than 10 to the sixth. So if we can realize 10 to the sixth, more than 10 to the sixth, we have a possibility. We can use the MR for the TADF materials. But at this moment, it seems very hard because the MR material is the basically kind of very flat structures. DA structure is kind of a twisted structures. It provides more easy to promote risk rate. But MR material is really a fixed structure. In this case, it's a little bit hard to enhance the risk rate. But I'm not sure. So if we can use the kind of helical structures or something new idea, maybe we have a chance to get the high risk rate in MR materials. It really depends on the future material design.
Okay, thank you so much.
Okay, thank you. Due to time constraint, maybe let's move on. Please join me to thank Professor Adachi give us a wonderful talk again. Okay, thank you. The next speaker is Professor Liu Rishi, and from the distinguished professors from national Taiwan universities. And for me, first time to attend Professor Liu's talk is he gave a talk in our department at the National University of Singapore. For me, it's very exciting to learn from Professor Liu again. Professor Liu's research is covered from all the converting of light into electricity, and also into the thermal and all the different. In today's talk, and we all know from photophysics, it's very difficult to prepare material near IR range because of the lower quantum yield. So this area is very challenging. So it's a very good opportunity, very exciting to listen from Professor Liu again. Thank you.
Okay, so thank you for Professor Xu to chair my lecture. So today I'm going to give you a title based on the Shining a New Light. That's innovative approaches to near IR phosphor design for cutting-edge LED technologies. So then, this is the outline of my talk. I would like to briefly separate it into 5 parts. So the first part lets you know how important of the infrared phosphor. Then secondly, I let you know the basic idea, principle of chrome-related IR phosphor. Then I move to the new discovery for the chrome-chrome pair and their energy transfer. Then we further discuss on not only from the pair, but also from the cluster and their energy transfer. Then I give you short conclusions. So firstly, the introduction. So this is a definition for the spectrons. So by using the ISO 20473, so they separately for the near IR from the wavelengths from 780 to 3,000 nanometer, and the middle IR from 3,000 to 5,000 nanometer, and the higher than 5,000 we call far IR. But for the LED industry, they usually use CIE for the definition. So for the IRA from 700 to 1,400 nanometer, IRB from the 1,400 to 3,000 nanometer, and about 3,000 nanometer usually called IRC regime. But for the biological definition, they have another kind of separation from 700 to 900, they call it a near IR1 region. From the 1000 to 1700, they call near IR2 region. That's a called shortwave infrared region as well. So above 1700, they call near IR3. So even they have a different kind of definition, but they have a similarity based on that. But depending on you are belong to which of the society, you give a different kind of name. But the gap between 900 to 1000 because of water absorption for this kind of things. So you know, in Taiwan, we have very strong LED industry. But so even now, they have a conventional LED. They separate as IRA and IRB. For the IRA, it's very usually to observe with emission wavelength around 810 nanometer. This one is usually for the iris recognition. And for the 850, so that's usually for face recognition and night vision. For 940, so usually for remote control and the blood oxygen detection. But most of them have a very narrow for the full width maximum. So usually less than 15 nanometers. And in the year of 2016, I attend the conference, especially they discovered in 2016. They announced in 2017 in the Phosphor Global Summit by the Osram company. They demonstrate there is a new type of phosphor excited by blue LED. Then they excite the phosphor, they can emit a broadband. If it is true, then we can shrinkage of the big volume of infrared spectrometer into the small chip of LED. But by that time, you can see there is a log scale for the emission, this broadband infrared phosphor. So this is, I think, is a near infrared phosphor and unlocking the potential for next generation LEDs. So after that, they demonstrated their products in the type of SFH 4735. So with operating current at around 350 nanometer, and we can emit 16 milliwatt. Further on, they developed another type, 4776. So it's a bigger size as compared with the previous one at the same operating current. So they can increase their power up to 24 milliwatt. So then after this 2017, all over the world, they try to guess what kind of formula would be for the Osram phosphors. So in the year of 2018, 1 year later after discovery by Osram, so we discovered based on the lanthanum gallium germanium oxide phosphor, so doped with chrome 3+. Then we found you can see the color is green color. This is the same as Osram they demonstrated. So during the conference of Phosphor Global Summit, I inquired Professor Andrew Merink. He told me it must be chrome, so it is correct, but difficult to guess what kind of host. Then my master degree student, he found this formula and said to me, oh, professor, this is a real broadband phosphor. It's very similar like Osram 1. Then we try to find a pattern with Everlight company. Then Everlight company say to me, oh, this one already demonstrated in the pattern of Osram. So even we got the formula, but why we cannot find it by ourselves? Because their pattern written in German, okay? So then after this, I think we just announced the phosphor reported in the pattern of Osram that's based on this. Then over the world, they come immediately into this field. So not too bad as a solid-state chemist. So you see, previously we only can use LED emit infrared phosphor. So after this, we can discover more than 15 new formula based on this. Then I will give you briefly what we have found in my talk. Then I let you know principle of chrome 3+ related infrared phosphor. So taking from the Tanabe-Sugano diagram, so they depend on the dq over b versus their field. So you can see at the lower crystal field, So you can see the excitation. And the emission as a broad band because they are spin allowed the transition, and the decay time resided in the microsecond regime. And another in the high field, so excitation exactly the same as low field. Then emission can reside into nanoband. That's because of a spin forbidden transition. So the decay time is a millisecond because it's a spin not allowed. So you can see the different decay time between these two type of emission. And there's also can reside the compound in between. So with middle of the crystal field, then you can see the nanoband and the broad band. Nanoband is so-called as R9. Okay, then if you understand this, if we can control the distortion of crystal field for young Taylor distortion, so you can see the further split of the emission. Then we move on to the luminescence of chrome-chrome pair and their energy transfer. This is the first topic I would like to give it to you. So the compound based on the strontium, alumina, gallium, oxygen 19. So we call is a 1,12,19 activated by using chrome 3+. So with this compound, if we substitute gallium into aluminum site, they have different aluminum site with 5 different positions. So with octahedral, so we call it a monomer because all the octahedral are separated. Then you can see this is a 5 coordinated, is a bipyramidal arrangement. And there's another tetrahedral arrangement. And another we call this one is a dimer because 2 stick together with an octahedral arrangement. Another side is we call trimer, 3 stick together with an octahedral arrangement. Then if you put a bigger gallium into smaller aluminum side, then which side would be the gallium can substitute into, and which side would be substitute first? That might be an interesting question to answer. So then our problem is previously most of infrared phosphor, they are inflexible emission wavelengths. So we try to use this solid solution to put gallium in aluminum, try to tune the emission wavelengths. And the other is a lacking of structure investigation. So here we use a joint refinement with neutron and X-ray. And the third one is unexploded luminescence mechanism, especially for the chrome ion pair. And here we will combine with a pressure-dependent photoluminescence and short-range structure investigation and also electron spin resonance to prove this kind of chrome-chrome pair mechanism. So to synthesize this compound is very simple. You just mix with strontium carbonate and some of the oxide compound. Only one step sintering. So it's a 125 degrees C for 8 hours in air. Then you can get a completely single phase for all the series compound from x equals 0 to x equals 12. But you can see the shift of the XRD peak to the lower 2 theta angle because gallium is smaller, gallium is larger than alumina. So by the combination of the synchrotron XRD and the neutron powder diffraction can allow us to probe which side substitution might be easier. So this first show you with a continued substitution of gallium in aluminum side, the latest parameter increase. And secondly, we show you gallium will substitute in which side of alumina first. So with the refinement of occupancy of different site, then we are allowed to get, so the first one is gallium substitute into the alumina tetrahedral site, then the 5 coordinate one by pyramidal, then the dimer octahedral, then the trimer octahedral, then the monomer one. So with this kind of refinement, you can easily get the data. How can we explain this? So we use a bond valence sum to demonstrate this. So if without gallium in alumina, so we can see the discrepancy of the alumina far away from 3+. So it's from the oxygen 4, oxygen 5, oxygen 6, oxygen 6, and the other octahedral. So with gallium substitute in the alumina, you will release the strength. So then the valency will approach to 3 plus. So the reason why this kind of order, because of charge valency of the gallium can compensate into the alumina side. So then further study by the photoluminescence, so we are allowed to see with increasing the gallium, so you can see the chrome 1 due to the transition not allowed nanoband. And for the second one, you can realize probably due to the not allowed transition from 4T2G to 4A2G. So if it is the case, then you will see they should have, both of them should have a red shift. However, the chrome 2 side, so it's corresponding to the blue shift. So not as our expectation. And if it is allowed transition, you will see the nanosecond decay time. But both of these are all recited in the microsecond emission. So by using the high pressure, you are allowed to see the pressure effect. They all negative value as increasing the pressure. It demonstrates they all microsecond and not allowed transition. Then it proves this is not the 4T2G to 4A2G. So we attributed this broader transition that's due to chrome-chrome pair, we so-called the N-band. But usually N-band is a nanoband, but our N-band is a broader band because of from the chrome-chrome pairs. So it is a new mechanism. How can we prove this? By using the ESR, so you can see clearly they have a chrome isolated ESR peak. Then the second one is from the chrome-chrome pair. So with without gallium, so you can see very strong. But with the gallium substitution, you can just enlarge the chrome-chrome pair distance. So you can see the signal decrease with continuous substitution of the gallium. So not only from this, you can also to prove it much more clearly from the other evidence. So then this one is a photoluminescence as a function of temperature. So you can see this newly discovered phosphor, especially for gallium-6. So the thermal stability is quite good. So the highest emission intensity appear at x equals 6. So for the further packaging, so by using the LED packaging, we are allowed to see the driving current versus radiation flux. So our newly discovered is far above the value as founded by Osram company. So now we can get at 350 milliamp, we can push to the conventional 24 milliwatt as demonstrated by Osram. Now we can push to about 96.6 milliwatt. So from this part, we hope we demonstrate to you there's a new mechanism through the chrome-chrome ion pair can get a higher emission intensity of this newly discovered phosphor compound. So later on, we try to push from the infrared regime 1 to the infrared regime 2. So we hope we can push to more than 1,000 nanometer. So then usually the people use energy transfer from chrome to nickel, but usually nickel has a lower intensity as compared with chrome. And we try to use through the ion-ion pair, not through the isolated chrome ions. And also we tune the flux, and we try to increase emission intensity. So this one is we do the energy transfer. We keep chrome as a constant, 0.08, as an ion pair emission happens. And different amount of nickel, so we can see, because for the charge balancing, we also added a lanthanum to get charge compensate. Because of charge balance of lanthanum in Strontium side, we will see the next one. So this one just to show you with different flux, we can still keep the compound in single phase. With increasing the nickel, because nickel is about the same ionic size as chrome, but lanthanum is smaller than strontium. So with increasing the lanthanum content, so you can see the shrinkage of latest parameter as increasing of the chrome in nickel in this compound. Then later on, we use energy transfer to see. So as you can see, with increasing the nickel amount, so you can see this broadened peak appear above 1,000 nanometer. So the decay time for the R9 chrome 3 plus or the chrome-chrome pair all decrease with a millisecond, as I demonstrated before. And this one is because of rising line time from the chrome to nickel. Then with pressure effect, so you can see this time is not only the negative as R9 and the N9, but for nickel, you can see the positive data. Let's demonstrate the spin allow transition of the nickel from 3T2 to 3A2. So from this, we are allowed to increase the emission intensity of nickel 2 plus with emission wavelength more than 1,000 nanometer. So with X equals around 0.02. And with the flux, by using the boric acid, so later is boric oxide, so later is a higher intensity as compared with others. So here we just demonstrated you by using ESR, so you can see the chrome isolated site and the chrome-chrome pair. And not only for that, you also can see the chrome-nickel pair as well. So this proves the chrome-nickel can do the energy transfer. For this part, I hope I demonstrated you from the isolated chrome 3 plus and through the chrome-chrome ion pair can do the energy transfer to the isolated nickel 2 plus. Then we can increase emission wavelengths from about 900 to about 1,000 to the infrared region 2. So then for the packaging, we can see in the infrared region 2, we can get 12 milliwatt with driving current 350 milliamp. So by that time, this data is quite high as compared with the traditional one. Then I move on to the other compound to demonstrate to you the chrome-chrome cluster effect rather than the chrome-chrome ion pair. So from this part, because lacking structure investigation, if you want to drive the chrome-chrome pair to the chrome-chrome cluster. So then we use another kind of compound I will show you later. So that's based on the magnesium, gallium, chrome doping, chrome site, and the oxygen compound. So it is very similar. We use a very similar sintering temperature around 1250 degrees Celsius for 5 hours in air. Then it is only one step, so you can get completely single phase with a different amount of chrome. So with this, you can see with increasing the chrome in the gallium site, the latest parameter decrease. That's simply because of ionic size of chrome is a little bit smaller than gallium. So then for this compound, we usually call this one is a spin layer compound. If it is spin layer, so the small ionic radius of gallium 3 plus will occupy octahedral site, and for the bigger magnesium 2 plus will substitute in the tetrahedral site. But from our refinement, we found that it is not in this case. We found that some magnesium 2 plus were resided in octahedral 2 plus site with our refinement. So this one is so-called inverse spin layer. But not for this. We also found there is some gallium substitute in the tetrahedral site. Okay, so with this mutual chemical substitution, we would like to rename this compound as a partially inverse spin layer. So with this kind of compound, so firstly, I demonstrated you by using the ESR, we found that it is not only cluster, not only the ion pair. So you see more broadening that's due to by the cluster. If you increase chemical dopant of X from the small amount to the higher amount. Okay, so this one is a further proof, not only by ESR, but also by magnetic measurement. We can see there's a two peak. You can fit it as a BB model. So by using the XOF technique, so we are allowed to check chrome-chrome bond distance decreasing all the way down with a chrome substitute in the gallium side. So with this, if you V down from the 111 direction of this crystal structure. So you can clearly to see the induce of this chrome-chrome cluster very easily. So with this, we can see with X small amount, 0.02, that comes from the ion-ion pair. So if you keep chemical substitution of chrome 3 plus up to 0.06, so you can see the broader band of the emission that's due to the cluster emission. So with this, we can prove from the other evidence by the pressure effect of the smaller X amount, that's chrome ion pair, and the higher chrome amount due to the chrome-chrome cluster. Okay, both of them are all negative, negative effect. As I said, it is not due to the spin allowed. It is a new kind of mechanism. It is possibly due to the chrome-chrome pair or chrome-chrome cluster. So with these kind of things, usually you will touch the highest chemical substitution of X 0.02. But with a further chrome doping, you will see the concentration quenching. But this one, you cannot see it. Even up to 0.06, you can still keep a higher emission intensity. That's compensated by the chrome-chrome cluster. So in this part, I hope I demonstrated you this one can be excited from the chrome-chrome isolated ion, and also from the chrome-chrome pair with a lower amount of X substitution for the gallium, X about 0.02. And from the higher amount of X value up to 0.06, you are generate a chrome-chrome cluster. So then you can emit as another new type of emission, so you can see very broadened due to chrome-chrome cluster. If the chrome-chrome pair, this emission intensity is low. So as you expect, the higher radiant flux as function of drive current. So the chrome-chrome cluster much higher than the chrome-chrome pair. So now we can push from the ion pair about 6.065 milliwatt to the X equals 0.06 from the cluster can push up to 70 milliwatt for this kind of discovery. So for this part, I hope I demonstrated you from the pair and through the chrome-chrome cluster. So then we try to also use this one to push this emission into the infrared regime 2. Also use the same technique, use nickel as an activator for the energy transfer from the chrome cluster to the nickel. So with this, we also just a variation of nickel amount into the chrome. Chrome, we use two type. One is a 0.02, that is from ion pair, and the 0.06 is from cluster. With these two types, we prove nickel always in 2 plus in this different kind of formula of X. And for this, I think we can demonstrate U is from the pair. So this emission regime around 900 nanometer with a small intensity. But with cluster, so you can see enhanced emission intensity very clearly. So then we do the energy transfer for the nickel substitute in. So with different amount of chrome, then we continue to substitute nickel into this compound. Then we'll compare the data, demonstrate to you. So from this part, I think our idea is from isolated chrome, then we can do the energy transfer not only from the chrome-chrome ion pair, but also from the chrome-chrome cluster for the energy transfer and push to the nickel 2 plus. This even can enhance the emission intensity in the infrared regime 2. So as I say, not only from pair, but also from cluster with a small X amount of chrome with around X equals 0.02. If we keep chrome as a 0.06, that is cluster can energy transfer to the nickel. That's even higher emission intensity. So this is data I would like to show you. If from the ion-ion pair, the highest emission intensity only up to 66.5 for the nickel. And if for the higher amount of 0.06, so you are from the cluster for the energy transfer, you can push up to 78.9. Can we further increase this emission intensity or not? So then we increase the sintering temperature. Before is 1250 degrees Celsius. So we increase to the 1350, 1450, and 1550. With increasing the temperature, you can see the emission intensity keep increase. Up to now, we can push the nickel in the regime, infrared regime 2, can have an efficiency up to 97.4. So this data, as we believe, this is the highest data up to now, can emit infrared regime 2 with such a higher emission data. And this kind of emission also proved by the ESR. So you can see the isolated chrome site and pairs cluster, and also chrome nickel emission pair as well. So for the real package, because we always want to help Taiwan industry can have these kind of products, so now we can push up to 23 milliwatt. So that is quite high. The company now try to use this one for the real application things. Then first, we try to do for the application of intravenous injection, because if you are the kids or fat people, when you want to do the intravenous injection, that is very difficult to find out where you can get your blood out. But with our newly discovered Phosphor converted infrared chip, so you can see much more clearly, you can see this. So then I hope in the future, it's not meant to take your blood out from your body. The robot can do this, because now we cooperated with Industrial Technology Research Institute. They developed this kind of machine. So by using our infrared phosphor, so they are allowed to much more easy to find your where they can take the blood from your body, because excitation by the red phosphor, by this infrared phosphor, is much more easily to recognize the place. Not only for this, if you want to play the car or display something, in the visible light, if you draw like this, you cannot see anything. And but if you shine by our infrared LED, so you can see the behind is MCL. So that Material Chemistry Lab is our lab's logo. If you write in the word, you can see this. But if you use infrared, you only can see this kind of things. So this just for the demonstration, possible application. So then I move to the conclusions. So for the future, I demonstrated you chrome-chrome ion pair as a new mechanism. Then energy transfer to the infrared regime 2. Then I also demonstrated you by using our cluster discovery emission mechanism. And then we can do energy transfer to nickel 2+ with very high emission intensity. So what is for future? For our sense, we think nano-size infrared phosphor, it is possible. So because in Taiwan, now we develop a micro LED. So then for micro LED, they definitely need the nano phosphor. How can we develop a new type of this infrared new phosphors? So then we use a temporary method. So we use a mesoporous silica nano particle as a template. So we close this kind of zinc gallium oxide chrome tin as an activator in the solution, and within the template, they can grow with a nano size. So this one is a mesoporous nanoparticle. So the nano size phosphor can recycle in and protect it well. So now we demonstrate you this is the first mini LED. So by using this broadband phosphor can be done. So we published this one in the early of 2019. So up to now, we can push the efficiency up to 91.4% for this new nano-size phosphor. Then at the end, I would like to thank ACS Applied Optical Materials. They supported our poster work. Not only for this, I also would like to ask you to submit your paper to our special issue. So I'm the people responsible for phosphor research for this journal. So we already organized one special issue in the 2023. So we also have another special issue for the radiative cooling. And even for the AR, VR display systems, this will come in soon. So for this conference, I think if you check in the website, so we are welcome you to submit your paper. So the deadline for this one is the end of November. So I hope we'll see your paper appear in this special issue for this Phosphor Safari. So then, not only for this, I also invited for the chemistry material, write a guideline for the Phosphor Society. If you want to submit your phosphor material, if you have this guideline, if you tick all positive, I think that definitely will send you a paper for review. Then for this, I think we are in the Phosphor Society. In the beginning, we found the high brightness of yak phosphor. Then through the high CRI thermal stability of phosphor, then the requirement of a nanoband in visible regime, then comes to the broadband in the infrared regime, as I demonstrated you today. For the future, we think the smaller particle size and the nanoband phosphor, especially for the micro LED, so that is important. So as I say in the open ceremony, so please check this phosphor handbook. Definitely good for students as a starter for these studies. So at the end, I would like to thank our collaborator. There's a group in Gdansk, Poland. They help us to do the high pressure measurement. We have a long-term international cooperation project. Not only for that, let's Dr. Lenik help and Professor Mojinska to help us to measure the ESR. That is very important for our research. So this is the end of my talk. Thank you for your attention.
Thank you. And now we have time for your question before the lunch. Yes, please.
Thank you very much for a very interesting talk. My question about the nickel 2+ luminescence. I didn't understand how the quantum yield jumped from 10% to 90%.
Yeah. Okay.
Can you make a comment about that?
Yeah, okay. So first, we use the cluster mechanism from the chrome-chrome cluster. From that, we can get about 70% of quantum efficiency. And we use that for the energy transfer to the nickel 2+ site. Then we can increase infrared regime emission by using the nickel 2+ as an activator. This can push up to about 80% of quantum efficiency. Then further on, we increase the sintering temperature of that compound. So we increase the particle size of the material. Then that is a trick. We can increase emission intensity of the quantum efficiency from 80% to about 97%. That is a trick for us to discover that compound with a higher quantum efficiency.
I have a question here. Can I use this one? Yeah. Is it working, this one? Can you hear me, Dr. Liu? Can you hear me? Okay, yeah. And my question is, first of all, thank you, Professor Liu, for your excellent research. And I think you have many review articles. Also, I think you did something using the phosphor. Can you hear me? Okay, thank you, Professor Liu. This is Wei Qin. And I know you also did a lot using the luminescence to enhance the agriculture, right? The plant growth. I'm curious if anyone or you did something to study the IR emission and the plant growth. I know you did a lot for how to convert the UV and the green to the blue and the red to enhance the photosynthesis. How about the IR emission? Any effect IR emission and the plant growth? That's my question. Thank you.
Okay. So can you just simply repeat your question? Because echo, I cannot hear.
Okay. The question is for the photosynthesis. I know you did a lot. How to convert the UV to the blue or the red to enhance the photosynthesis, the plant growth. How about the IR emission? Is it possible to use the IR emission to do something to increase the production?
Yeah. I think usually we just use solid state synthesis by using the furnace conventional solid state material. I think if you use IR or other method, that could be possible as well. Yeah.
Okay, thank you. Any more questions from audience? Yes, Professor.
Yeah, very nice presentation again, Ruchi. And I'm always amazed how you managed to put almost 80 slides in 40 minutes. Really impressive. Can you show slide 24?
Yeah, 24. Oh, 开到24页。直接退出来跳比较快。
So there you see a pretty high quenching temperature.
Yeah.
But for the XS4, you also see a 20% increase between. Can you go and explain that increases temperature?
Yeah, the increase due to the maybe some kind of impurity, not impurity, some impurity level resided between the excitation regime. Then your electron probably resided less. Then with your higher temperature, that one can be excited
Back transfer.
back. Yeah.
Okay, thank you.
Yeah.
Okay, thank you. I think maybe the time for lunch, so please join me to thank Professor, and you gave us a wonderful talk again.
Thank you.
And an announcement from conference organizers. Or just
Okay, so everybody's the morning sessions now is the finish. So we have the lunch box in front of the gate. Maybe you can take the lunch box, go to the classroom. Okay, we have 3 classrooms is already open, so you can enjoy your delicious lunch. Thank you. 哒啦啦啦啦。下一套。
in terms of metal bonding, the 4D orbital had cobalt. The MMR of this hydrogen only 4 peak because they are symmetrical. If I have the cobalt nickel metal complex, it's unsymmetrical, so this 4 will split into 8 peak.
好，可以了，可以了。我先把它关掉，关掉是这样。Here。
Okay, time is up, and time is due, and then the door is closed. Good afternoon. This is Chun Gui-Wu from National Central University, Taiwan. I will chair this afternoon section. And then in this afternoon, we have 3 plenary talks, and all are very excellent chemists. I think you will enjoy their talk. And then 3 of the 2 come from Taiwan, 1 from National Taiwan University, another come from National Jiao Tong University, and the other come from Singapore, from National University of Singapore. Okay, since time is, and I think the first speaker is Professor Zhou Bitai. I think I don't need to introduce him. I think an audience must know about him. So to save some time for his talk, we are start. And Professor Zhou, the floor is yours.
Okay. Well, first of all, thank you for the kind introduction. But well, I'm the small potato, not VIP, okay? And anyway, I mean, I'm very pleased, okay, to be joined, okay, in this conference, okay? And normally, okay, I say, I don't know, I mean, which pronunciation is right, okay? But always I pronounce Safari, not Safari, okay? But anyway, you can check it, okay? Okay, but you can check it, okay? But Safari, since like when I learned in USA, okay? Anyway, I have many fields carry out, okay? You can see that, okay? But today I would like to only focus for one field, okay? And I prepare rather, limit of the slides because I would like to let you understand what we are doing, okay, for the last couple of years, okay, based on the molecular interactions, okay. And the molecular interaction actually in this field, okay, 2 kinds of progress. One is called molecule-molecule interaction. Okay, we try to extend exciton delocalization, of course, to the near infrared. But this is quite different from the Liu Luxi just gave a talk, last one, right? Because what he's doing is a transition metal or metal type of oxide. So through the cell assembly, actually the vibration mode has been drastically reduced. So he doesn't have any problem for that kinds of the problem encounter for the organic molecules, okay, in the near infrared. So I'm going to talk about this and let you understand how you're going to overcome this. Secondly, okay, I would like to talk about molecular interaction, the structure and the photophysical property of the surfactant, but limited by the time, I would like to just focus on the Xiplex, okay, and leave the eczema or cluster or like a JH aggregates, okay. If somebody would like to invite me, yes, please welcome, okay. But anyway, so this is what I'm going to talk about. All right, anyway, for the organic molecule, you have a 3n-6 different kinds of mode. So you can see once you are achieving so-called greater than 800 nanometer, even 700 nanometer, you're going to face a dramatic quenching by internal conversion, okay, which is so-called the energy gap law. The energy gap law, actually, people always use this. All the chemists and material science chemists, they all use this kind of formula, which is formulated by Jordaner, okay. Actually, he's still alive, I believe, okay, 96 or 97 years old, okay, anyway. Okay, so his formula is like this. So people knows when you decrease your energy gap of the emission, of course, exponentially, you are going to increase the internal conversion without any problem, okay. But this is an intrinsic gap you have to achieve. So you cannot increase it because you would have to go to the near infrared, okay? And then the next one will be lambda, which is so-called reorganization energy. That means the equilibrium distance, okay, of the ground state and the excited state, the difference in terms of the energy. So we call this a reorganization energy, okay? So reorganization energy, if it is increased, then you got trouble because you increase all the KIC. Okay, because this is in denominator, this is in the numerator. So these two just inverse. So you can see, okay, your quantum efficiency will drastically decrease, okay, upon decrease the delta E or or increase of the lambda, okay, then your POQY will be drastically increase. Actually, for the organic molecule, polyatomic molecule, I never seen any organic molecule emission greater than 800 nanometer with a quantum yield greater than 10%, which is almost impossible in theory, okay? So how are you going to overcome this? You have to think about, you have to move over the fundamental, okay? And then, of course, here, simply speaking, you cannot change anything. The only thing you can change is lambda, okay? So I thought about this around 2016, okay, how we are going to change this, okay? Well, the best way to do is so-called gathering together is the strength. In terms of Chinese, it means 团结就是力量, okay? So if we have a whole bunch of the molecule, okay, which can gather together, okay, like in J aggregation, okay, and this is a single molecule. So we can start immediately to see actually the vibration, okay, for 3 trimer. It's been reduced by what? By lambda divided by n. How many n cell sample? And of course, this cell assembly has to be coherent. That means it has to have a strong coupling, okay? So this is like a workman. One single workman, okay, will drill the street, okay? You can see they're shaking, okay, all the time. Okay, but for the 3 people, if in theory it's okay, all right, then the shaking will be just kind of very small. So that means you reduce the displacement of your vibration, okay? So virtually, you decrease your lambda. Okay, so this is the same thing as this, okay? So you can see, okay, previously you have a lambda over here. You have lambda over here. Now, with the 3 all cell sample together, okay, you can decrease to 3, lambda divided by 3. Okay, that means that you do decrease the lambda. If you are forming J aggregation, okay, in the case, actually, your energy can be decreased as well. Okay, and also decrease your lambda. That means that probably you can achieve the near-infrared region for organic molecule by increasing the PLQY drastically. Okay, so this is a basic idea of this. Okay, now let's see. So how are you going to achieve this? Okay, actually, okay, we sort of think about pi-pi interaction, maybe not strong enough. Okay, what would be the best way? Put the metal on the center. Okay, get the metal-metal interaction and the pi-pi interaction together. Okay, so in this case, we design so-called PT complex because square planar, you have a DZ square, which is a non-bonding over here. Okay, so they can interact with your so-called metal-to-metal interaction. I think Professor Peng Xuming just gave a talk, so you have a background of this, okay? So you can see, and how are you going to design the ligand? Wow, you cannot design ligand with the full so-called pi conjugation without changing anything because then you are going to form the H aggregate. Okay, you have to alternate the donor and acceptor for the bidentate ligand, so like this. Okay, so in the case actually, when they start to form the cell assembly, you can see it's alternative stagger type of the interaction. They give you the transition dipole, okay, in the head to tail, not head to head. Okay, so you are going to see this is a J aggregation with a pi-pi interaction and with a PT-PT interaction. They could both give you so-called reducing the energy gap as well as decrease your reorganization energy. Okay, so this is the basic idea of this. All right, so using this, okay, we're using vapor deposition. Okay, for the vapor deposition, you can see for this compound, okay, from the monomer, see? Oh, I'm sorry. Okay, from the monomer, which is 400 over here, okay, when they form the vapor deposition, they go into the 740 nanometer for the emission already. Okay, and the quantum yield, look at it. 740 for the organic molecule, okay, you can increase the quantum yield to 82%. Okay, so you can see this is a drastic event. This is a breakthrough, okay, of all the organic molecule with high quantum efficiency of the emission, okay. And then from the jigs, okay, from X-ray study, okay, we can see actually, yes, they do have formed the cell assembly, and each layer, okay, you can see each layer like this, all right? So you can see the 001, 002 are enhanced a lot. So based on this, your transition dipole is horizontal. Okay, for the horizontal, you can see the isotopic, okay, of the emission. That means that you gain the output coupling, okay? So in the case, you can see that. So this is the first one, okay, what a breakthrough, 740 nanometer, we can achieve EQE, okay, for 24%, okay, and well, there's no rooming, okay, because there's no calibration in the near infrared. So we have to use the radiance. So they can achieve 3.6 times 10 to the fifth, okay, milliwatt, okay, radiance per meter square. Okay, so this is a breakthrough at the time, 2017, okay. And we are not satisfied at that because 740 is just around deep red, not near infrared, okay, according to my definition. Okay, so we are going to move one more step, okay, how to generate those, to say longer than 800 nanometer for the emission. Well, the best way to do for organometallic is what? Is you lower your LUMO and you increase your HOMO, right, for the monomer. And once they are cell assembled, they can decrease the delta E once again. Okay, so we use this kind of strategy, okay, and then we let it go down to almost 830 to 920, okay. But this time, we have to gain deep insight into what is the mechanism of the cell assembly. Okay, although jigs, we gain a lot of experience in learning about how to measure the jigs. Okay, so this is very beautiful. We know this is a tier kind of arrangement, okay, and this is because of party group, so they have to kind of have a face on, and this is an on, okay. But anyway, they all kinds of tier and cell assemble. Let me ask you one question. Actually, I asked you one question by myself. Say, how many cell assemble can together for the exciton delocalization? God, this is a key question of this. Although I can see, all the unit cells through the fitting process, I can see, wow, 32, 34 of the molecule, they all kinds of aligned together. But this is, we know organic molecule is kind of Franco type of molecule. They cannot delocalize too much. Okay, you have to think about this. Okay, so how many they really can delocalize? Okay, actually, okay, 40 years ago, when my boss, Michael Kasher, he never said molecule is exciton. Because this is a Franco, they only can emit, excite, and then emit, okay? They never kind of delocalize, okay? When he say exciton means like a J aggregate or H aggregate, that means they can move 2 or 3 molecules, then we call it exciton. Of course, in physics, they always call exciton because the semiconductor is exciton. They can delocalize through the ball radius. So this is quite different, okay? But anyway, how many really can form this type of exciton delocalization is our interesting. So we use the physical method, okay? The physics tell you, say, the same as the band gap theory, okay? And this electron is a fermion. So whenever you excite one electron over here, then you use a multi-photon by exciton, increase the intensity of laser light. The second one cannot be localized here because what? Because each state only can accommodate 2 electrons. So the second one has to go to the K equal to 2. So K equal to 1 and K equal to 2, there will be a spacing in between, and they will follow this kind of formula they call 1 minus 2 will be equal to 2V, okay, multiplied by those how many N together for exciton delocalization, okay? And 2V can be calculated by dimer without any problem, okay? And then what you need to do is try to fit the first absorption. We use bleaching. Bleaching is the same as absorption, okay? And then we use the second one over here, and these 2 minus together, okay, and fit to this equation, you can immediately obtain how many N for this, okay? So we did this, okay? So you can see we use a very state-of-the-art of instrument, okay? We use a Fourier transform, step scan IR, so we excite and probe. Okay, so you can see actually this is bleaching, which is 0 to 0, and this is 0 to 1. Okay, so this subtract by this one, okay, you can obtain this equation, okay, and giving the V as 0.24 electron volt, okay, and fit this N is only one parameter, okay, so you can immediately calculate to say, yes, the exciton delocalization is about 5 to 6 and 8 to 9. So you can see, though not many, but really it's exciton delocalization. This is the exact proof of the exciton delocalization over here, okay? So you can see that Okay, so using this type of molecule, okay, vapor deposition, and make an OLED, you can generate actually about 890, 2.3 for EQE, okay? And for the POQY, which is the internal content efficiency, so always very high, 20%, even 30%, okay? So 910, you can achieve 1.9, and 960, you can achieve 2.5%, okay? So this is the second breakthrough, okay? We figure out how is the theory for the exciton delocalization for the organic molecule through the cell assembly, okay? Now, we are going to do one more target. The one more target is what? Try to achieve greater than 1,000 nanometers, so-called NIR2 region, okay? So in the case, how are you going to do that? Well, the previous one, we lift the HOMO, and we decrease the LUMO, right? This one is even much easier, okay? We just increase the pi-pi delocalization, okay? So we use a kind of fused ring. So a fused ring, you can see, you drastically increase the HOMO, decrease the LUMO. Okay, so in the case, they all are in 1,000 nanometer region for the emission, okay? And this time, actually, you can see very beautifully, okay? Really, they are all the tiered kinds of the cell assembly, and you even can see, we figure out all the spacing, okay, for this one. I'm not going to detail of this, but anyway, this is for sure, I mean, there's a very beautiful alignment, okay, not because of PT, but because of the fused pi ring, okay, for that. Okay, so you can see the same method that we did over here, okay, and the same fitting, okay, even we can increase to 8.5, almost 10 exciton delocalization. God, this is really world record because I can tell you, organic molecule is a Franco type. Unless it's a very strong coupling, that's impossible for you to delocalize for the 10 molecule, okay? So in the case, I mean, we set a world record of this kind of delocalization, okay? And in this case, you really can figure out what's going on for that, okay? And let me show you, okay, one more thing. And this is a critical thing for this publication. As whenever it's 1,000 nanometer, you know that the vibration high frequency of this molecule has been touching the second overtone of the environment, okay, and of the molecule itself too, okay. So would it be overtone of the high frequency, such as the CH stretching, really can quenching the emission? That's what people really pay attention. People would like to use the deuterium isotope effect, try to overcome this. Let me show you, I think the key point of my talk is deuterium isotope effect. Okay, let me show you. Okay, so people always say, well, the high frequency vibration, okay, such as CH stretching, okay, are common for the quenching of NIR. I think you all thought about it. I'm thinking about this too. Okay, so what about the CH deuteration? Okay, from CH to CD, per deuteration should give you the increase of emission in the infrared. Okay, yes, okay, you say, this should be right promptly, okay, but indeed, in theory, I can tell you, Jordan told you, say, no, this is impossible, okay. Why is it impossible? Let's check the benzene. For a benzene, when you excite to excite state, which one have a displacement? Which type of the bond has a displacement more? I can tell you CC double bond, right? Because the CC double bond is pi to pi star from the double bond to single bond like. What about for CH? I can tell you almost no change because it's not involved in the conjugation, right? This is what we thought. So you got trouble of this. For example, here, okay, if for the CH bond, actually your lambda is equal to 0, there's no effect at all, according to Jordan's equation, right? Lambda equal to 0, so CH is out of the ball game. Okay, and indeed, actually, CC double bond really kind of play the game. Okay, so when you deuterate that, suppose in theory, from Jordan's formula, you're not going to see anything at all. Okay, so let me show you the next one. Okay, so next one, let's say, according to Jordan's theory, this one, for 1 mole, CH mole is almost equal to 0. Now, I'm not going to affect this. It's the other mole, accepting mole, which affect all the KIC, not this one. Okay, so how do you, I'm going to think about this. I can tell you, say, well, this one is in 中文 we say 倒果为因. We use the consequence. We have a consequence. So we go back to the origin. We say something wrong for the Jordan type of the formula. Okay, so we have to really deeply move over the Jordan overall. What is wrong of the Jordan formula? Okay, let's see the Jordan formula here. For the Jordan formula here, actually it's the one CH bond, if it's only the accepting mode, this is derived from content over there. I can tell you, okay, there's no way you can involve the CH bond for the quenching. The only way you can think about is that one implicit variable, which is this one. He never mentioned about it, but he knows this is Weibonic coupling. This is sort of a Weibonic coupling. I know that this is sort of a Weibonic coupling, but I mean, he just leaves this as a C squared. Okay, C squared doesn't mean anything, right? So 2 years ago, we start from beginning. Okay, we start from beginning to derive all the equation. Okay, the next one, I'm going to spend 20 minutes for deriving. No, I'm kidding, okay? So anyway, I mean, I end up the equation like this. Okay, and here is from content evidence. Here is a Weibonic coupling. But you can see what's the difference. The difference is that, Jordan forgot one thing. You got to have a promoter and the acceptor. You cannot have acceptor only. Okay, for example, say, if I treat this as a promoter, okay, that means decrease the one quanta of some, say, vibration mode, and then all the rest of the vibration mode becoming the acceptor. So this becoming the promoter. Okay, so if you put the CH over here, okay, this one, Weibonic coupling is huge. Okay, though this one is very small, but this one is huge. That means what? That means actually, though this one is negligible for the CH, but this one is huge. That Jordan, he forget about that, okay? So when you put two all together, you will see actually CH really can quenching that drastically for some specific case. I'm going to show you what kinds of case they can quenching drastically, okay? So we plug this one. Of course, we got the result first. The result tell you, say, let me show you the result. The result is here. Okay, the result is here. Let me show you here. When you have a CH bonding, okay, you can see the quantum E is 10.6. When we produced this, we got the 21.3% for the increase of the quantum E. Now, this is amazing. Okay, it was because of this. We go back to derive the new equation. Okay, try to modify the Jordan's equation. And as for the mechanism, you can see actually like this. The mechanism is when you decrease one quanta by promoter, which is CH bond, okay, and the rest of energy can be dissipated by the acceptor. Okay, and the CH bond, 3,000 wave number, CD bond, 2,200 wave number. That's the reason. See here, okay, for the acceptor to accept the energy is much easier than this one. That's why KIC for this is much faster. That means the quantum E of this one is smaller than this. Okay, so this is absolutely right, okay, for this kind of derivation for the small coupling, well, for large coupling. I'm show you later, okay? So let me go to the next one. For the next one, actually, so we can over this one, and then we can use a deuterated isotope effect and generate the 1,000 nanometer of the OLED. Okay, we got the 4.2% of the EQE, okay, the 1,000 wave number, okay, and with a radiance such high, okay? So by the progress of this, you can look at this. Okay, the progress from 2017, we achieved 740, and then we derived the delocalization, okay, of the experimental and the theory. Okay, we got the 830 to 930 nanometer. And I skip this one because we can prove the interaction, okay, for this type of so-called cell assembly. And then the next one, 2022, we really kind of end up in the 1,000 nanometer with 4.2 using the deuterium isotope effect. Okay, remember that, okay, before 2022, okay, there's no OLED, say longer than 1,000 nanometer, which is impossible, okay? So let me show you the next evidence. The evidence is this. So when you have a delocalization, Okay, just like a phonon echo. Okay, you got to have a so-called echo frequency. The echo frequency we can predict in theory, but could we observe in the experiment to give the further support of my proposal? Okay, so we cancel using the femtosecond transient absorption. Now you can see all the cell assembly molecule with a high yield. We always see so-called the quantum peak. Okay, the coherence of the quantum peak, you can see it here. So Fourier transformless, you always get the low frequency, which is the phonon echo of the vibration. They give you a piece of good evidence. Yes, it has to be like this, okay? So after here, okay, we sort of like finish all PT type of the complex. We can achieve it without any problem. But PT complex, first one is kind of the cost. It's a pretty high cost. Secondly, I mean, this is a very special one. Okay, so could we achieve this kind of cell assembly, okay, by organic molecule to achieve this? We never succeed because I can show you, because organic molecule, okay, no matter how you cancel around it, your exciton delocalization is very small because they're always in a pi-pi interaction. So this is a very small coupling. Okay, you have to use the metal-to-metal coupling. But alternatively, we're using one kind of the approach. Okay, how are we going to do that? Okay, let me show you. Okay, well, before I show you this, let me show you, probably you are very much pay attention to, say, we increase the CD effect by double, from 10 to 21. What about the other NIR organic molecule? For example, the most famous one, which is Y6. Everybody knows Y6. Y6 has a good emission around near infrared, around 880. Okay, but when we deuterate it, we spend half year. We deuterate it, we don't see anything at all. 6.23 to 6.52. But how come we can increase double of this? Let me tell you, this result and this result is a so-called pros and cons for every researcher in the near infrared. Sometimes the deuterator say, God, there's no effect at all. I mean, Dr. Cho, you are cheating, okay? And then somebody say, yes, we do see that. So how are we going to unify the theory? Yes, we unify the theory here. Okay, so we unify the theory is tell you the truth. If you have a strong coupling, what does strong coupling mean? It means lambda is kind of large. For example, say here. Okay, the lambda is kind of large. You can see the lambda here. Okay, so it's our case. Okay, and for those kinds of Y6 or a lot of acceptor for a solar energy cell, the lambda is always small. Okay, for a small one, we call weak coupling. This is a strong coupling. So you can see for a weak coupling, we end up in this. Okay, for a strong coupling, we end up this. Okay, let's forget about mathematics. But let me just give a proof. Okay, for the deuterate and the non-deuterate, one more. So you can see actually the big difference is in the strong coupling. See, for strong coupling, see the red one and this red line. So you can see at 100 nanometer, God, the difference is so big. Okay, compared with the weak coupling, there's almost no change. So they tell you in theory, yes, if you have a strong coupling case, that means the lambda is strong. I can tell you, okay, you got the deuterium isotope effect without any problem. But if you have this kind of case, like organic conjugation molecule with a small lambda, okay, you cannot increase your quantum yield too much by per deuteration. Okay, so this is my our conclusion on this. Okay, all right. So finally, okay, well, if organic molecule cannot do that, okay, how we are going to do this? And we have an alternative way to overcome this hurdle. Okay, how we are going to do that? Well, we use the PT complex. Okay, here, one layer. Okay, and this is a vapor deposition for the cell assembly. So you cannot destroy it by heterojunction. You cannot mix it. So you have to vapor deposit or using spin coating for the second layer. But when you spin coat the second layer for the Y6 cannot vapor deposit. Okay, so use the spin coating, you destroy the surface. So you cannot do that. We spend half years to do that, but we can never be successful until we find one thing is, why don't we use the OPV a lot of use, so-called using the printing or using PDMS for the printing. Okay, so we use the printing method. Okay, so we print this one over here. God, we got the perfect service in the interface. So in the case, actually, through the interface of the energy transfer, okay, we can generate the high yield of this, the energy transfer to here, and then get you out for the OLED. And you might be very skeptical. How come this is sick? Okay, when you excited light, your exciton can never migrate to the interface. Yes, this is true, but not for the electron luminescence. For the electron luminescence, you can control your carrier migration. Okay, just here to here and to here. You can use the all commercially program. The commercial program can give you say how thick it is. Okay, then you just try to optimize this one. Okay, by setting up the theory first, and then optimize by your human hand. Okay, so you can do that. Okay, without any problem. Okay, so this is finally. Okay, we can cut this one. Okay, so you can see on interface. Okay, if we can set up the electron and hole in the same interface, okay, you are going to get very, very good, okay, after your so-called the energy transfer, okay, in the electron luminescence and give you the near infrared light out. How many minutes I have? Hello? Do I have more time? 5 minutes? Give me 2 minutes, okay, I can finish it. Okay, so let me sort of switch the topic, okay? But Wang Gengchong, he's going to give the talk, the same talk. We collaborate, okay, in this topic about X-plex structure, okay? For the X-plex structure, actually, this is first invented by Adachi, okay? And for the intramolecule, it's easy. Okay, but intermolecule is much more easier, okay? So for engineering, you like it. You just put the HTO, which is the whole transporting layer and electron transporting layer, you put two together, okay? For the type 2 arrangement, you also can get the so-called charge transfer, okay? And then give you the X-plex emission, okay? But what kinds of the configuration? What type of interaction? No one knows. Okay, so I spend a lot of time, okay, in trying to kind of understand what's going on, get the insight into this. Okay, so our first result is using this kinds of two types of the say Hall transporting and electron transporting material. Okay, then we pump this one, and with the stepping IR, okay, we probe the vibration structure. Yes, indeed, we do see the donor and the acceptor decrease and increase of all different kinds of vibration band. You can see it very beautifully. And all the kinetic tell you say, yeah, this is the same as the TADF. Everything is the same. Okay, so we are so exciting, okay? And even we can see the polaron. This is the polaron, not polariton. So-called polaron is, we do see the polaron growth. That means what? That means this intermolecule is quite different from intramolecule. Intramolecule has no polaron because everything is inside. But inter is on the surface. You can dissipate this carrier, okay? Plus over here, minus over here. Okay, so that means you dissociate these kinds of polaron rather than recombine this one to give you the light. That's the reason X-plex, the quantum yield, or EQE is always worse than those of the intramolecular TADF molecule, okay? So we got a conclusion of this, okay? But this one cannot tell you anything because structural X-plex is still elusive, okay? The lack of the structure, okay? So how are you going to do it? The best way is to do the crystallization. You have the crystallization, the donor and acceptor. But the trouble is TADF always have a very small interaction. Small interaction means delta H either is equal to 0 or you're positive. How are you going to grow the crystal unless? Okay, so we have an ingenious thought, okay? We just use so-called entropy driven. That means what? That means inside of this cage, there always is a solvent, 3 solvents inside. Okay, so 1 plus 1 give you 1 plus 3. That means the entropy is increased. Okay, so using this type of, we can grow this crystal, and they give you entropy is positive, but the entropy is positive too. Okay, but anyway, we can get the delta G is minus. Okay, so using this one, okay, we can easily generate this type of so-called X-plex emission with the non-structural, Okay, I'm not going to talk about structural analysis, okay? And by using a different donor, you can have a different emission, okay? But we use a typical one, prototypical one. This one, we can achieve 16% for the EQE of the X-Plex. We just published this one for 3-4 months. It's booming so fast. Okay, you can see next one. Okay, immediately, okay, one NG1.10 has been published, and one checks has been published, even still online. So you can see how popular it is. Okay, so we are kind of left behind, although we create this field. Okay, but anyways, okay, we are using alternative, using morph. Okay, using morph, we still can create these kinds of. So I'm going to think about how to use morph to create these kinds of X-Plex formation for doing this. As a conclusion, I would say, see, we start from a bulk material long time ago. Okay, and bio for micrometer type of the research. Then molecule being, okay, atomic-like, molecule-like, cluster, okay, 0 to 1D, nanomaterial, 2D material, okay, even 3D for perovskite. But now we have to think about for organic molecule, we use a smart and rational functionalization way, try to using the cell assembly for the strong coupling, and go back to here to get you so-called the new property. Okay, I would like to go to the either semiconductor or conductor. There seems to be no problem in theory. According to band gap theory, there should be no problem. Okay, here I wrap up my talk, and thank you very much for your attention.
Thanks, Professor Chuo, for the excellent talk. Now, this talk is open for question. Okay, I have one very naive question. For the platinum complex, although you call it organic, I'm not totally okay. Okay, organic. And then the function of the platinum is just because they are square planar coordination, so they can like assemble only one, or they didn't have other thing.
What I'm using right now is using strong pi stacking, and put the zinc on the center.
Oh, okay.
Okay, then you can call it. You cannot call this one non-organic, right? It has to be organic material. Okay, I don't care organic or inorganic. Once it can work, it is it.
My question is, besides platinum, because there's quite a few transition metal, they can from square planar structure.
Yeah.
So, have you changed the metal center and still have the square planar structure?
Well, to tell you the truth, I mean, the same group, you can do that. Nickel, you can do that, right? Okay, but remember that just like, who said this? Okay, well, nickel has a problem, is the DD transition is so small. Okay, unless you would like to go to the 2000 nanometer, blah, 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 and like a Ulysses type, okay, you have to use an atomic type. Though it can be perturbed by environment, by its atomic transition, okay, so they can bypass the vibration quenching. Otherwise, for any kind of molecule, you just have to worry about the vibrational quenching. Okay, and for the semiconductor molecule, like a 2536, why they have no quenching at all from vibration? Because this is a cell assembly, right? So you are talking about linear type of the particles, so they can never be quenching. All right, so this is always a theory behind, okay, without any problem.
Thank you so much for a very nice talk. I have a question regarding to the polaron formation. You mentioned about the polaron. So
mentioned about what?
Polaron.
Polaron, yes.
The polaron formation. Is it good to have this polaron in order to improve the quantum efficiency of the emitter?
Yes. Now we always do this way, okay? We also check this X-Plex, okay, by so-called step scan FTIR. When we see the polaron is huge, we say forget about this. I mean, this one, the efficiency will be bad. Okay, if we reduce the polaron absorption, they always be good. Okay, the correlation is very well. I haven't published this yet, okay? But this is a very good piece of equipment, okay? Try to, just like a sensing, okay? Try to give you the correlation of that.
So this polaron, the quasi-particle is always smaller than the band gap of the semiconductor?
Well, polaron, I'll give you an example, okay? Polaron, like I say, is a solvated or environment stabilized carrier. Okay, so in that case, actually, once it's becoming more stabilized, the absorption will be in the higher frequency. Okay, so you can check this one without any problem. Okay?
Thank you so much.
Okay. Okay, please.
Professor, it's a very interesting work. I have a question. After you replace hydrogen bonding, the PIQY increased. The molecule was platinum complex. So there's a possibility the spin-orbit coupling may be changed. So I wonder if you look at the intersystem calcium rate before and after you replace hydrogen bonding.
Let me tell you, okay, so embarrassing is it's not your English. Your English is perfect. But now I start to realize how come Peng Xunmin cannot hear that. Because of the echo, I cannot hear anything almost.
Oh, you cannot hear
Yeah. Could you translate?
No, I use Chinese to ask a question.
Oh, okay. Yeah, I can barely hear you, actually, really.
No, you cannot hear me? No. Oh, he cannot hear me. So what I need to do?
下，你要问我，他问我是吧？下问我，你会问我，再问我就好。Come on, go downstairs.
Yeah, your work is very interesting. After you replace the hydrogen bonding in the platinum complex molecule, there's a possibility spin-orbit coupling may be changed. So I wonder if you have a look at the intersystem calcium rate before and after.
Yes, you are right. Okay, because through the aggregation, we see the intersystem crossing is our detection limit, which is less than 100 femtosecond.
Okay.
Yeah, it's so fast.
Okay. Good. Thank you.
Due to the time limit, I'm sorry, no further question, because we are a little bit late. Then the next one is Professor Liu from, let's thank Professor Chu again for a very excellent talk. Next talk from Chicago, he has some reason cannot come here, so we are online, so they are prepared for that.
I have kind of perceived, it's especially, try to hear mine.
Professor Liu, can you hear me?
Yes, I can. I can.
Okay,
yeah.
great. Thanks for giving us a talk. If you are ready, we can start.
Okay.
Whenever you're ready. Okay.
Yeah, I'm ready.
Please.
Yeah. Thank you. First of all, I want to thank the organizing committee, especially Chunze, for your very kind invitation. Just very unfortunately, I couldn't get a visa, but it seems I missed a big party yesterday. I think Lucy's birthday. I just want to say happy birthday. Congratulations for your all achievements over the years. So today, what I thought I would like to talk about is still older topic, lens-like transducers for imaging. So perhaps I just focus on a few new development, but also I want to summarize the recent advance in the field of lens-like transducers. First of all, I want to thank the people, especially my students and postdocs, former students and former postdocs, who really made this my talk today possible. I also would like to thank the collaborators around the world. They are all exceptional scientists in their own. Also, I want to thank the financial support from these funding agencies. So for luminescent imaging, so you think about luminescent imaging, optical imaging, microscopies. Normally, there's two types of imaging techniques. One is label-free. The other one is biomarker-based imaging techniques. But certainly, if you can compare both imaging techniques, both have pros and cons. For label-based imaging, you can improve the labeling specificity, but also you can also enhance the imaging resolution. But the problem is you need to label the biological species, protein cells, with the biomarkers. So the biomarkers also have some the capabilities. For example, the biomarkers should have a very high photostabilities. Also, the biomarkers needs to be excited on the specific wavelengths. So if you think about the challenges for optical imaging, especially multi-wavelength, multi-spectral imaging. So I think nowadays, I think the most challenging issue is how you can achieve multi-spectral imaging over a broad range. So it means, for example, here, if you want to perform imaging in the space, so you want to cover the wavelengths from UV, gamma rays, X-rays to middle infrared regions. So basically, you have a very complicated setup. You have to have multiple detectors. So each detector designed to detect a particular wavelength. So you think about the overall setup. We talk about instrumentation. It's very complicated. So perhaps using luminescent labels, we actually can solve some of the problems. When you think about the problems with conventional optical setup, you need to use multiple, for example, multiple filters, optical choppers, multiple lenses. But if you can simplify this complex optical setup using frequency conversion materials, so certainly you can design this on-chip photonic device. I'm talking about this ultra portable device. So that could significantly reduce the cost of imaging. So here comes the luminescent materials. So luminescent materials, I think it can solve some of the problems that conventional microscopy or spectroscopy cannot achieve. So using this frequency conversion materials, we actually can, for example, we can convert near infrared light, middle infrared light into visible light. And then we can integrate the materials with on-chip detectors, because most of the detectors are in the visible range. So we can actually integrate the conventional visible detectors with this frequency conversion materials. So you can, for quantum dots, so this is I listed several classes of luminescent materials, including the quantum dots, lens-edge nanocrystals, and also the metal organic framework, curves, and the single crystals, those for X-ray imaging. So for the quantum dots, this is Nobel Prize winning materials. They have excellent capability to convert, for example, UV light into visible light or even into the near infrared regions. Laser-doped particles, I will focus on, for today's lecture, I'll focus on laser-doped materials, especially to differentiate with lensite-based complex. So last year, I'm very happy for these three researchers because I greatly admire these three researchers for their work in nanoscience and nanotechnology, especially Professor Monji Balwindi. He actually developed this the synthesis of monodispersed nanoparticles. So if you look at the Nobel Prize citation, this particular paper was mentioned. So it was done by Chris Murray now at the University of Pennsylvania. So you can see this is a wonderful paper on the synthesis of monodispersed semiconductor quantum dots. So it's not about new concept development. It's actually about improvement in the synthesis of nanoparticles. Actually, after the Nobel Prize announcement, I sent an email to Chris. He actually sent a reply email very quickly. So you can read his replies. Very humble scientist. So I will give a few examples showing how we actually can use the quantum dot nanomaterials to couple with on-chip electronics to perform multispectral imaging. Because as I mentioned earlier, if you want to perform multispectral imaging, so the setup is very complicated, but you can solve the problems. For example, in this case, Monji Balwindi and his research group have developed this colloidal quantum dot spectrometer. So you can couple with conventional CCD cameras. You can for this work, they actually synthesize almost 200 different type of quantum dots that gives a different color output. So with a spectral range of 300 nanometers. So based on the color conversion, and then they can couple with the CCD camera to resolve different wavelengths. So this is a very neat demonstration of using quantum dots to perform multispectral imaging. Okay, I want to give you another example. This is another very interesting study focused on single nanowire spectrometers. So this is if I remember correctly, this is a cadmium sulfide doped with selenium. So this single nanowires, you can see. So this is they actually can engineer these nanowires to emit different colors for different segments. So basically, they can achieve based on they can combine the luminescence spectrum and also the semiconductor, the current output, and then using the imaging processing, machine learning, so they can reconstruct the spectrums. So they actually can resolve two peaks that separated by 15 nanometers. This is outstanding research, demonstrate that you can actually achieve multispectral imaging actually using a single nanowires. So this is quite an achievement. So I mentioned this the quantum dots. So the wonderful materials that can tune the emission colors based on the quantum confinement effect. So certainly the laser doped particles also have tremendous applications for multispectral imaging because they can convert excitation light into different wavelengths of emission output. So depending on the dopant composition and also dopant combinations. So unlike a lensite-based complex or bulk materials, for nanoparticles, we actually can engineer the luminescent colors by controlling the concentration of the lensite dopants in the nanoparticle matrix. So basically, by controlling the concentration of the dopants, we actually can control the energy transfer or energy crosstalk between the lens ions. Also, we can fine-tune the luminescent colors using the surface ligands through the surface coordinations. I will give you a few examples in a moment. So this is the basic concept of lens-based photon optic conversion for color tuning. So basically, if we have a YB co-dope with TM or ER dopants, we actually can achieve multicolor emission that covers almost the entire visible range. So for example, we can use an ER as an emitter to tune the relative emission intensity of the three emission colors, red, the green, and also the blue colors. We can also use a TM as emitters to achieve the color tuning. So for these lens-doped particles, why they're interesting? Because of their outstanding optical properties. For example, for this photon optic conversion, so if you look at the optical window, if you use near as excitation, we actually can achieve much better imaging resolution because we can minimize the background absorption by the tissues or by the tissues or water absorptions. So also, if you use a near IR as an excitation, we actually can achieve much deeper tissue penetration. So all these lens-doped the systems, they actually exhibit pretty high photostabilities. So if you look at the photostability test over 4,000 seconds, you can see the emission profile is very consistent. So over the past almost 20 years since I moved to Singapore, so you can see the expanding of this up conversion nanomaterials into different fields. So there's quite a lot of different developments in bioimaging, super resolution microscopy, photodynamic therapy, lasing, photocatalysis, thermometry, and the biosensors. So I think these slides that showcase, nowadays the research can be very much interdisciplinary. So that covers multiple research expertise. So I think that in the future, the machine learning, the AI should play a significant role in this field. So I just want to give you a few examples, early examples. Almost 14 years ago, I think my group actually developed this discovery. I think it's a very important fundamental discovery by introducing the GD dopants into the lens and nanoparticles. We actually can achieve three things. Okay, one is obviously the color tuning. Also, we can actually use the lens dopant to control the nanoparticle growth. So if you introduce the GD ions into the system, we actually can reduce the particle size. Another very interesting discovery is that if you introduce a GD into the nanoparticle system, we actually can control the particle growth, especially the phase. So we actually can control the crystal phase from cubic to hexagonals. A few years later, my student then actually discovered this very interesting pulse duration based the color tunings. So if you look at the figure B right here, so you can actually see the very interesting color tuning. So different color output under different excitation conditions. So the first, the red emission is actually on the 980 nanometer long pulse. If you look at the bottom, the spectrum here is under 980 nanometer 80 nanometer short pulse as the same materials that gives a different colors, but under different excitation condition. So if you switch to AOA nanometer CW lasers, so that gives a blue color. So this is quite amazing because you think about quantum dots, if you want to tune the colors, so you have to modify the size. Even for laser doped particles, so if you want to tune the colors, you have to redo the synthesis, modify the dopant concentration. So here we actually demonstrate one particle that gives multiple colors by controlling the excitation conditions. We actually also can achieve the white colors. So these type of particles is quite interesting. For example, I can use it for volumetric 3D displays. So nanoparticles offer, so this especially laser doped particles, offer a very nice platform for fundamental studies, energy transfer studies. As Bitai actually just mentioned, some of the his molecules. So if you think about the conventional, the force of resonant energy transfer, you need a donor, you need an energy acceptor. But normally the critical distance is around the 5 nanometers. So most of the cases, it actually is less than 5 nanometers. So you think about how you're going to develop this energy transfer system based on laser doped particles, because the particle size is typically 30 nanometers. Think about if you have dye molecules coated, it's right here on the particle surface. So this is certainly if you have a laser dopants on the other side of the particle, so the cross distance is about more than 20 nanometers. So the thread efficiency must be very low. So in this case, actually, we demonstrate we can improve the thread energy transfer efficiency by taking advantage of energy migration involving laser dopants. So in this case, we actually demonstrate that gadolinium ions can be an excellent energy migrator to improve the energy transfer efficiencies. Certainly, you can develop different systems. Even you can design this particle donor system, acceptor system using quantum dots to combine with laser doped particles. So since I mentioned this organic dye functionalized laser doped particles, so a couple of years ago, so my group and also a group from University of Cambridge, so we actually discovered that using organic dye molecules, for example, rubrene, we actually can achieve direct triplet generation. So this is quite interesting because to stabilize triplet states, normally you have the donor acceptor system. Also, you have to have the heavy atom effect. But actually, using this laser doped ions, laser doped nanoparticles, we have to realize that. So this laser doped system can enhance absorption to enable the singlet to triplet energy transitions. So we actually tested several molecules, this tetrasin and also the P3HT. And this P3HT, actually, this is a very popular polymers used for photovoltaics, and also the FABT, very popular molecules, polymers for LED applications. So in all these cases, we have seen the enhanced absorption. So we actually investigate the mechanism of this direct triplet generations. This is a very interesting discovery because we realize that so this enhanced, this stabilizer triplet formation is actually not due to heavy atom effect. Because if you look at the atomic weight for these laser ions, obviously LU is much heavier than GD, but here GD, we see much better improvement. So we reason is because of this, the number of ampere electrons that can play a significant role in the enhance of this direct triplet generation. So you can also using this lens-side doped system to couple with small molecules to improve the photon up conversion. So here's another example. So you can see here, we actually did the simulations using this sodium yttrium fluoride-based systems. So if we dope with these lens ions, then couple with small molecules, if you have small molecules, so the surface coordination environment is very different from the lens ions in the nanocrystal matrix. So the nanocrystal lattice, in the crystal lattice, so the lens ions typically have typically have a 9-fold coordination. So on the surface, lens ions actually only has a 6-fold coordination. So based on this surface anisotropy reconstruction in this lens sublattice, we actually demonstrate we can using this bidentate picolinic acid, this 2PA ligands to improve the up conversion. So what this small molecule does is once it coordinates on the nanoparticle surface, so this ligand coordination can facilitate energy migration. Also, it can impede energy diffusion to surface defects, thereby enhance the energy transfer between the lens ions. So another important role is, so these small organic molecules can assist in energy level reconstruction. So if you look at on the left here, so without this ligand coordination, with the ligand coordination, you can see, with the ligand coordination, you can adjust the energy level. So in order to balance the energy transfer process. So this is remarkable, the distance between the ligand, the surface coated ligand, the lens sensitizers. So you can even have a separation distance between the ligands and the sensitizer over 2 nanometers. Okay, so this is another interesting discovery. A couple of years ago, so we thought about, photon up conversion. We always test the up conversion using near-infrared light, sometimes using the second optical window, 1500 nanometers. So we have been thinking, can we extend the detection range to middle infrared? We talk about 4 micron to 10 micrometers. So Liang actually come up with a very interesting design here. So we're actually using this ND-doped systems. So on the 740 nanometer CW excitation, so you can see the materials, the particle emit 2 peaks. So the first peak, you can see this very little intensity here is 806 nanometers. This peak is very weak because of multi-photon relaxation. So, but if you look at the other peak, 866 nanometers, is much intense. So, but if you excite it using another laser, for example, using the middle infrared lasers, you switch on the laser. So in this case, as you can see, the relative emission intensity of these 2 peaks, A06, A66, dramatically change. So this is because of this back pumping at this 4th F302 energy levels. So this design actually enables us to detect the middle infrared excitations using this ratiometric approach. So this is important because so here's the results. This is the spectrum on the left. You can see if you increase the pumping using 2 lasers, you actually can tune the relative emission intensity of the 2 lasers. So using this design, we actually can make a nanoparticle film. We can develop this nanotransducers that can be used to near middle infrared imaging. So this is quite important because many molecular vibration modes, they're in the middle infrared regions. Of course, now the challenging for this work is the imaging resolution. So somehow we need to optimize the system to further improve the imaging resolution. Okay, so I want to highlight this another interesting work using these lens-side particles for X-ray imaging. So this is very important because conventional, the upconversion nanoparticle can only be excited by near-infrared light, but the near-infrared light has limited tissue penetration. So we realize that so this special class of nanoparticles can be excited by X-rays. So we actually can make a flexible X-ray detectors. So to achieve this high resolution imaging. So we actually name the technique luminescent extension imaging by taking advantage this position luminescence of these nanoscintillators. So even after the X-ray is switched off for 5 minutes, you can see we can still see the luminescent emission colors. Lastly, I just want to quickly give an overview of recent development using the lens-side nanoparticles coupled with the compressed sensing to perform multispectral imaging. So this technique we actually call we call it space stochastic photoluminescent compressed sensing. So basically, we actually can use 4 types of lens-side doped particles that can, each of these particles can convert a particular wavelength. So for example, this particle can convert UV light into visible light. On the right, this particle can convert X-ray into 550 nanometers. Then we have another 2 sets of particles can convert infrared light, and also the second optical window excitations, 1532 nanometers. So basically, we can combine this nanoparticle using 3D printing technique. Then, based on by coupling the compressed sensing, so we can reconstruct 4 different images using this space technique. So we actually borrow this compressed sensing from the mathematical models. So this model basically states that to have this compressed sensing, the sampling frequency must be at least twice of the highest frequency component of signals. So I just want to quickly show the results of why this is better using the luminescent converters than conventional these passive filters used for compressed sensors. So using this active luminescent materials, we actually can achieve, you can see for the conventional non-randomly designed systems. So for different colors, the pixel size, we can only get 4 by 4. But using this random distribution, so we're using the random distribution of different color emitters, we actually can achieve 4 different spectrums with a pixel of pixel dimension 8 by 8. So this is the results. They show that we actually can, on the right you can see this is 2 different type of, this is the real result, the imaging results. We actually mix 4 different color emitting particles. So the patterns you can see, this actually complementary to each other. So using this design, we actually can achieve labeling, encoding 4 different color spectrum, emission at AOA, 1532 nanometers, and also X-rays and the UV light. So we actually can decode 4 different imaging using this space technology. So I think this is what I wanted to talk about today. I just want to share with you some of the recent development in the field of luminescent materials, especially lens-adjustable particles. So I think there's a tremendous room for improvement, be it imaging or biosensing or multispectral imaging. So I think that in the future is how we can combine these luminescent materials with optical electronic setup to achieve ultra-sensitive, ultra-portable device. I think that the future has yet to come. With that, I want to stop right here. Thank you for the invitation.
Okay. Thanks, thanks, Professor Liu, for the nice talk. And now this talk is open for question. Okay. You should use your microphone, otherwise you cannot hear you.
Well, thank you for a very nice presentation and overview of all the different applications for luminescent materials. I have a question about these compressive sensors with the random emitter distributions. What are the constraints on the spectra of the different colors? Do you want them to overlap or not overlap? And what are the desired widths of the different colors?
Yeah, so it's a very good question. I think we don't want the different emission overlap. So that's why we have to use a filter. So that's the challenge. I would think perhaps the limitation for these designs. So when you choose for different types of emitters, so you have to make sure they don't have a crosstalk. So you don't want the emission overlap. That's exactly the question you mentioned. So either we have to use a filter. Also, when we choose the particles, it's very important we choose that the emission, you can see, we're using these different particles, we convert different excitation into a particular wavelength without overlapping.
Okay, thank you.
Okay, if not, I think time is up. Let's thank Professor Liu again.
Yeah, thank you.
Thank you, online. Okay, for the time, a little bit. Let's go to the last talk of this section. It's come from National Jiao Tong University. Okay, Professor Xu. And Professor Xu also is a very well-known polymer scientist in Taiwan. So I don't need to introduce her. And his talk today is going to talk about something about the polymer solar cell, right? And then Professor Xu, the floor is yours. Let's welcome him.
Thank you, Professor Wu. And first, I would like to thank the organizing committee, Professor Lin, invite me to give the talk. And today I'm talking about how to achieve high-performance organic solar cell with some later type conjugate polymer and non-fluorine acceptor. And I think most of people know right now we have the solar panel based on the silicon-based material. And why we need a polymer solar cell? Because people are always thinking this polymer can be solution processable, so we can do the low-to-low coating, so we can have the lightweight and the flexible substrate, and can be produced in large scale and low cost, we hope, for this material. So the solar panel, polymer solar cell can be tunable absorption, so they can be used as a built-in integrate solar panel, or you can suitable for some indoor application. And I think here maybe not everyone know the solar cells, so I just mentioned a little bit. At the beginning, the solar panel is bilayer. It's one P-type material, the other is N-type material, and you coat it bilayer, but the efficiency is very low. And in 1995, Nobel laureate Alan Heger, he just proposed so-called back heterojunction solar cell. Actually, they just mix P-type material and N-type material together. We are polymer people are thinking it's the polymer blend. Actually, and by the some thermal annealing, or you can get the we call interdigital two channels. So one you can for the electron and the hole to come up from the cell. So the advantage of this solar cell is just one single layer, and you have the large donor acceptor interfacial layer. So the quantum efficiency is much higher. But actually at that time, it's only about 3% of the power conversion efficiency. Now, for this kind of the solar cell, they use two materials. One is the fluorine, also Nobel laureate the prize material. This has low lying unoccupied Lumo level, so and therefore so induced transfer is very fast. So it's a good material for electron transport for this fluorine derivative. The other is they use the conjugate polymer, especially for the silicon-based material, and so they put it together. So when we started to synthesize this conjugate polymer, at that time the Yanru Zheng just joined our department, and we started to cooperate each other by this kind of the strategy to design many P-type conjugate polymer. First, we do the chemical rigidification. So we fix this aromatic ring together, get the lateral type molecule. And second, you can easily have introduced some bridge atom. So besides carbon, you can use silicon, germanium, nitrogen, everything. And you also can play the Chacogen effect. So you, besides bending ring, you can get furane, silane, selenofilm, even tellurofilm. And usually we need sidechain engineering. We can introduce the long archaea chain on this bridge atom or some substituent in the organic compound. So in order to increase the solubility, also facilitate the phase separation for the blend. So we synthesize quite a lot of this later type of molecular moiety that became very important in the, recently because this molecule not just useful for the P-type material, but also they are especially important for the N-type material. And from the Alan Heger's work to about 10 years later, most of people do the P-type material and just mix with the PCBM, that's a fluorine derivative. However, this fluorine derivative is had a very low absorption in the visible region. So this is a PCBM. And the problem of this furin derivative is the synthetic cost is very high, and they have very weak absorption in the visible region. But also the most important thing is their morphology instability, because when they mix with the conjugate polymer to get the interdigital penetrate network, they were easy to crystallize when you heat up to the high temperature. So they will became aggregate for this furin derivative. So in 2015, Professor Zhang Xiaowei from Peking University, he started to do this kind of, based on our design, later core, and we do one pipe bridge, and have either a strong acceptor, so you downshift the Lumo level, and we have the very strong absorption in the visible region, and also very effective the intramolecular charge transfer. So for the PCBM, most of people do is around 10% of the power conversion efficiency for most of the conjugate polymer. But for this, we so-called non-furin acceptor, it's quickly higher than 10%. So people are attracted. And today I'm just talking about we doing some carbazole-based non-furin acceptor. In the 2012, we did this carbazole-based the later type moiety, and do the conjugate polymer, and the efficiency can improve quite a lot. So when we started to synthesize this carbazole fused ring, it's quite complicated. I'm not go to the detail for the synthesis, and we have the silicon bridge and nitrogen bridge, and at that time reach about 5% of power conversion efficiency. 2012, that's quite high at that time, with the furin N-type acceptor. So we just started to do the molecule with the as the so-called non-furin acceptor through this pi bridge, and add this moiety IC unit as the strong acceptor. So certainly the power conversion efficiency with our conjugate p-type polymer is around 10%. Then we started to modify this molecule with many approach. First, we replaced this aromatic ring with some aqueous chain. Even although the synthetic method is quite complicated, but we finally got this molecule, and we can also do the fluorination or the N group effect. So when we mix this polymer with several conjugate polymer, like a J71, you can see it can cover all the visible region. So the power efficiency is also around 10%, and they are all face-on orientation. You see very strong face-on orientation after the mixing with our non-furin acceptor. Then this is the J71 you see here, and use another. This is the other is right now is mostly called PM6. developed by Ho Jianhui group in the academic of science case in mainland China. You see the absorption actually complementary. This is our langfluorine acceptor, and this is two kind of the P-type material, one J71 and this PM6. Actually, we just mix together as the active layer, and we can gather the absorption in the visible region, and certainly the power conversion reach about 13% of the power conversion efficiency. And if we do the further N group with the fluorination and the two coordination, the material can be improved. And also we do the extension besides one silicon ring with the TT ring. They can be improved because the conjugation length increase. You will shift to the red light region, so the absorption will be higher or in the all visible region. So we just mix this langfluorine acceptor with the PM6 here. So you see the absorption. This is the conjugate polymer. This is the langfluorine acceptor we synthesize. So we see they can cover, go to the near IR region for this langfluorine acceptor. So the power conversion efficiency for this DT4F, that means just one carbazole and one silicon ring. The JSC, just the absorption of this visible region is narrower, so it is about 20. But if we extend to the TT unit, then can reach about 15%. At that time, this is maybe the highest for the langfluorine acceptor. And we also do some this langfluorine acceptor to so-called Y6 material. Professor So just mentioned about the benchmark material, because Yingping Zhou in the 2017, he published this Y6 material, certainly in Joule, and at the time, the efficiency is 15.7. So it's a very sophisticated material, and we just add our material as the third component, just mixed with the PM6 and the Y6, and this ternary blend, so can reach about 16, nearly 17% of the power conversion efficiency. And the reason is we call it because the problem of Y6 material, their VOC value is less than is only 0.8%. Although their absorption is strong, and so it's 25 for this J value. But our material, carbazole, had a very high VOC. So when we mix the three together, both the VOC value, and we can keep the high VOC value, and also the JC and the fear factor also increase. So it's the reason why we can reach about 16.5. And if you modify this cathode material a little bit. Just change it. Here is a BTBO. Actually, it's also Y6 material. Just here, the branch is different. And we mix this cathode material as the ternary blend for PMS and this modified Y6 material, and finally can get about 18% of the power conversion efficiency. So that's quite high in the record. Then the OPV polymer solar cell, the problem is the long-term stability. Because I just tell you, when you heat it up to the high temperature, usually we reach about 150 centigrade. They will, when the two polymer blend usually mix very well and get a good morphology. But when you heat up too high temperature, the acceptor usually will aggregate, and the device will decay very quickly. So due to the morphology instability, so the OPV material will decay very fast. So we are thinking we can use the polymer strategy to fix the morphology. So we synthesize this fluorine derivative at the beginning, just add the two styrene group, and when you heat it up to the over 160 for 30 minutes, they will be polymerized, get the polymer. And also, if we can use the other is oxytane. This oxytane can be photopolymerization. So this group, so at the room temperature, you just shine the UV light, you can get a cross-link polymer network. So you will stabilize this fluorine derivative. We show it very early. For example, here, I just show you, when we mix the PCBM with the conjugate polymer, for example, P3HT, and you annealing, thermal annealing around 110 degrees, you can get optimal morphology. That means you have the channel of the anti-material fluorine and the conjugate polymer. But if you heat up to the high temperature, here we just use 150 centigrade, you will see they will decrease quite quickly. After 25 hours, you show the efficiency is very low. It's less than 1%. So when we ate a little bit, maybe about 5% of the fluorine delivered with this cross-linkable fluorine moiety, then you can fix. We just heat it up to high temperature, get this optimum morphology. Then you heat it up to 150 for 30 minutes. Then you will fix the morphology. So you see, after 25 hours, the PC value is around the same. So we published this here in 2010. That's quite an important work for this polymer solar cell. And very recently, because we found that this material also can be useful for the PM6, Y6. So we just add this cross-linkable into the PM6, Y6 active layer. And you see here, when we cross-link this PCB-SD, you rinse with the chloroform, you will see the UV absorption of this layer is the same. That means you can get a robust polymer network, so it not washed out by the chloroform. And also on the zinc oxide, there on the top of zinc oxide, you have the cross-linkable, the contact angle will increase quite a lot. And after you have the active layer, you will heat it up to the high temperature. Here is 500 hour. You see at the beginning you get a quite good morphology. And here you have roughness is increased quite a lot. But if we have this fluorine as the interfacial layer, then after 500 hours, you still keep quite the same. The roughness is the same. So here is because we have the this cross-linkable PCBSD better for active layer deposition and prevent. Also, the important, many publication in the literature for this PM6Y6, when they have the long time, this will cause some degradation of the Y6. The reason is because on the zinc oxide layer, they will, when you shine the light, they will generate some photoelectron. And this photoelectron will cause the degradation of the PM6. But if we have this cross-linkable material, not only improve the power conversion efficiency because due to we get the better field factor, that means morphology is better. And so the power conversion efficiency increase. And the most important is the long-term stability. They are keep quite the same. Introduce this cross-linkable interfacial layer to the PM6Y6 active layer. Then after 9,000 hours, still keep about more than 80% of their PC value. And finally, I just talking about some of the cross-linked PCBSD also useful for this perovskite solar cell. I think everyone knows perovskite. That's invented by two Russian, discovered by two Russian scientists. And people use the dimethyl iodine, by dimethyl amine and lead iodide. They can use the form this ABX3 crystal structure. So it's organic and inorganic hybrid perovskite material. And Miyazaki in 2009 used this perovskite as the dye-sensitized solar cell dye, can got the OPV. Then afterward, many people use this perovskite as the active layer for the solar cell, and they can increase quite quickly. Right now, it's about 25% of the power conversion efficiency, so it's very high. Now, we use this cross-linkable material, just add to the perovskite layer, and as both the interfacial layer and add to active layer at the beginning can improve the stability, so get about 17% of the PC value. That's use the zinc oxide, not a high temperature titanium oxide layer. The reason is because we have this cross-linkable PCBSD or PCBOD. They have the cascade transfer for electron and hole. So that's the reason why they can get a higher PC value. And we also use the titanium oxide, not instead of the zinc oxide, they can be improved higher, get to about 20% of the PC value. And for the flexible substrate, this is not the flexible. Besides our PCB-SD, we just add graphite dye-in, this material mixed with the PCB-SD. The result even better for for this perovskite. And this is also useful for flexible substrate because perovskite usually had quite a brittle crystal grain, and so it's easy to crack for the flexible substrate when you bend it. But if we have this robust cross-linkable layer, then it can be quite stable for this perovskite layer. So they got also around 20% of the PC value. And more recently, we used this tin perovskite, and also it worked. So the record is about 23 PC value. And also you see the long-term stability with this cross-linkable PCB-SD. So just accepted by the advanced material recently. And we use the OPV, we just do some large area OPV modules. It has potential application for the agriculture, the greenhouse agriculture application. So in conclusion, I just show you we synthesize a lot of the conjugate polymer, and also more recently just focus on the non-fluorine acceptor based on this the carbazole material. At the beginning, we use this just silicon ring, then fuse with the TT ring. They get also do the fluorination and chlorination of this acceptor N group, and they can improve the efficiency. So they reach about 18% of the PC value when we add this material as a third component for ternary blend with the PM6 and the Y6 material. And we also do some indoor application I did not mention today. And the second part I just told you, we synthesize both cross-linkable PCB-SD and PCB-OD. These both material are useful for OPV device and also perovskite in order to improve their long-term stability. I think this is quite important. And I thank the supporting financial support National Science Technology Council and also Ministry of Education. Actually, many work cooperate with Professor Yan Lu Zheng. He did all the molecular design of those kind of the later molecule. And I thank my hardworking student, and thank you for your attention.
Thanks, Professor Xu, for the wonderful talk. Now this talk open for questions.
Yeah, I have one question. Can you hear me? You mentioned the longevity or stability for like more than 9,000 hours. How do you test for that?
Oh, we just not yeah, this one we just put in the actually that device is put in the air without encapsulation. Yeah.
You actually wait there and you put there and waiting for 9,000 hours, right?
Yeah. After 9,000 hours, measure it again. Some take out some time and measure. So we have so many data.
Okay, thank
You see the maybe the 100 hour, 200 for the long time. Yeah.
Okay, thank you.
Thank you, Professor. I think in slide number 6 or 7, you mentioned about HOMO-LUMO OPT. Is it optimization structure? Did you calculate with quantum calculation or?
I beg your pardon.
Yeah, I think slide 7 or 8, you mentioned about HOMO-LUMO
this
optimization.
one, the together. Usually, when you add this, two n-type material together or one n-type together, usually not everyone is work can improve the efficiency. Sometimes you will get the worse result. I just showed you. The ternary brain, you mean. So I think recently Professor Yan Luzhen just published one paper in JAX. That's to study why the Y6 is so good. Because this usually you need to design the molecule is like a C shape. And you hide all your archaea chain inside this C shape. And actually our capital also, this structure is not very correct because it's also some kind of the C shape. We have hide this long archaea chain within the C shape. And so it's a molecule, the n-type molecule can pack with the very crystal structure. So they will be complementary. If you have the two n-type material, the shape is very difficult. Then they will interfere each other, so you can get a good morphology. Then you will get a low power efficiency. So not just add each one is efficiently. And for our this non-foreign acceptor, we think the absorption is complementary, and also the morphology is complementary, so they can get a good high efficiency.
Thank you, Professor.
Any question? If not, I have a quick one. I think the solar cell you measure, you fabricate is a very small area, right?
Yeah.
And you want to, if they want to go to real application, you need enlarge.
Yeah.
So I was wondering if, we say the same donor, and then you have two acceptor like A and B, and A in small area higher efficiency.
Yeah.
Are you sure when they enlarge the size of the cell, is still A efficiency is higher, or based on the structure, maybe for the large area, B will be better? Have you think about that?
Decrease. Actually, for the truth is the OPV. Right now is, for example, it's about 11 or 12% only when you have the large area. Well, here we have the large area over 200 centimeters square. That panel, and it's 11 to 12% only. And perovskite also, some people can over 15 or nearly 20. It's depend.
Okay. I think pretty much time is up. I think everybody is eager for a cup of coffee. Let's thank you, Professor Xu Yang for a wonderful talk.
Thank you.
And we are close for this section. Maybe the organizer have something to talk about, the housekeeper.
Okay, since the Professor Wu's as the chairman, so for today's apparently the speakers we just finished here, and after the coffee break we will continue have the sections. So please pay attention about the agenda's book. We have the 4 rooms together for the speech section. Okay, thank you very much. So maybe you can take the coffee break in the outside.
伯君，我找你。 老师不好意思，可以出一下声吗？我们测试一下音量。
哎，能听到吗？
有听到。
Slide 正常吗？幻灯片正常吗？
目前
那
可以把那个灰色的框把它移到中去，你电脑 老师，喂，老师不好意思，左下方还是有一个灰色的框框。
哦，对。OK 了吗？现在 OK 了没？
Okay, so hello, how are you? You here?
Yes.
Okay. Okay, so we'll start the last session of today. Okay, the sound is not so good in our room. You say okay? Okay, so please start.
Okay. Thank you, Chairman. Hello, everyone. First of all, I would like to thank Professor Lin Chunze for inviting me to this wonderful conference. It's a pity I can't meet you guys there. Today, my talk will focus on the topic of near-infrared luminescent 136 quantum dots. In this morning, Professor Andres Lin gave a very nice introduction of 26 family quantum dots. This is my talk table content. First, I will give a very brief introduction. Why we are interested in this kind of near-infrared 136 family quantum dots, followed by their proof of concept applications in the fields of LEDs and biomedicine. Near-infrared luminescence in a window of 700 to 2000 nanometer recently received reviving interest due to their unique features like low autofluorescence and deep penetration of tissues, which is extremely promising for biomedicine and AI applications, such as guiding precise surgery and eye tracking. Here too, several kinds of near-infrared nanoprobes has been explored, such as single-wall carbon nanotubes, organic dyes, rare earth-doped nanocrystals, and quantum dots. Among them, quantum dots possess unique optical properties, including quantum confinement effect, large light absorption, and broadband excitation, and tunable emission. Nevertheless, conventional 2,6 or 4,6 family near-infrared quantum dots contain toxic elements like lead and cadmium, which hinders their practical applications in biosensing. Thus, it's urgent for us to develop cadmium lead-free but efficient near-infrared quantum dots. 136 family quantum dots are regarded as a promising alternative to conventional 2,6 or 4,6 quantum dots. Due to their superior PLO performance, like broadband emission and large stock shift and long PLO lifetime, most importantly, eco-friendly composition. The band gap of most 136 quantum dots are relatively narrow, usually in the range of 1 to 2 eV. Therefore, these quantum dots exhibit near-infrared PLO emissions, showing great potential in near-infrared applications. However, their emission region was generally limited in visible to near-infrared 1 region. In addition, most of these quantum dots exhibit relatively low PLO quantum yields. For practical application of 136 quantum dots, the bottleneck lies in their relatively low PLO efficiency and limited emission region. So the key issue is how to tune the PLO properties to fulfill various application requirements. By means of our customized photophysical measurement platform, we propose several strategies, including cautious design, composition tuning, and band gap engineering to optimize their PLO properties. This is our customized photophysical measurement platform. It's modular design with different kinds of laser sources located in the center of a clean room, coupled with several kinds of spectrometers. Here is the overall specifications. By means of this platform, we focus on inorganic luminescent nanomaterials for decades, covering from their very fundamental electronic structure and excited state dynamics to optical property design and applications. Next, I'll show you a few examples for the design and application of such 136 quantum dots. Currently, it remains still challenging to fabricate high-performance near-infrared micro-LEDs because conventional near-infrared phosphors generally suffer from large particle size or low PLO quantum yield. In this part, I'll show you our strategy of designing highly efficient near-infrared nanophosphors based on 136 quantum dots for micro-LED applications. High-quality copper indium selenide quantum dots, hereafter referred to as Caesar quantum dots, were synthesized via hot injection method. To tune the PLO properties of these quantum dots, we first doped the zinc ions in quantum dots. The quantum dots were tetrahedral-shaped nanocrystals with a size around 6 nanometer, with increasing the precursor ratio of zinc to indium. The absorption tail will be shifted, blue shifting, and the emission peak shifted from 945 to 750 nanometer. The absolute PLO quantum yields significantly increased from 13% to 29%. Our theoretical calculation also confirmed that higher zinc content resulted in larger band gap here, and PLO blue shift upon zinc ion doping due to the very strong hybridization of zinc 4s, 4p, and selenium 4p states in a conduction band minimum. Based on our formation energy calculation, we found the zinc ions would prefer vacancy side instead of indium or copper cation sides. To further improve the PLO efficiency of zinc-doped quantum dot, we coated a crystalline shell of zinc selenide with a wider band gap to protect the Caesar quantum dots. Its size slightly increased from 6.1 to 7.2 nanometer. the PL quantum yield is greatly improved from 29% to near unity 93%. The effective PL lifetime is also prolonged from 221 to 307 nanoseconds. Furthermore, the PL stability of these quantum dots was also greatly enhanced after coating. The integral PL intensity of core shell quantum dots maintained 87% after 150 days at room temperature. While for those core-only counterparts, nearly no PL signal can be detected after 40 days. To reveal the mechanism of PL enhancement, we then performed femtosecond transient absorption spectroscopy. The decay curve can be fitted by a tri-exponential function, which showed two fast processes, A1, A2, and one slow process, A3. The fast processes were associated with the non-radiative recombination of electrons to the surface or internal trapped states, while the slow process was associated with the radiative recombination. As you can see here, after coating, the contribution of radiative recombination markedly increased from 19% to 68%, which indicates that most of the trapped states were eliminated. Furthermore, we discovered that the thermal stability of these quantum dots was also improved after coating. According to the temperature-dependent PL spectrum, the thermal activation energy of core-only and core-shell quantum dots were determined to be 55 millieV and 116 millieV, confirming that coating the zinc selenide shell effectively inhibited the non-radiative process and increase the thermal stability of our quantum dots. To exemplify the application of our core shell quantum dots, we fabricate the near-infrared phosphor-converted LED by combining core shell nanophosphors with a commercial blue chip. The LED device exhibits remarkable thermal stability with 72% remained at high temperature for 23 Kelvin, a high moisture resistance with 19.5 remained after aging for 72 hours. By increasing the drive current, the near-infrared output power continuously increased. Specifically, at a drive current of 350 milliampere, a near-infrared output power of 89 milliwatt was realized, which is the highest among the reported lead cadmium-free quantum dot-based near-infrared phosphor-converted LEDs. Our 7 nanometer small quantum dots are ideal for application in near-infrared micro-LEDs. By means of electron hydrodynamic jet printing, we fabricate near-infrared micro-LED by adopting core shell quantum dots as luminescent converter ink. It resulted in uniform, very uniform and shape controllable microarrays with pixel and stripe arrays diameters down to 4.2 and 3.7 micrometers, which significantly exceed the resolution of commercial inkjet display. Moreover, other complicated shapes like a pentaphore, can also be perfectly printed, which reveals the flexibility of our quantum dot inks, particularly a more complex pattern of Chinese Academy of Science logo with 10 times 10 millimeter was successfully printed. Bright and homogeneous near-infrared light emitted from locally enlarged images can be observed here, confirming the high uniformity and reproducibility of our microarrays. Besides LED application, Caesar quantum dots are also excellent candidates for nanoprobes in bioapplications. In this part, I'll show you our strategy how to tune the peer emission to near-infrared 2 region, while composition and size manipulation for versatile bioapplications. The composition of 136 semiconductor can be tuned over a very broad range since they can form a long-range ordered vacancy structure, which results in excellent composition tolerance and peer tunability. Specifically for these quantum dots, by varying the stoichiometry of the selenium to indium ratio from 0.5 to 4, we can tune its size from 5.4 to 10.3 nanometer, and the emission peaks shift from 920 to 1224 nanometers. The near-infrared 2 quantum yield of our core quantum dot can reach 22%. Note that the quantum dot showed a very broad excitation band extending to near-infrared 1 region at 820 nanometers. Through surface modification, our hydrophobic OA-capped quantum dots can be transferred to hydrophilic lipo-capped quantum dots. These lipo quantum dots were then conjugated with anti-apican antibody via EDC NHS chemistry protocol to obtain antibody-linked quantum dots, which can be well dispersed in aqueous solutions. The successful bioconjugation was verified by Fourier transform IR spectrum here. Such antibody-linked quantum dots exhibited high specificity to CTC, that's namely circulating tumor cells or MCF7, which is a human breast cancer cell and apican positive. After incubation for 2 hours, upon visible excitation, bright near-infrared pyroluminescence from quantum dots can be detected on the surface of these MCF7 cells. While for the control experiments here, by replacing MCF7 with hello cells, or by replacing antibody-linked quantum dots with lipo-capped quantum dots, near-infrared photoluminescence can hardly be observed in the surface of these cells. All these findings verify that our antibody-linked quantum dots can be successfully used as near-infrared nanoprobes for targeting apican-positive tumor cells. By virtue of the high specificity of our antibody-linked quantum dots to MCF7 cells, we then applied these nanoprobes for in vitro detection of CTCs. Upon 808 nanometer excitation, the near-infrared 2 peer signal of antibody-linked quantum dots was found to enhance with increasing the number of MCF7 cells. The linear range is from 10 to 5,000 for MCF7 cells, and the limit of detection was determined to be 12 cells per well. We further apply these nanoprobes for real-time tumor-targeted imaging in live mice. The imaging of tumor area here became clearer from 0.5 to 8 hours post-tail vein injection because of the increased tumor accumulation of nanoprobes, exhibiting the maximum signal-to-noise ratio of 5.8 relative to later non-target region at 8 hours post-injection. Also, blood vessels with diameter of 0.36 millimeter can be well distinguished here, which reveal the excellent spatial resolution based on our nanoprobes. This is the typical real-time imaging in live mice at 4 hours post-injection based on our near-infrared 2 quantum dots. Particularly, the near-infrared 2 period signal can also be detected in urine and feces here after 4 hours post-injection. After 30 days, no pathological changes were observed in the major organs. This result, which indicates a very rapid clearance via hepatic and renal pathways. This result confirms that our nanoprobes exhibit excellent biosafety. Besides biosensing, our causal quantum dots are also highly promising for near-infrared light-triggered tumor therapy. Specifically, these quantum dots exhibit superior photothermal conversion capability upon 808 nanometer laser irradiation. Meanwhile, they can also generate ROS like hydroxyl radicals originating from the triplet energy transfer or quantum dots to adjacent oxygen or hydroxyl groups. By supermolecular host gas cell assembly between hydrophytic quantum dots and amino acid precursors, scissors quantum dot can be conjugated with amino acid helical nanofibers. Scissor quantum dots can be conjugated with amino acid helical nanofibers with induced chirality. The hybrid hydrogel possesses superior absorption and luminescence dissymmetry factor, which is in the order of 10⁻² and 10⁻³ magnitude, indicating its outstanding chiral-optical property. For left-handed quantum dot hydrogel, upon 808 nanometer left circularly polarized light irradiation, we successfully achieved synergically enhanced phototherapeutic efficacy by combining the improved photothermal conversion efficiency and elevated ROS production. Furthermore, we carried out the near-infrared circularly polarized light-triggered in vivo tumor phototherapy. Particularly, improved tumor inhibition was observed in left circularly polarized light-treated group with the inhibition rate of 83% after 16-day treatment, showcasing the synergistically enhanced anti-tumor efficacy of our chiral quantum dot hydrogels. This is our conclusion. In brief, in this talk, we explored a novel class of 136 near-infrared nanophosphors based on India selenide quantum dots, which were employed for fabricating near-infrared phosphor-converted micro-LEDs with excellent performance. Moreover, we can tune the period peak of quantum dot nanoprobe to near-infrared 2 region, which were then successfully applied for background-free biosensing of CTC cells and near-infrared circularly polarized light-triggered photothermal and photodynamic synergistic therapy. The story is just beginning, and there are still a lot of future work to be done. Specifically, like here, for instance, the band gap engineering near-infrared 2 pure quantum year improvement and long-term biosafety, and eventually for multifunction applications in different scenarios of flexible electronics, QLED, or cancer diagnostics. Finally, I would like to thank the financial support and all my group members and collaborators. All these, most of these were done by my two PhD students, Lin Wei and Gao Han here, these two students, and co-supervised by Professor Du Datao and Professor Liu Yin. Particularly, thank you all as reviewers or contributors for continued support for journal luminescence and Science China materials. As some of you may know, I'm the editor-in-chief of Journal Luminescence and associate editor of Science China materials. Thank you all for your attention.
Much for your excellent talk.
Okay, thank you, Professor.
Thank you, Professor.
Could you
Yes.
please show your slide, page number 14?
Page number 14.
Yeah, you mentioned.
Which slide you mentioned?
Page number 14.
Page number 14. 14.
Yeah. Yeah. Okay, may I know what kind of method that you use in theoretical aspect here?
Sorry, it's not very clear to me here.
No clear. Please,
Your question, I cannot hear very clearly.
Yeah, my question is, I want to know, may I know what kind of quantum calculation or computational method that you use in this part, in theoretical calculation?
Oh, this collaborate with another researcher. For the detail, here the composition is shown here for this composition, but it's not done by me, so I can't remember the details for these calculations. Yeah.
Okay, thank you, Professor.
Okay, thank you, Professor. Thank you.
Yeah.
Hello. Thank you for the presentation.
Yes.
I have two questions. The first is that the 136, the quotient material for visible range, has the severe problem of the tail emission. So, and this kind of the tail emission is originated from the defect, the concentration. From your the decay time analysis result, the defect level is highly removed by making shell. So is this the asymmetric wavelength, the emission shape is also exhibited in your research?
So you are curious about its pure origin?
Pardon?
I mean, your question is about its photoluminescence origin.
Yes, so I mean the asymmetric waves, the shape, and relationship between the defect concentration.
Effect, which concentration?
Defect.
Defect, okay. But yes, this is a very good question, but hard to answer your question. You know, so far the pure origin of this 136 family, 136 family still remains not very clear. Even after we have performed this measurement or calculation, we just guess here. We guess it's a pure emission. It's related to free to bound localized states like the COP defect states. Yeah, it's not free to bound originate from this kind of emitters, this kind of emissions. When we coating the shell, it will significantly reduce the carb vacancy. So this is why we can get improved PL quantum yield. I hope this clarifies your concerns.
Thank you very much.
Yeah, thank you, Professor Chen, for your wonderful talk. It's really nice work. And I'm Shi Hui Wen from UTS. And my question is maybe about the surface modification of the nanoparticles. In your slides, you show the 25/25.
25?
Yeah. I want to know after the surface modification, when the nanoparticle transfer from the oil phase to the water phase, whether the quantum yield will reduce or how much it will be reduced.
The quantum yield, the PL efficiency will slightly reduce. I can't remember the exact number right now. Yeah, slightly reduce.
Yeah, because we use the lengthened Doppler nanoparticles for the near-infrared two regions emergence. We find that when we transfer them to water, and the emission will reduce very significantly for us. So maybe we can learn a lot from you, from your method for the modification.
But remember, you have to, in our some particles, we coat a shell or like a zinc selenide or zinc sulfur. So that's very helpful for this kind of quenching. Yeah.
Okay, thank you. Yeah, thank you.
Thank
Okay,
you.
very sorry. The online process happened some sound program. Okay, so let's thanks again to Professor Chen. Okay, thank you.
Thank you.
Thank you very much. Okay, how are you, Professor Xue? You can ready?
Yes, yeah.
Oh, it's a great pity. So not to face to face. Okay.
Yeah. I'm sorry. So, okay, so can I start?
Okay, please.
Okay, so good afternoon, everyone. So first of all, I should give my thanks to Professor Linchunde for inviting me to give this talk. So I'm very sorry, so I cannot go to Taipei to meet you all. So the topic of my presentation is the data-driven discovery of luminous material for lighting and displays. I'm from Xiamen University. Okay? So in this talk, I'm going to introduce the following three contents. One is the method for phosphor discovery. And second one is introduction to data-driven phosphor discovery. And the last one is the new phosphor discovery in our group. Okay, so traditionally to find a new phosphor or luminous material, so we usually use the trial and error approach. So we start from the ICD or database to find a compound and dope this compound with some rare earth ions or transition metal ions, so we can get a new phosphor. So actually, so we now group typically we now was in length, so we discovered this many oxide or nitride phosphors by using this method. So here to these tables, you know. But this method is you know, time consuming, also very heavy lab intense, you know. Okay, so another one is proposed by Professor Song in Korea. So he proposed a heuristic optimization based combinatory chemistry. So first he designed the parameter space, for example, based on the appearance, and then using this kind of strategy to do some solid state combinatory chemistry to make some powders, and then to have a target. For example, in this case, use the blue emitting phosphor, and then use some experiment finally to get a single phosphorus in these kind of powders. So using the powder XRD, so can determine the structure of this kind of new compounds or new phosphorus. And then actually he found several types of oxide and nitride phosphorus in his lab. So another one is proposed by Professor Schnick in Germany. You know, he grows some large sized single crystals, for example, some nitride compounds, and then using the single crystal XRD determination method, it find the structure of the kind of materials. Okay, so in his lab, he also discovered a lot kind of new compounds, typically the ready emitting phosphor 258 or 1147 compounds like this. So also he suggested some kind of new method, for example, the structural unit substitution. For example, he found a model materials, a model compound. by substituting this kind of materials with lithium nitride or aluminum nitride, even the alkaline earth ions, it can replace this kind of compounds with this kind of structural unit and form some new types of nitride compounds like this, the strontium lithium aluminum nitride, and barium and magnesium gallium nitride. And due to this kind of compounds with European 2+, we find that these types of compound can emit red emission and have very narrow emission band. Okay, so it's very great progress in the phosphor research field. And also based on this kind of method, Professor Zhi Guoxia also found some narrow band blue and green emitting phosphor in this natrium lithium silicate compounds. So also found some interesting new phosphorus. And in actinium, so we another group, Hirosaki and Takeda, and we propose a single particle diagnosis approach to find some new phosphors based on this method. So here shows some process of this method. First, we synthesis of several kind of chemical composition. We see all called a powder library, and pick one composition from these 5 powders, and the UV irradiation, so we can find several types of emitting powders, and pick up one of them, and using the single crystal XID method to determine the structure. So, for example, in this case, so we find that in this kind of powders, so we find some single crystals and some agglomerates and some polycrystalline crystals. So in this case, we use a single crystal to determine the structure. So here I show some examples of this method. So we can use different size and different shapes, and also even different particle size. And with this method, we can clearly determine this kind of structures. So this method, we actually in 3 years we found more than 15 new phosphors in our lab. So okay, so here shows an example. For example, in this kind of compositions on the space. So we found some red, blue, red, or even green, or even red phosphorus in this kind of materials. Okay. So, but all of this above mentioned method depend on some experiment. So the efficiency is not so high. So then we needed to find some high-speed discovery of new fossils. So here, next time we introduced the data-driven fossil discovery method. So actually, when we are searching for a new fossil, usually we ask the following question. For example, which are the suitable fossil hosts? And actually, we try to find a compound that can be doped with rare spines or even other types of metals. So and then find a high efficiency fossil for desired properties. So the next one is whether is the emission predicted. So this is also we should often ask the question. Another one is how to obtain narrowband or even broadband emissions. And the next one is quantum efficiency high or low for the discovered fossils. And the next one is how is the thermal quenching of this theory for the practical applications. So, but using without any experiment, we cannot answer this kind of question. But using data-driven method, so maybe we can find these answers without any experiment, doing experiment. Okay? So the basic idea of this driving data material discovery. So I show you some examples. This is published in Nature Communication by Xin. So there are a lot of kind of candidates in the database. So, but we cannot try everyone because it costs a lot of kind of time and even the cost of high cost. So we need some describers to screen the target proposal. For example, we use the thermostability or chemical stability, or the band gap, or even some the band time to screen this kind of candidates. And finally, we can get a very small number of candidates. So at this period, at this stage, so we can do experiment with a small number of materials. So, but in this case, we need to find the descriptors for screening this kind of material. So, and also we should use the high throughput calculations. And this technique is very important in this kind of method. So, if you were searching for in the reference, we found that for the AI assisted material discovery in 2000 and 2023, you can see the number of papers published is growing fast, typically in recent years. This yellow one means the AI plus luminous materials. The number also is increasing in recent years. Okay. So the three very important parameters in kind of data driving materials is the database. So database is very important, the basic item in the kind of method. Another one is material computation, typically the high throughput out of computation or the machine learning method to find some relations between the structure and the properties. Another one is either the high throughput experimentation and analysis. So these are three key points of this kind of materials. Okay, here are two examples in Wang's lab. So he proposed the data mined ionic substitution to find some new fossils. Actually, he find some descriptors for searching for fossils. For example, the chemical stability, and also the band gap, and also the debate temperature. So use these three descriptors, they can searching for the target phosphorus. So his idea is simple. So choose candidate from the ICD database and using some ionic substitution method to create a new material and use this kind of descriptors, for example, the chemical stability and the band gap and the temperature. So if this kind of candidates can meet this requirement, so this candidate can be considered as a promising possible host. Okay, so he then use this method. He find a new green emitting phosphor structure lithium aluminate. So here I show some spectrum of these kind of new types of phosphors. Okay, so this is one of his work. Another one is done by Professor Song. He predicted the band gap and emission excitation energies by using the machine learning or some kind of data driving approaches. He built a prediction model, a prediction result based on various model by using the structure of parameters, and also it created the Pearson correction predicting the maxi for PSU. It's really complex, so I cannot understand typically. Okay, okay, another one, try to find some describers, for example, the band gap emission. So Professor Wang in the United States, they find the relation between the electron structure and the bandwidth. So calculate a lot of kind of materials, this electron structure of this kind of phosphor. We found that if we need another band emission, so the energy between these four bands, the upper two energy levels should be lighter than 1.01 electron volt. So it calculated more than 2,000 nitride. So find the kind of describers. So use this descriptor, he can find some new nitride phosphors with narrowband emission. So here let's use some data on this. Here choose this kind of this descriptor lighter than 0.1 electron volt. Okay. So another one is done by Professor John at Houston University. So he tried to find high efficiency and similarly robust phosphor. So he calculated the body temperature by using the machine learning, and also calculated the band gap. So and established the screen model based on the body temperature and all the band gap data. So for example, he calculates 2,500 compounds, the body temperature, and also using the body temperature and using the machine learning to get the body temperature data of this kind of compounds, and then establish the screen model based on band gap and the body temperature. Finally, they find a candidate, a new candidate is natrium barium borosite with even 2+. So in this phosphor, this phosphor has a high efficiency, and also the thermal quenching temperature is also very high. Okay. And okay, so also in Professor Wang's group, so predict the thermal quenching temperature of phosphorus. So based on the thermal quenching mechanism, so he produced built the prediction model of thermal quenching. So the error is quite small. So and then finally he obtained the phosphor design mapping by combining the band gap, average bond length, and electronic negativity and also thermal quenching energy. So use this model, it can find the phosphors with a high thermal quenching temperature. Okay. So last I show you some of the discovery, the new phosphor discovered in our lab. So first we cooperated with Professor Wang in the University of California in San Diego. So we discovered white emitting nitride phosphors. Okay, so using a model structure in the RISCD database, for example, barium, zinc, gallium, and sulfur oxide. So by substituting some kind of chemical units with aluminum nitride or silicon nitride, even the strontium elements, so we can create a new compound, strontium, aluminum, silicon oxide nitride, and with other model structures, we can produce this kind of material from strontium, aluminum, silicon with different strontium to silica or oxygen ratios. So, for example, in this table, so we found 3 new compounds, but we don't know if this candidate can be used as a phosphor host. So we calculate the chemical stability, the E-hole. So this E-hole is 0, and another 2 larger than 0. So this means that the thermostability of these 2 compounds is not so good. So we cannot synthesize these 2 types of oxide nitride compounds. So then here shows the band gap and also the right temperature. So we found that the band gap is suitable, and also the right temperature is quite high, 525 Kelvin. So this means that this first one should be the phosphor candidate, phosphor also. So then we doped this material with European 2+. So we found that this material emits a wide emission. So the emission spectrum is quite broad. So here we found that we can use this material to produce high color index white light. Okay, so this work is partnered with Project 1. So here shows some candidates. So we use the structural unit substitution in this model material. So here shows part of them. So another one that the first type work is try to find a host, is the compound. Another work is also cooperated with Project 1 in California, University of California. So we try to predict the European 2+ emission. So in the previous work, so the prediction of the European 2+ was also proposed, but the error is quite large. For example, more than 20 or 30 nanometers. So this is not so good to precisely determine the European 2+ emission. So in this work, we built a relation between the emission and the structural parameters by the harmonic Kovalov electrostatic parameterization model. So the emission energy between the 4,5 and 4,4 and the 5D energy, event energy is the emission energy of the European 2+. So this emission energy is determined by several parameters. For example, the band gap and the centroid shift, and also the crystal field stability. So we found that the centroid shift is determined by several parameters. For example, polarization ability, the band length between nearest ions and also the next nearest ions, and also the induction. And so these are 4 types of 4 parameters. The crystal field stability is determined by the angular parameters and also the band length between the ligand and also the activators. So by link the emission of the European 2+ with these 6 key parameters, structural parameters, so we can build the model. So here shows the model, the experimental data and technical data. So we using the machine learning with 223 nitride samples. This quite a little bit simple, but using oxide or other compound, this model maybe should be adjusted the model. So here we show that this predict emission, this expanded emission. We found that the error is about 7 nanometers, so it's quite small. So use this precise predict model to we predict 5 nitride phosphors with 8 near infrared emissions doped with European 2+. Here, lithium nitride, strontium emission, gallium nitride, and skin calcium emission, boron nitride, and something like that. So here, then do experiment, we find that actually all of these 4 samples have the NI emissions. So here, so the longest one is the strontium emission nitride, okay, around 800 or even can reach 830 nanometers with European 2+. So this is the longest emission found in the European 2+ emission. So also we use this strontium barium lithium silicon nitride. We can reduce the NI-LEDs. Actually, this under 200 milliampere. So the efficiency, the power is around 41 milliwatts. So it's higher than others reported in the reference. So another one is try to find the laser phosphors on the high power laser irradiation. So in order to understand why the phosphors, the efficiency of phosphors degrade under the high power laser irradiation, so we need to find some saturation mechanism. For example, in this the figure, we find that with different activators or different hosts, we find that the emission degradation is different on the high power laser irradiation. For some, the degradation is less, but for most cases, typically for the European doped samples, the degradation is larger. So we proposed energy transfer upconversion process to describe this decline of the emission efficiency, and use this model to repeating this experiment data with these equations, and actually we get the relative optical excitation quantity efficient. So we find that the larger the coefficient is larger, this means that the degradation or decline is great. Okay, and we link this kind of efficiency with the decay time. So we find the shorter decay time means the smaller quenching coefficient. This means that if we try to searching for laser phosphor, we need using actuators with very short decay time. This means the cerium 3+. Okay, so then next we try to find the ready emitting laser phosphors with less saturation. So here is the descriptor for searching this kind of ready emitting laser phosphor. For example, the emitter should be cerium 3+, means it's very short decay time. And for the host means that we should have a suitable band gap of 2.5 to 3.5 electron volt, and to obtain ready emission. So the lattice distortion should be larger, and the bond length should be shorter. So use these parameters. So we calculate these three data in the oxynitride nitrophosphate. For example, we calculate 114.5 and select 25 should be the candidate for the ready emitting phosphate, and using this one, select only one. This means the high pressure calcium silicon nitride. So this means these samples have very short bond length and higher distortion index. This means that if we dope this material with cerium 3+, this material should emit red color. Actually, it is. So then we synthesize this phosphors. We can see that here shows the particle, the particle color on the UV irradiation, and here shows the emission and excitation spectrum. So we found that this material emits at around 610 nanometers, and can be excited by the blue light. Actually, in the reference, so this type of calcium silicon nitride is only emitted orange colors, but only can be excited by the green color, like green light. But in our case, we can excite this material with blue light, so we quite interested in the laser lighting. So here shows some data of these materials. So the internal tolerance is around 14, and the absorption is around 18%. So actually, the external tolerance is around 32%. Okay. And use this material. So we try to use this material in the laser lighting. We find that under 10.9 watts per meter square. So we found that this phosphor can be survived. So the brightness around 187 lumen. Okay, so we use this method. We find interesting and rare phosphorus. So then also develop several types of orange red phosphorus. For example, the colorsome, selenium colorsome also is quite interesting orange molecular red phosphorus. Like aluminum doped random silicon nitride uses selenium 3+. And this means that we can produce warm white laser lighting using this random aluminum silicon nitride and random silicon nitride. Okay. So now also we produce some ceramics, for example, calcium aluminum nitride doped with 2+, so we can essentially use phosphor powder into dense ceramics, so they can survive on the higher power index, power density. Okay. So we also use our developed phosphorus to produce some products for the laser lighting, for example, hand lamps. So compared with the LED hand lamp, so LED laser guiding auto lighting so has very small glare, so it's quite safe for driver. Also, we developed some warm white laser lighting. So the lighting distance is around 600 meters. Okay? And also, we use the laser lighting to develop this kind of material used in the endoscopy. For example, we using the red and the green emission phosphors, we get a high color index lighting. So compared with sunlight, you see the color and also the color saturation, color purity is quite high. So this is quite interesting for the fiber embed endoscopy. So the last one, I should give you some ideas of the mechanoluminescence. So we try to searching this kind of material by the data driving method. For example, if we try to obtain the mechanoluminescence materials, usually we try to find this material in some piezoelectric materials. So this is one of the mechanisms for the mechanoluminescence. So you see that the local distribution is low. So this can produce some field, the local field, and this field can produce some electrons, and this electron can be combined with the activators. So this means I can generate the mechanoluminescence. So in this idea, so we try to find some new mechanoluminescent materials in anion mixed compound, for example, oxynitride, also sulfide, for example, this kind of junction sulfide oxide, and also some oxynitride for ytterbium dope on a European dope data sample. Here shows some PM and ML spectrum of these materials. So find that the ML is quite similar to the PL. This means that the luminescence is quite mechanical process quite similar. So this means that the luminescence from the doped ions. Okay. So we can also find some butterfly curves in this mixed anion mixed compound. This means that the mechanism for the luminescence is quite similar to the piezoelectric effect. Okay. So how to select, how to describing the unsymmetry or local symmetry. So we propose the distortion degree. So to describe this kind of local unsymmetry. So for example, we select the mixed ion, also single ion compound. We found that the D values in this the distortion degree is high for some kind of materials with central symmetry, and also quite some high for the non-central symmetry powders. And typically for the mixed ions, the value is quite high. But for the single anion compound, you can see even for the central symmetry, also the non-central, this can see that the value is quite smaller. So this means that we can find a strong mechanoluminescent material in the mixed ions is quite similar to our ideas. So here shows the ML intensity. So you can see the red one means the central symmetrical crystal structure. So here you see that some of them has no have no ML phenomenon, and for the crystals with non-central symmetry, so it means that most of them have the ML emissions. You can see. Okay. So we compare the yttrium oxide and with yttrium oxide, we can find that the yttrium oxide has a larger E value, a larger distortion degree. So you can see we can find the ML emissions in this compound, but there's no ML emission in yttrium oxide. Okay. Now, also, we calculate this kind of butterfly curve, so we can find that this quite obvious for yttrium oxide so far. Okay, so then we using this ML method, we try to develop some detectors. For example, we can detect the dynamic stress mapping on the complex mechanical stimuli. So we can see that we can calculate observe the structure of the stress mapping of the tail of the mouse. So can you see we can insert the record this kind of stress or even the mapping of the stress. Okay. So another one we use this ML method materials to detect the ultrasonic waves. Okay. You know, with in this case we use the ML converter, with ML film, and plus the lens, and are using the PMT detector, so we can detect the ultrasonic wave, given the frequency. Okay. But we needed to know the decay time is a key parameter for these kind of detectors. We need a very short decay time, so we can clearly distinguish the wave between this neighboring ones. Okay, so how to calculate the decay time of the ML materials? So it's blank. So then we built a method to calculate the ML decay time of fossil, also different fossil, and see we find a way to calculate this. So here shows some ML decay time of business dope, of plasma dope, even copper dope, even some rare dope materials. So to produce this kind of ultrasonic wave detector, we need material with very short decay time. So then we select the business of the central zinc oxide sulfide. So in this case, the decay time is only 39 micrometers, but for the magnesium 2 particle one, the decay time is 3.6 milliseconds. So it's quite long. So we can see that the wave cannot be clearly distinguished by using the magnesium doped phosphorus. But for the bismuth, we can clearly find the wave, ultrasonic wave. So the limit of this using the strontium zinc oxide doped with bismuth, the wavelength frequency around 25 kilohertz. So this is our by using the ML method to detect this high frequency ultrasonic wave. Okay. So finally, I will mark of this my talk. So you know, the descriptor are the key for data driving design of phosphor materials, and also the strong correction parameters of phosphor needed to be found. And the reliable and complex experimental data and computation data are really highly required. Okay. Finally, I should give my thanks to my group members and also the financial support. I'm sorry, so the time is over. I'm sorry. So thank you for your attention.
Okay, thank you very much for your interesting and excellent talk. Okay, so I hope your new materials more widely applicable. Okay.
Thank you. Thank you.
Okay, so have a question or comment?
Professor, thank you for your talk. It's very good work. And I want to know if combined with the machine learning, whether we can further to get more data input and get more the performance, the properties of the materials discovered. Because now I think the AI for science is really popular. I'm not sure whether that one can combine with the data-driven process. Yeah, thank you.
Yes, very good question. So actually, in my remarks, I said that we needed some reliable and complete experiment data in computing data for the data for machine learning. Actually, in this case, in typically the phosphor field, so the kind of data are quite less. So we use a very small number of data. We should to build a very reliable machine learning model to build a relation between the structural parameters with the luminescent property. So this is quite important in this kind of field, AI phosphorus. So yes, so we cooperated with other professors in some kind of information, College of Information Technologies and something like that. So this is not our, we're not good at this kind of, but we cooperate with others. So actually the data quite important, usually Bible data.
Yeah, thank you.
Okay, so it's not so much time, so we move to next talk. Thank you again to Professor Jie.
Thank you.
Can be seen.
Hello everyone, I have sent my video. I recorded the video.
Oh, hello, Professor Zhao. You can hear?
Hello. Yeah, I can hear.
Okay, thank you for your waiting. So please start. Okay. So sound cannot. Sorry, cannot hear.
Hello everyone, my name is Jing Zhao from University of Science and Technology Beijing. My topic includes these 5 parts. The first one is the background. As we all know that hybrid metal halides has lots of applications. For example, these land-based iodides has shown very high sunlight conversion efficiency, and it can be used in solar cells. And after that, in 2014, this low-dimensional metal halide has been found showing very broad peak emission for one single compound like this compound. It can give single component white light emission, and this has drawn lots of attention, and lots of compounds were reported showing very high efficiency, and I also did lots of work in this area, and I found that in this zero-dimensional compound, it shows tunable peak emission by tuning the length and thin in this compound. We can change the color also by changing the exciting wavelength. And we also found that this kind of compound can be designed to be non-stereosymmetric and showing very high error and linear optical properties, and also the photoluminescence properties. And here I wanted to introduce something new, and we have found this by accident. And we found this room temperature phosphorus materials, which could respond to stimuli such as force, heat, light, electric field, etc., and which have drawn increasing attention for their broad application prospects, especially in the fields of anti-counterfeiting, sensors, and data storage, and so on. And the mechanism for this stimulus responsive room temperature phosphorus can be divided into 2 main groups. For the single component compound, which only have one kind of molecular or one type of element, that the stimulus to the environment is due to the structure or packing or conformation change. But for the multi-component compounds, which may contain 2 different molecules or different elements or atoms, which showing this change of properties is due to the change of the oxygen around this atoms, and also the A and B distance also that may have the same reason with a single component. For example, the change of the structure of these 2, or the packing, or the a big conformation change. And the mechanical response luminescence includes 2 parts. The first one is force, which force represents an easily obtainable external stimulus. You can get this force by hand, and the phosphorescence and fluorescence serves as a sensitive visible response signal. You can detect it by naked eyes. But there are still some challenges in this kind of compounds, because current MRL materials are mainly organic compounds, metal organic complexes, liquid crystals, very limited organic, inorganic hybrid metal halides. As far as I know, my group is the first one to report this inorganic hybrid metal halides with such MRL properties. And there is a scarcity of materials with high stress response sensitivity and contrast, and a demand for reversible cycling performance in such materials in practical applications. And in the literature, there are some types of compounds showing such properties that typically are metal organic complexes. For example, these gold-based compounds showing very obvious change to pressure after it is grounded. You can see here its color changed from this blue one to this yellow, yellow, and after fully grinding it becomes yellow, and after it was treated with a solution, this solution, you can see here the solution, it becomes blue again, and the mechanism was investigated by X-ray diffraction. You can see here from X-ray diffraction, we can see here treated with this liquid, the compound, the peak of the X-ray diffraction weakened, and also the ground sample also shows broadening and weakening of this peak. So the mechanism is the transformation from the crystal to amorphous phase for this type of compound. And also, this compound also based on gold. It is non-emissive on the UV for the crystals obtained, but after scratching, it becomes emissive of green light. And after heating at 80 degrees C, you can see here the emissive peak weakened, and after heating it at higher temperature, the peak was fully quenched. And after cooling to room temperature and scratching it again, it becomes green emissive again. And the mechanism for this type of change is due to the molecular motion, which is generated when subjected to the force. So to the force, that means the force induced the molecular motion and the conformation change of this kind of organic part. And also in this type of compounds, they obtained a series of organic compounds that 6 new compounds was obtained, and here it shows the crystals. And also the crystals in the UV light. So under the UV light, you can see here these 4 compounds are non-emissive, but after grinding, it becomes emissive with green and yellow light, and the efficiency is relatively high. And this mechanism for this change is the grinding changes the molecular conformation. So we know something about this change, the reason for this change, and when we design new compounds, we found these two new compounds, and we solved the crystal structures. These are totally new. And for the organic part, we chose this one. In this compound, all the carbon-carbon bonds are single, and it has lead trimer and zinc tetragonal, and this zinc can be changed to cadmium. These two compounds are isostructure. Here are the crystal we've obtained, and the crystal of these two compounds are very alike. Here showing the EMS is the element distribution of in these two compounds. This is the SEM figure of these two compounds. And here you can see after grinding, the non-emissive crystals become emissive. You can observe green light, and after heating, the green light becomes dark. And when it is emissive for the zinc-based compound, it has 3.9% of PRQY, and for the cadmium-based compound, it has PRQY of 5.7, and after as a PR quenched, when you grinding it again, it becomes green emissive again. And the green emission originated from this land tremor, because the similar PR property has reported for other compounds that didn't has the mantle of zinc and cadmium. And here are the crystal in the UV light. You can see it non-emissive, and after grinding, it becomes green emissive. And after storage in air for 1 week or 2 hours at 100 degrees C, you can see here the PR quenched. So we measured all the samples PR properties, so we give them different names. For the fresh powder that is freshly ground, that one is for this fresh sample, the green light here, it is emissive. And after repeatedly the black line repeatedly grounded it, you can see here a blue shift. Small group blue shift was observed, and also we measured the decay time. The PR decay curve indicates that the emitting centers remain unchanged. For the repeatedly ground sample and freshly ground sample, the same emitting centers was observed. And also, we did the powder X-ray diffraction. We found that for the simulated peak, you can see here, and the freshly ground sample here, and after heating, the PR quenched, but it becomes the crystalline properties becomes better. So from XRD, no phase transition was observed together. This was further confirmed by infrared and Raman property measurements. And we also found the grounded sample becomes more amorphous. For the peak becomes lower. And here we did the solid state NMR. The broadening of this peak here, this peak shows here, indicates that the chemical environment around the organics changed after grinding. After grinding, is changed. And we also did in situ high temperature PR on the hydrostatic pressure. We can see here with the pressure increases, no matter it is the PR quenched sample or freshly ground PR emissive sample, its PR increased when the pressure increased. And here shows that for all the two compounds, compound 1 and compound 2, no matter it starts with non-emissive one and emissive one, the final samples are very emissive. And we also found a peak shift when the pressure increased, the peak shift to the blue area. And we also did the temperature-dependent pH of both compounds, and we found that the peak moved when it is heated from 18 Kelvin to room temperature and higher temperature. We found a move of the peak, and we assumed that the peak can be the peak are attributed to two emissive centers that is due to STE1 and STE2 that is originated from the self-trapped excitons levels with different energies that gives the broad peak. And we also know that from our previous characterization that this emissive and non-emissive change is a combination of the organic molecular rearrangement and the crystalline change of this compound. And after grinding, the organic conformation changed. This gate, this tunnel or gate can be open or be closed. So pressure and grinding can change the path to be closed, or it can be open to showing the gray emission. And here we did some application for this zinc-based compound. We made a composite film with this compound and PDMS on an aluminum foam, and handwriting this USTB, and this can be erased by heating, and it can be rewritten again. And it also can be used for damaging detection in the car collision, and also can be stress recording if there is a stress in this car, and it can be recorded. And after repeatedly grinding and heating the sample, we found that this gray emissive and quenched property can be cycled for many times, and we also found that after cycling, the intensity of this emission not decreased at all. That is the first part of the two compounds we have obtained showing such properties. And fortunately, we also obtained another compound showing such very interesting multi-stimuli responsive emission. And in this is also a new compound, which we synthesized that, and also we solved the structure. We found that there is antimony chloride dimer, and also this compound, this organic compound. And after we obtained this compound, we found it is very interesting. For the crystal in this UV light of 365 nanometers, it shows blue emission, and after smashing, it also shows blue emission. And after grinding, the blue emission becomes this orange, and the PRQI is very high. And after heating or storing in air for a few days, it becomes blue again, and the PRQI is still very high. And after we dissolve this into the solvent, and we obtained to the blue emissive crystal again, and we mirrored the PL of these compounds, of these different color emission compounds. We found that on the 365 nanometer excitation, this compound, this double compound means this double compound, this orange emissive compound, we call it double peak compound because it shows double peak. But for the blue emissive compound, no matter we use what kind of excitation wavelength, it only shows one peak. So we called it single peak compound. So after we obtained these two kind of emission, we also tried to stimulate it with different in many different ways. For the crystal we obtained, it showing very good blue emission, and after treated it with hydrochloric acid at room temperature, we found it turns to this pink or orange emission, and after heating and treated with water, it becomes blue again. And after hydrochloric acid treating, we found that it becomes orange emissive again. So it is a solvent stimulated luminescence in this compound. So this compound is very interesting. It can be used to change its color on the mechanical stimuli, also the solvent stimuli. And we also investigated the mechanism in detail. Also, we did a solid state NMR. We found that for the samples of the single peak and double peak, they both shows very alike NMR, but a very small difference was observed. This means the organic part has small difference. And the Raman shift has no obvious change was observed, and we also simulated the X-ray diffraction, which shows that no change, no phase change was observed. So we concluded that the chemical environment surrounding the organic motif has changed. The refined results unequivocally validate the conformity of the crystal structure. So crystal structure no change. We also give a very large PXID of these obtained compounds. You can see here, this is a simulated peak, and this is the fully grounded peak. We find that the fully grounded peak, no amorphous was observed. So no phase transition observed. The grounded sample didn't become more amorphous. So the reason for this, we need to further investigate, and we found that low temperature, we did different temperature. We collected the PR at different temperature and different pressure. We found with pressure increasing, this peak here, the low energy peak increases, and after the pressure increased to a certain level, it decreases. And we also found here, when the temperature increased, with the temperature increased, no obvious change of the blue emissive peak was observed, other than the increase of the peak, increase of this peak. We also found for the single peak sample, but when it is excited with this kind of wavelength, we find that it shows two peaks emission at room temperature. At room temperature, two peaks were observed. Two peaks was observed at a lower temperature. At high temperature, it is just a single peak, but at lower temperature, it becomes double peak. So the low temperature and the high pressure spectrum of sample S both exhibit ideal double peaks. And also from the X-ray diffraction, we found that no obvious phase transition was observed when the sample is suffered from high pressure. And we can see here we suggested a mechanism that the blue emission and the double peak emission has different excitation wavelengths. For the blue emission, it can be excited with the high energy, and also temperature can change the color. It will change the color from the single peak one to this double peak one this double peak one. For this, if the temperature is lower, because the high temperature will affect the emission of this compound. And we also investigated the structure difference of the two compounds. For the compound at low temperature, it shows double peak, and we calculated the distortion of the angle, and found that the angle distortion is higher, but no obvious distortion of the distance, and the bound distance didn't change here, and the averaging bound angle, averaging bound length, and the didn't change here. This didn't change. Only this angle distortion changed obviously. And we also simulated the structures at different pressures, and we found that when the pressure increased, the distortion becomes extremely larger. The emergency of the double peak emission is related to angle distortion of the inorganic pyramids induced by the organic motif. And here are the application for this compound. It can be used as a smart sensor. It can be used to sense water and hydrochloric acid. Here it shows the different color. It shows blue in water, and shows orange in hydrochloric acid, and also it shows different color on the different temperatures. At lower temperature, it shows double peak. Here you can observe near white light emission, but at room temperature it shows only the blue peak emission. And after heating and cooling, the temperature, the pure intensity are stable. No obvious change was observed. No decrease was observed. So this compound can be used as temperature detection and anti-counterfeiting applications. So here, as a conclusion, the synthesis of new compounds exhibiting mechanical response luminescence represents potential candidates for applications in intelligent sensing and stress monitoring, and established the structural property relationships and elucidated the mechanisms of MRL materials. Finally, as acknowledgement, so thanks for the National Natural Science Foundation of China for funding, and Professor Quanling Liu, Zhongnan Guo, Yonggang Wang, Zhi Guoxia, and Jin Song for their help to conduct all the works. Thanks so much for your attention.
Okay, thank you very much for your interesting talk. Okay, is there any comment or questions? So I have one question. So in your materials, the temperature, depending on temperature, the properties decreased.
Yes.
How is the time stability?
The stability of the compound is very stable in the hybrid metal halide. It will pause at around 200 degrees C.
So difficult. Okay, if not, then move to the next session. Okay, thank you again.
Okay.
It's very difficult. Okay, so today's last talk will be done by plenary speaker. Okay. Professor Teng. Professor Teng prepared. You are ready? Not yet. Professor Teng.
Hello. Can you hear me?
Hello. Yeah. It's okay.
Can you hear me?
Yeah.
Yeah.
We can hear. Okay, please.
Yeah.
Please start. Okay.
Okay. Can you see my video?
Yes. No problem. Only your photo, your image cannot see.
Yeah, I cannot see my image. Where is the image?
你是说电脑的屏幕还是？
不是那个我自己的那个 Where is it? Okay, never mind. Wait.
要不点一下那个退出的。
Okay, let me. Okay, so you can see my PPT, right?
Okay, so go ahead.
Okay, then let me start. So, good afternoon. First of all, I would like to thank the organizer to give me this opportunity to present some of our recent research results. So the title of my presentation is Class Luminescence, a conceptually new luminescence system emerging from non-luminescent macromolecules. So basically, here I'm talking about the luminescence system as a whole, but this whole is composed of non-emissive molecules. So that's the parts. So in some sense, I'm talking about a system in which the whole is much bigger than the sum of its individual parts. So here, let me talk about a little bit about the research philosophy. Okay, so currently, the scientific research is guided by this reductionism in terms of philosophy. So what is reductionism? It says that a whole is nothing, but the sum is individual parts. Or simply put, 1 + 1 equals to 2. Okay, but here there's another philosophy is holism. Holism is different from reductionism. It says that all the properties of a given system cannot be determined or explained by its component parts alone. So in other words, according to holism, 1 + 1 is not equal to 2. Sometimes 1 + 1 is smaller than 2, and sometimes 1 + 1 is larger than 2. Okay, so it further says that the system as a whole determines in an important way how the parts behave. Okay, so in reductionism, it basically says that the parts determine how the whole will behave. But holism says otherwise. Okay, so the whole will determine how the parts will behave. Let me give you 2 examples. Okay, so as I just mentioned, the research philosophy basically in the past, several hundred years are guided by reductionism. Why? Because in the early time of the Industrial Revolution, people were trying to make a machine. So they figured out that if you want to make a good machine, you make good parts. Then you put the parts together, you get a machine. Okay? So basically a machine as a whole is the sum of its individual parts. Okay? Okay. Let me see. It looks like you are sharing video as well. Can you see my PPT? Hello? See. Hello? Can you hear me?
Yeah, we can hear you. But
and you can also see my PPT, right?
Yeah, but the PPT is stuck. They are not moving.
Stuck?
Yeah. So can you change your PPT? Okay. Yeah. Oh, okay.
No, you can. But you can see it now. Okay. Okay, great. Okay.
No.
So it's okay now.
Can you show the next slide? No, that's the previous one. Oh yeah, now it's okay.
And how about this picture here? Yes or no? Hello? Not here. Hello?
Okay, now it's okay. No, now it's not okay now. Previous one is okay. Yeah, the next slide, please.
It's okay now?
No.
Can you see the machine?
No. Yeah, this is the machine. Reduction.
Okay,
Reduction.
great.
Yeah.
Okay. Let me continue. So, it's here. Oh, okay. It's okay now?
Yeah, now I see your face now. Yeah.
Oh, you can see, but I cannot see myself. Okay, anyway. Okay, yeah. So, basically I was talking about reductionism, okay? Because the great success in this mechanical reductionism, so people, were basically expanding this reductionism to almost everything, okay? Say, for example, I'm a chemist, okay? When you do chemical research, basically you reduce everything to the molecular level, okay? And reductionism is telling us if you understand the molecules, you will understand the materials composed of the molecular species. However, as I just mentioned, there's another philosophy, that's holism. And holism is saying that actually, the whole can be bigger or smaller than the sum of its parts. Okay, so for example, the brain is actually not the sum of its individual parts. Okay, if you think about it, the brain, if you reduce to the molecular level, that would be DNA, RNA, proteins, carbohydrates, amino acids, all these things. Okay, and if you think about it, actually, we are not so much different from each other in terms at the molecular level. However, as a whole, as a brain, everybody is thinking differently. Okay, so in the beginning of this year, I published a perspective in JAX. Okay, so in that perspective, I talk about how to view the living aggregates. So basically, how to view the life from a holistic perspective. Okay, but of course today I will not talk about life science. Today I will talk about the physical science. So before I talk about that, okay, I share with you a paper published by Professor Anderson in 1972 in Science. So in that paper, they said the behavior of large and complex aggregates of elemental particles is not to be understood in terms of a simple exploration of the properties of a few particles. Because he's a physicist, so he thinks everything, if you reduce, you go to particle level, okay? And as I mentioned, for chemists or for material scientists, we reduce everything to the molecular level, okay? So here, basically, he's trying to tell us that, you cannot do the following, okay? You understand the molecular properties, then you just do a simple exploration, then you understand the behavior of the molecular aggregates. Okay. It further says that at each level of complexity, entirely new properties appear. You just think about it. Okay. For protein, the protein is a dead molecule. When you form aggregate, you have alpha, helix, beta sheet. You have a secondary structure, tertiary structure. You go up, you have a cell, you have a tissue, you have an organ, all kinds. At each level is complexity, you get new properties. And so his conclusion is that the whole becomes not only more than, but very different from the sum of its parts. Okay, so that's what I'm going to talk about today. Now, let me go back to physical science. So in physical science, because the substrate is complex, it's too complicated. So people reduce it to molecular level. Why? Because they believe, okay, if a molecule has a certain property, its aggregate should have that property. So the relationship is 1 to 1, okay? So you understand the molecules, you will understand the aggregate of the molecule species. So this is called molecularism, okay? Molecule determines everything, or the parts determine the whole. However, there are many opposite examples. So here I share 2 examples with you, which are against this molecularism. The first one is aggregation caused quenching. What does this mean? This means a molecule, can be highly emissive in dilute solution. But when you form an aggregate, the emission is gone. Okay? So here the relationship is 1 to 1 in the molecularism system. Here this is 1 to 0. So from something to nothing. Okay? So obviously this is against the molecularism, against the reductionism. As another example is aggregation-induced emission. This is the opposite of ACQ. So in this case, the molecule is not emissive, but its aggregate can be highly luminescent. Okay, so the relationship is 0 to 1. Again, obviously, this is against the molecularism, because the molecularism tells you if the molecule has a lot of property, its aggregate will have a lot of property. But in this case, the molecule does not have a lot of property, but its aggregate, does have the property. Okay, so in this case, I propose this aggregatism. Okay, so it's the aggregate that determines the property of the materials. Okay, so now let me use 2 videos to tell you the difference between ACQ and AIE, although both are anti-molecularism. You can see for ACQ, okay, okay, it's running too fast. Okay, initially the molecule is emissive, but if you add water to induce the formation by aggregate, the emission is gone. For the AIE system, you can see the molecule is not emissive, but if you add water to induce the formation by aggregate, the emission appears. Okay, so these two are totally opposite, but both are anti-molecularism. Now, let me use this video to tell you how the AIE is functioning. So, a molecule normally is in the ground state. If you excite it, it will go to excited state. We know that the exciton is not stable. It must come back, okay? So here, let's assume this waterfall is light beam, okay? So if it goes back to the ground state through this pathway, you get light emission. So that's radiative decay. However, there's another pathway for the exciton to go back to the ground state. In this case, the energy is converted to mechanical energy, to the molecular motion, okay? So this is a non-radiative decay. Now, let me use that molecule to tell you how the molecule is functioning. You see, this is a molecule named tetraphenylethylamine, in short, TPE. Okay. Now, this molecule, if excited, it will, oh, it shouldn't rotate. But anyway, this video doesn't work. Okay. Anyway, the benzene will rotate, and the double bond actually is open, so you undergo this cis transition. Okay. So what does that mean? In the single molecule species, upon excitation, it will come back to this pathway because the molecular motion will consume the energy. So the molecular motion basically converts the photonic energy to thermal energy. So that's why the single molecule species is not emissive. However, when the molecules are aggregated, okay, now the molecular motion is restricted. You cannot, the molecule cannot move anymore. So that means you block this pathway, the aggregate will come back to this radiative decay channel. So that's why you see the aggregate is very, very emissive. So here the working mechanism is a restriction of intramolecular motion, or RAM. Okay, so the AIE, in some sense, is a very simple experimental phenomenon. Okay, the molecular species, the diluted solution is not emissive, but if I add water to induce the formation of aggregate, the emission appears. Okay, so in some sense, it's a very simple, experimental observation. But if you think deeply, what does this mean? This means, okay, you can make something impossible at the molecular level possible by aggregate formation. You don't need to change the molecular structure. You just make the molecule perform an aggregate, then you can make the impossible possible. Okay, so from that, we try to develop this kind of system. Okay, so for example, we have this organic room temperature phosphorescence. Many organic molecules cannot emit phosphorescence at room temperature in diluted solution, but the aggregate can emit a very efficient, RTP. Okay, so we have many of these kind of systems, but today, of course, I will not talk about this all these cases. Okay, today I just talk about one system, that's cluster luminescence. Okay, so cluster luminescence means that luminescence is from the clusters, from the clustering, aggregate. So first of all, let me share with you what is cluster. According to the Cambridge Dictionary, cluster is simply defined as a group of similar things growing or held together. So anything, if you put them together, that's a cluster. Okay. Now let me give you an example, a very famous example of cluster. That's water. We know that the water can form dimer, trimer, tetramer, heptamer, hexamer, all kinds. Okay. Actually, the type of water we drink usually has water clusters with around 14 to 15 molecules. Okay, so water is very simple, but actually it has all kinds of clusters. Okay, now, so let me talk about the cluster luminescence. So first of all, let me talk about background and motivation, why we do this kind of research. So we know that luminescence has been studied for thousands of years. Okay, now there are many, many different kinds of luminescent materials. For organic luminophores, basically the design principle is the following. You need to have extended pi electron conjugation. Say, for example, for a simple benzene, the emission is at 290 nanometers, very weak. But if you put more and more benzenes together, the emission will redshift and the emission will become stronger. Now, another approach is to introduce donor acceptor pairs, DA pairs. Okay. Say, for example, this is the TPE. TPE emission is kind of blue. But if you put an acceptor here, instantly the emission will redshift by 100 nanometers. And if you put a donor here, you have a DA system, or you have more DA pairs, the emission will all the way redshift. Okay. In this case, we call this as electronic conjugation. But however, here I want to emphasize that the conjugation here is through bond, through chemical bond. Okay. So, this pi electron delocalization is all through chemical bond. Okay, this is a TBC. Remember, this is TBC. Now, okay, we eat starch, we wear cellulose. Okay, this kind of molecule species, they have low pi electron conjugation. They even don't have pi electrons. Of course, they don't have d pi A structure motif. So the question here is, if you excite these kind of molecules, do you think they will emit light? Okay, so this is the experimental data. Okay, you can see now we can dissolve starch and cellulose. We can make a very dilute solution of this kind of natural products. Okay, now if you excite it with UV light, you get nothing. Okay, so the molecule species are not emissive. So, as I just mentioned, the modern organic optoelectronics theory is telling you that if you want to make an organic molecule to emit light, you should have an extended pi conjugation. You can have DA, structure motif, and this kind of system, don't have pi electron conjugation. They don't have a PA, so that's why the molecule species are not emissive. However, when the molecules are aggregated, okay, now if you excite it, you get a visible emission. Okay, you can see this is the aggregate, this is the clusters of the starch, and this clusters of cellulose. Okay, you may think that this probably is accidental just for these two, natural products. Okay, let me give you more examples. You can see this is the rice you eat. Okay, you can see actually it can emit light. Okay, in a solid state, and the protein can emit light, and actually the arginine, this is the seagrass, okay, can also emit light. Okay. Now, so basically, what I'm trying to tell today is that the molecule species are not emissive, but when they are aggregated, when they are clustered together, they will start to emit light. So we call this as a clusteration triggered emission, or CTE. Okay, so let me summarize the characteristics of the cluster luminescence. So the first one, in terms of structure, okay, they don't have an extended pi electron to bond conjugation. You can see the first example is water. Okay, you have this kind of small molecules. Okay, they are not conjugated. You have this linear polymer like this polyethylene glycol. It's not a conjugated polymer. Okay, this is linear polymer. This is a hyperbonded polymer, and this is the dendrimer. None of this, okay, has extended pi electron to bond conjugation. This is the first feature, structure feature. And second feature is that these kind of molecules contain a lot of hydrogen atoms like the oxygen, nitrogen, sulfur, phosphorus, silicon. But if you think about it, all these items are all these elements are in the right side of the periodic table of the elements. Okay, so they are electron rich, they have lone pairs. And also think about it, these are the hydrogen atoms abundant inside our body in the biological systems. Another unique feature is that, normally for conventional aromatic compounds, okay, their absorption spectrum and excitation spectrum are similar, sometimes are identical. But for this kind of system, you can see the absorption spectrum, the excitation spectrums are very different. They don't match at all. And another very interesting, characteristic is that, if you change the excitation wavelength, you are going to change the color of the emission. Remember, for conventional aromatic compounds, if you change the excitation wavelength, you are not going to change the color of the emission. You only change the intensity. You don't change the color of the emission according to Kasha's rule. Okay, but you can see for this arginate, this is a natural polymer. Okay, now if you use UV to excite, you get a blue emission. If you use blue to excite, you get a green emission. If you use green to excite, you get a red emission. Okay, so this is the natural polymer. Let me give you an example of a synthetic polymer. You can see this is synthetic polymer. When the current reaches very low, you don't see the emission because the molecule species is not luminescent. But if you increase the current region, they start to emit light. You can see the film is very emissive. Again, if you use UV to excite, you get a blue emission. If you use blue excite, you get a green emission. If you use yellow to excite, you get a red emission. Okay, so this is a kind of interesting. It's wavelength excitation, wavelength dependent. And another feature is that normally this PL spectrum is very broad and has multi-peaks. Okay, and you can see very interestingly, if you turn off the light, okay, you see the arginate actually will emit phosphorescence at room temperature. You can see that's the phosphorescence. So again, as I told you, for pure organic compounds, seldom you get very efficient room temperature phosphorescence. But for this natural product, you can see the aggregate, the clusters can be, can emit, phosphorescence at room temperature. I'll give you another example. You can see this is a very simple, molecule. Okay, again, the excitation, the cluster luminescence is a wavelength, excitation wavelength dependent. And if we see the lifetime here, you can see these are all phosphorescence at room temperature. Okay, now basically the most important question here is how it works. Okay, so in the following, I will use two examples to discuss with you how this cluster luminescence is working. Before that, I will again discuss about this through bond conjugation. You can see that for this molecule, the pi electrons can flow along the chemical bond. Okay, so the pi electron is delocalized, along the non-conjugated, unsaturated, okay, chemical bonds. However, as another system, you can see these two benzene rings are not, conjugated through this chemical bond because you have two saturated methyl group here. So this is so-called through space conjugation. This part is through bond conjugation, but this part is through space conjugation. Okay, so let me give you more examples. So you can see this molecule, these three benzene rings are conjugated through chemical bond. Okay, you can see the p orbitals are, are close to each other, so the pi electron will delocalize along these three benzene rings. But if we see these two benzene rings, actually the electronic conjugation is disrupted by this saturated carbon here. Okay, but however, you have this so-called homo conjugation here because you have p orbital here, you have p orbital here. These two orbitals can, can have overlap. When it has overlap, that's a so-called homo conjugation. I call this as a through space conjugation. Okay, now let me give you an example. You can see this molecule, if we dissolve in dilute solution, if we excite it, no emission because it's not conjugated. However, when you form crystal, Okay, now if excited, you can see the crystal is kind of emissive. Why? Because this kind of homoconjugation, this kind of through space, interaction is rigidified, is stabilized in the solid state, in the aggregate state, in the clusters of this, this oligomeric species. Okay, so here I propose this through space interaction. If you have a pi electron or you have a lone pair, even you don't have a chemical bond to enable the through bond conjugation, you can still have through space conjugation. Or you have a donor and acceptor, if you are not, if they are separated by saturated metal groups, never mind, you can have through space charge transfer. Okay, now let me discuss two systems. One is a aromatic system, but a non-TBC. So that means, let me give you an example. You can see this is a petrophenol, I think, okay? So here you can see this is a saturated. It's not a double bond. This is a saturated here. So these four benzene rings actually are not conjugated through chemical bond. So in dilute solution, if you excite it, you only get isolated benzene, benzene ring emission. 290, if you remember in the beginning, I told you single benzene ring we emit at 290, very weak. Okay, but however, if I add water to induce the formation of the aggregate, you can see you got blue emission in the visible range. Okay, so you can see the emission is increased upon the formation of the aggregate. You can see this is the aggregate of this single bond TPE. Okay, the reason actually is very easy to understand. For this molecule in the dilute solution, theoretically you do have this homoconjugation, this through space conjugation. However, the vigorous molecular motion, okay, in the solution state, we easily destroy this kind of conjugation because this kind of conjugation is not very, very strong. This kind of electronic interaction is non-covalent, it's not very strong. So the molecular motion will easily destroy it. So that's why you only get a benzene emission. However, when you cluster together, this kind of homoconjugation is stabilized. Okay, so again, if you still remember, I talked about restriction of intermolecular motion. So here, in the solid state, the RM mechanism, okay, rigidify the structure and make this kind of non-conjugated molecular species, okay, emissive, because they form clusters. In the clusters, you have all this kind of homoconjugation to generate, chromophore to emit light. Okay, so, I talked about this system when discussing this through space conjugation. Now, in the previous case, for single bond TPE, basically that's the case. Okay, if we put a two benzene here, not with a single bond TPE, you have this kind of homoconjugation. And actually, polystyrene can emit light. Okay, why? Because you also have this kind of a two-space conjugation. But of course, you need to have a isotactic polystyrene. If you excite it, it can emit light. Okay, so this actually is very general. Now, since we understand it's kind of a two-space electronic interaction, so we made this, triphenylmethane. Okay, now if you put a donor group here, you are going to enrich the electron density here. You enhance the electron density here. So you put an amino group here, so you can see when you put a donor here, you redshift the emission, you increase the quantum yield. But if you use the electron withdrawing group to take the electron out, so here you don't have a two space electron because you don't have electrons. Okay, so even in a solid state, you don't have you don't see net emission because you basically weaken the through space electronic conjugation. Okay, so we can put all different things together. You can see this is the TSC part, through space conjugation, and this is through space charge transfer, and this is room temperature phosphorescence because it's kind of heavy atoms. Okay, will give you RTP. Okay, you can see when you excite, you get a TSC emission, you get a charge transfer emission, and if you delay, you get a RTP. Okay, so that's the case. When you excite, you can have this TSC emission that's in the blue region, and you have this charge transfer emission that's kind of green, and if you have a phosphorescence, that's kind of yellow. Okay, so you put all this together, is kind of a white emission. Now this is the first synthetic polymer, okay, made by human being. Now, if you do modification of this kind of system, although of course it's not conjugated, but if you put one benzene here, you can see it start to emit light. And if you put an electron donating group here, it also helps. Okay, and you go further and further. Eventually, you have a more through space conjugation. You have an electron donating group here, so you can get a yellow emission with high efficiency, almost 50% quantum yield. Okay, so that's the basically schematic illustration. If you don't have, you only have isolated benzene, that's the isolated phenolic emission, very blue, very weak. But if you put, you have this electron donating group here, so you have this homoconjugation, so you get this, through space, locally excited, okay, species and not responsible for the carcinolominescence. But if you put a donor accept here, you get a charge transfer, through space charge transfer, so the emission will further redshift. Okay, now let's talk about the non-aromatic system. Basically no aromatic ring at all. Of course, there are many such systems. Here I use the simplest example. That's the simplest amino acid, adenine. Okay, so the adenine, of course, in the solution state, if you excite it, no emission. But amino acids, many amino acids can easily form crystals. If you excite the crystal, you see blue emission. Okay, now if you ionize the structure, the crystal structure, you will know that there's a lot of hydrogen bond. This is an intramolecular hydrogen bond, intermolecular hydrogen bond. This kind of hydrogen bond will stabilize the structure, will rigidify the structure. Okay, so that this kind of through space interaction will be stabilized. Okay, you can see that's the intramolecular N-pi interaction. So this is the lone pair of nitrogen. This is the pi electron of a carbonyl. Okay, you also have space N interaction. You have all this kind of interaction. As I mentioned, this kind of interaction in the solution state can be easily destroyed, but in the crystalline state, okay, in the crystalline state, this is stabilized. Okay, so this will form the cluster luminescent to emit light. Okay, you can see this is PEG, polyethylene glycol. You can see that's the structure. And if you excite it, it can emit light. Okay, and this is because of time limitation, I will go a little bit faster. Okay, so you can see this is the through space N interaction. Okay, that will generate chromophore to emit light. And actually, the N-pi interaction is well known. You can see for adenine, the lone pair will form the through bond N-pi interaction. But for our system, we don't have a chemical bond. This is through space N-pi interaction. Okay, and also the nitrogen is donor and the carbon is acceptor. You got this DA network. But of course, in the polymer, it's amorphous. You got the different size of the clusters. So that is why when you change the excitation wavelengths, you got a different emission color because the different size of the clusters will emit different color. Okay. Okay, so you can see these are all non-conjugated polymers without the aromatic rings, and in the aggregation state, they emit carcinolominescence. Okay, and we try to, of course, manipulate. You can see if we change the carbon to oxygen, to nitrogen, and to sulfur, the emission all the way redshift. You can see that's the case. When you have a carbon, that's the kind of a blue emission. When you have a nitrogen, okay, when you have oxygen, you got the sky blue. If you get nitrogen, you get a yellow. If you have sulfur, you get a red. Okay, so you can change the emission color by simply change the hydrogen atoms. Okay, so now we have a system can have a quantum yield up to 100% with a very narrow emission, and we can change the color of the emission from blue all the way to red. Okay, let me summarize. So basically today, I talked about this kind of a non-conjugated system, okay, but rich in heteroatoms. And these kind of molecular species are not emissive, but when they form clusters, okay, depends on the size of the cluster, the gap will change, will become smaller and smaller, and eventually you get this valence band and the conduction band, okay? So here you get a network of DA, structures, and the different size will give you different color emission. And if you want to read more, we have published some review articles in Materials Today and Jack's Gold. You can probably read it to get an idea of these kind of systems. So basically, what I'm trying to conclude is that the cluster luminescence is from molecules, but the molecule is not emissive. Okay, so the aggregate can be beyond the molecules. So here is against reductionism. Reductionism means the molecule must be emissive, but here we have non-emissive molecules, but we can get a very, very emissive, clusters. Okay, so this is a very exciting area for research because for conventional system, they are aromatic compounds. So when you make it, you pollute, you cause environmental pollution. Of course, you need to spend money to make it, and it's toxic. And it's very, very difficult to decompose. After you use it, it takes years to decompose. Okay, especially for polymers. Okay, you have this so-called white, plastic pollution. But for our system, basically, these are from grasses, from trees, from vegetables, from from natural products. So first of all, it's very cheap, inexpensive, and it's biodegradable, biocompatible. So you can do a lot of things. Okay, and theoretically, it's even more interesting because now we have to think about something different from the traditional, or the modern optoelectronics theory. So to promote aggregate science, I have launched a journal named Aggregate. Okay, so the current impact factor is 13.9, and this is my editorial board, my associate editors, and I hope that if you have a good manuscripts, and I invite you to submit it to our journal for publication. Okay, so in a few days we have the 6th International Conference of Aggregation Using Emission in Boston at Harvard Medical School, and I hope to see you there if you will have time to attend the conference. So now I'm working in Shenzhen at the Chinese University of Hong Kong in Shenzhen, and I welcome to visit us. Thank you very much for your kind attention.
Thank you for your excellent talk and interesting image. Okay, so let's take the question or comment.
Thank you, Professor Tang, for your excellent presentation. AI is a wonderful phenomenon you discover. When you are talking about clusters or the aggregate, I noticed that the size are very similar to the contour dots and nanoparticles. Is it possible to use the contour, like a contour confinement theory to explain your phenomena?
Okay. Yeah, thank you. This is a really excellent question. Okay, so the phenomena is kind of similar to quantum dots because for quantum dots, if you change the size of the quantum dots, you change the color of the emission. Okay, but for our system, I think mechanistically is different. Okay, so probably there's no quantum effect here, but basically you change the extent of through space conjugation, and that will lead to the redshift of the emission. When the cluster size become bigger, you have the gap becomes smaller, and the emission will redshift. So mechanistically, it's a little bit different. But of course, practically, I think our system, in some sense, is better than quantum dots because it's biocompatible, biodegradable. But the difficult thing is that now we have difficulty to get a uniform size of clusters. So we cannot, if we can get a uniform, size of the clusters, then we can systematically study it. Now we only have mixtures. So that's the difficulty we are facing now.
Okay, thank you. You focus on the organic stuff, but some publication extend this phenomena to some metal clusters, right? Some gold nanoparticles, something like that, right? For the metals, are they similar? The mechanism is similar?
Yeah, you are asking a very good question again. Some people are working on metal clusters, like Professor Xie Jinping at Singapore, National University of Singapore, and Professor Zhang Chuanqian at Zhengzhou University. Many people are working on metal clusters, and those metal clusters can emit light. Okay, and also you can change the size, you can change the emission color. I think that those systems are kind of similar to quantum dots. Okay, for our system, it's in some sense it's much simpler. You don't need to spend a lot of effort to make the metal clusters. But the thing is that our system is kind of a mixture at the present time. We are trying, as I mentioned, we are trying to make a uniform size in the future so that probably we can compare with the metal clusters.
Okay, thank you. Okay.
Yeah, thank you.
Okay, the other. Okay. Okay, thank you again to Professor Tang. Okay, thank you.
Yeah, thank you. Thank you.
Okay, let's finish today's session. Okay, thank you very much, all participants. Okay.
Thank you.
Okay, now we have prepared the dinner box, the outside, so you can enjoy the dinner box. Okay, see you tomorrow.